Have you ever been amazed by how Google Home and Amazon Alexa assist in finding information when asked over voice? Or have you ever wondered how e-commerce companies send you personalized emails for shopping suggestions based on the products that you bought online recently? Well, it's all because of machine learning that these virtual assistants and product recommendations work swiftly. In this video, we're going to look at machine learning roadmap for 2022. We will give you the step-by-step process that you need to follow to build a successful career in machine learning. So before we get started, make sure that you subscribe to the Simplilearn channel and hit the bell icon to never miss an update from Simplilearn. So what is machine learning? Machine learning is a subset of artificial intelligence that uses data, algorithms, and statistical techniques to build intelligent systems. These systems learn by themselves and improve with experience. The goal of machine learning is to create computer models that can imitate human behavior. Machine learning has found its usage in almost every business sector. From self-driving cars, medical imaging and diagnostics, speech recognition, facial recognition, to online fraud detection, all of these are possible because of machine learning. In recent years, AI and ML technologies have made several breakthroughs, and the rising demand for AI applications across different industries has led to the significant growth of machine learning. As per marketsandmarkets.com, the machine learning market is expected to grow to $9 billion by 2022 at a CAGR of 44%. Another report from verifiedmarketresearch.com suggests that the machine learning market was valued at $2.4 billion in 2019 and is projected to reach $47.29 million by 2027, growing at a CAGR of 44.9% from 2020 to 2027. Keeping these facts and forecasts in mind, let's look at the roadmap and critical skills required to build a career in machine learning. First and foremost is programming skills. For a machine learning engineer, programming languages form the building blocks to develop complex machine learning models. You need to learn at least one programming language, preferably Python or R. You should be familiar with various computer science concepts such as data structures including stack, queues, trees, and graphs, algorithms for searching and sorting, dynamic and greedy programming, space and time complexity, etc. You also need to know libraries like NumPy, Pandas, Matplotlib, Seaborn, dplyr, Tidyr, and ggplot for data analysis and visualization. The second skill you need to possess is applied mathematics. While solving business problems using machine learning, you have to use machine learning algorithms. To understand the mechanisms behind the algorithms, you need to have a good knowledge of mathematical concepts such as linear algebra, calculus, statistics, and probability. So mathematics in machine learning is not just processing the numbers, but understanding what is happening, why it's happening, and how to obtain the best results. The third skill to become a machine learning expert is data wrangling and SQL. Data analysts and machine learning specialists often work with raw data collected from various sources that are not fit for analysis. It has been observed that 80% of data analysis spend too much time on data wrangling. So it's crucial for machine learning experts to clean, structure, and enrich raw data into desired format and make it ready for analysis using data wrangling techniques. SQL is another crucial set that you should carry. Machine learning tasks involve using data stored in the form of tables that are present inside relational databases. A good understanding of SQL commands enables you to store, manipulate, retrieve, and handle structured data. The next skill set is machine learning algorithms. It's incredibly essential to grasp all the standard machine learning algorithms. Implementing any machine learning techniques requires choosing the suitable model, determining the correct learning method, and an in-depth understanding of hyperparameter tuning. So you should be really good with different supervised, unsupervised, and reinforcement learning algorithms such as linear regression, logistic regression, SVM, KNN, decision trees, K-means clustering, etc. Now coming to the final skill, we have data modeling and evaluation. The objective of a machine learning engineer is to train the best performing model possible. Depending on the problem at hand, you will need to choose a suitable error measure and an evaluation strategy for a machine learning model. The most vulnerable part of a machine learning candidate's resume is the absence of experience working on diverse machine learning projects. With all the essential skills acquired, you can now build an impressive machine learning portfolio highlighting some exciting machine learning projects. Machine learning engineers need a portfolio that showcases their expertise to implement machine learning techniques to real-world problems. With your resume ready, you can now look for the best machine learning jobs in top product companies and startups. You can become a machine learning engineer, a data scientist, a data analyst, or a research scientist. Some of the top companies hiring for machine learning roles are Google, Amazon, IBM, Uber, Gramener, NVIDIA, and LinkedIn. Machine learning engineers are some of the highest paid professionals in the world. According to Glassdoor.com, the national average salary for machine learning engineers in the United States is $1,31,000 per year. In India, you can earn nearly 8 lakh rupees per annum. This salary may vary based on your experience, the industry you are applying for, and the company policy. There are immense opportunities in machine learning for sectors such as e-commerce, manufacturing, logistics, retail, and healthcare. If you are interested in a career in machine learning, then start your journey now with Simplilearn's postgraduate program in AI and machine learning that is in partnership with Purdue University and in collaboration with IBM. You will learn all the in-demand machine learning skills and work on programming with hands-on examples. The program also offers job assistance. To know more about the learning path tools covered and projects that you'll be working on, please click on the course page link in the description below.
In this video, we will cover everything you need to know to become an expert in machine learning. Our experienced instructors with good industry experience will take you through this course. First, you will understand the basics of machine learning from a short animated video. You will then know the essential applications of machine learning. You will understand machine learning concepts and learn why mathematics, statistics, and linear algebra are crucial. Then, we will focus on some vital machine learning algorithms such as linear regression, logistic regression, decision trees, random forest, and k-nearest neighbors. You will also learn about regularization, dimensionality reduction, and principal component analysis. We will perform a prediction analysis on the recently held US elections as well. Finally, you will study the machine learning roadmap for 2021. So let's begin.
We know humans learn from their past experiences, and machines follow instructions given by humans. But what if humans can train the machines to learn from their past data and do what humans can do and much faster? Well, that's called machine learning. But it's a lot more than just learning. It's also about understanding and reasoning. So today, we will learn about the basics of machine learning. So that's Paul. He loves listening to new songs. He either likes them or dislikes them. Paul decides this on the basis of the song's tempo, genre, intensity, and the gender of voice. For simplicity, let's just use tempo and intensity for now. So here, tempo is on the x-axis, ranging from relaxed to fast, whereas intensity is on the y-axis, ranging from light to soaring. We see that Paul likes the song with fast tempo and soaring intensity, while he dislikes the song with relaxed tempo and light intensity. So now we know Paul's choices. Let's say Paul listens to a new song. Let's name it as Song A. Song A has fast tempo and a soaring intensity, so it lies somewhere here. Looking at the data, can you guess whether Paul will like the song or not? Correct. So Paul likes this song. By looking at Paul's past choices, we were able to classify the unknown song very easily, right? Let's say now Paul listens to a new song. Let's label it as Song B. So Song B lies somewhere here with medium tempo and medium intensity. Neither relaxed nor fast, neither light nor soaring. Now can you guess whether Paul likes it or not? Not able to guess whether Paul will like it or dislike it? Are the choices unclear? Correct. We could easily classify song A. But when the choice became complicated, as in the case of song B, yes, and that's where machine learning comes in. Let's see how. In the same example, for song B, if we draw a circle around the song B, we see that there are 4 votes for like, whereas 1 vote for dislike. If we go for the majority votes, we can say that Paul will definitely like the song. That's all. This was a basic machine learning algorithm also. It's called k-nearest neighbors. So this is just a small example in one of the many machine learning algorithms. Quite easy, right? Believe me, it is. But what happens when the choices become complicated, as in the case of song B? That's when machine learning comes in. It learns the data, builds the prediction model, and when the new data point comes in, it can easily predict for it. More the data, better the model, higher will be the accuracy. There are many ways in which the machine learns. It could be either supervised learning, unsupervised learning, or reinforcement learning. Let's first quickly understand supervised learning. Suppose your friend gives you 1 million coins of 3 different currencies, say 1 rupee, 1 euro and 1 dirham. Each coin has different weights. For example, a coin of 1 rupee weighs 3 grams, 1 euro weighs 7 grams and 1 dirham weighs 4 grams. Your model will predict the currency of the coin. Here, your weight becomes the feature of coins, while currency becomes their label. When you feed this data to the machine learning model, it learns which feature is associated with which label. For example, it will learn that if a coin is of 3 grams, it will be a 1 rupee coin. Let's give a new coin to the machine. On the basis of the weight of the new coin, your model will predict the currency. Hence, supervised learning uses labeled data to train the model. Here the machine knew the features of the object and also the labels associated with those features. On this note, let's move to unsupervised learning and see the difference. Suppose you have cricket dataset of various players with their respective scores and wickets taken. When we feed this dataset to the machine identifies the pattern of player performance. So it plots this data with the respective wickets on the x-axis while runs on the y-axis. While looking at the data, you will clearly see that there are 2 clusters. The one cluster are the players who scored high runs and took less wickets, while the other cluster is of the players who scored less runs but took many wickets. So here we interpret these 2 clusters as batsmen and bowlers. The important point to note here is that there were no labels of batsmen and bowlers. Hence, the learning with unlabeled data is unsupervised learning. So we saw supervised learning where the data was labeled and the unsupervised learning where the data was unlabeled. And then there is reinforcement learning, which is reward-based learning, or we can say that it works on the principle of feedback. Here, let's say you provide the system with an image of a dog and ask it to identify it. The system identifies it as a cat. So you give a negative feedback to the machine saying that it's a dog's image. The machine will learn from the feedback, and finally if it comes across any other image of a dog, it will be able to classify it correctly. That is reinforcement learning. To generalize machine learning model, let's see a flowchart. Input is given to a machine learning model, which then gives the output according to the algorithm applied. If it's right, we take the output as a final result. Else, we provide feedback to the training model and ask it to predict until it learns. I hope you've understood supervised and unsupervised learning. So let's have a quick quiz. You have to determine whether the given scenarios uses supervised or unsupervised learning. Simple, right? Scenario 1. Facebook recognizes your friend in a picture from an album of tagged photographs. Scenario 2. Netflix recommends new movies based on someone's past movie choices. Scenario 3. Analyzing bank data for suspicious transactions and flagging the fraud transactions. Think wisely and comment below your answers. Moving on, don't you sometimes wonder how is machine learning possible in today's era? Well, that's because today we have humongous data available. Everybody is online, either making a transaction or just surfing the internet, and that's generating a huge amount of data every minute. And that data, my friend, is the key to analysis. Also, the memory handling capabilities of computers have largely increased, which helps them to process such a huge amount of data at hand without any delay. And yes, computers now have great computational powers. So there are a lot of applications of machine learning out there. To name a few, machine learning is used in healthcare, where diagnostics are predicted for doctors' review. The sentiment analysis that the tech giants are doing on social media is another interesting application of machine learning. Fraud detection in the finance sector and also to predict customer churn in the e-commerce sector. While booking a cab, you must have encountered surge pricing often, where it says the fare of your trip has been updated. Continue booking? Yes, please, I'm getting late for office. Well, that's an interesting machine learning model which is used by global taxi giant Uber and others, where they have differential pricing in real time based on demand, the number of cars available, bad weather, rush hour, etc. So they use the surge pricing model to ensure that those who need a cab can get one. Also, it uses predictive modeling to predict where the demand will be high, with the goal that drivers can take care of the demand and surge pricing can be minimized. Great! Hey Siri, can you remind me to book a cab at 6 p.m. today?
Okay, I'll remind you.
Thanks.
No problem.
Comment below some interesting everyday examples around you where machines are learning and doing amazing jobs. So that's all for machine learning basics today from my side.
Machine learning has improved our lives in a number of wonderful ways. Today, let's talk about some of these. I'm Rahul from Simplilearn, and these are the top 10 applications of machine learning. First, let's talk about virtual personal assistants. Google Assistant, Alexa, Cortana, and Siri. Now, we've all used one of these at least at some point in our lives. Now, these help improve our lives in a great number of ways. For example, you could tell them to call someone. You could tell them to play some music. You could tell them to even schedule an appointment. So how do these things actually work? First, they record whatever you're saying, send it over to a server, which is usually in a cloud, decode it with the help of machine learning and neural networks, and then provide you with an output. So if you've ever noticed that these systems don't work very well without the internet, that's because the server couldn't be contacted. Next, let's talk about traffic predictions. Now say I wanted to travel from Buckingham Palace to Lord's Cricket Ground. The first thing I would probably do is to get on Google Maps. So, search it. And let's put it here. So here we have the path you should take to get to Lord's Cricket Ground. Now here the map is a combination of red, yellow and blue. Now the blue regions signify a clear road, that is you won't encounter traffic there. The yellow indicate that they are slightly congested and red means they're heavily congested. So let's look at the map, a different version of the same map, and here, as I told you before, red means heavily congested, yellow means slow moving and blue means clear. So how exactly is Google able to tell you that the traffic is clear, slow moving or heavily congested? So this is with the help of machine learning and with the help of two important measures. First is the average time that's taken on specific days at specific times on that route. The second one is the real-time location data of vehicles from Google Maps and with the help of sensors. Some of the other popular map services are Bing Maps, Maps.me, and here we go. Next up, we have social media personalization. So say I want to buy a drone and I'm on Amazon and I want to buy a DJI Mavic Pro. The thing is it's close to 1 lakh, so I don't want to buy it right now. But the next time I'm on Facebook, I'll see an advertisement for the product. The next time I'm on YouTube, I'll see an advertisement. Even on Instagram, I'll see an advertisement. So here, with the help of machine learning, Google has understood that I'm interested in this particular product. Hence, it's targeting me with these advertisements. This is also with the help of machine learning. Let's talk about email spam filtering. Now, this is the spam that's in my inbox. Now, how does Gmail know what's spam and what's not spam? So Gmail has an entire collection of emails which have already been labeled as spam or not spam. So after analyzing this data, Gmail is able to find some characteristics like the word lottery or winner. From then on, any new email that comes to your inbox goes through a few spam filters to decide whether it's spam or not. Now, some of the popular spam filters that Gmail uses is content filters, header filters, general blacklist filters, and so on. Next, we have online fraud detection. Now, there are several ways that online fraud can take place. For example, there's identity theft, where they steal your identity, fake accounts, where these accounts only last for how long the transaction takes place and stop existing after that, and man-in-the-middle attacks, where they steal your money while the transaction is taking place. The feed-forward neural network helps determine whether a transaction is genuine or fraudulent. So what happens with feed-forward neural networks are that the outputs are converted into hash values, and these values become the inputs for the next round. So for every real transaction that takes place, there's a specific pattern. A fraudulent transaction would stand out because of the significant changes that it would cause with the hash values. Stock market trading. Machine learning is used extensively when it comes to stock market trading. Now you have stock market indices like Nikkei. They use long short-term memory neural networks. Now these are used to classify, process and predict data when there are time lags of unknown size and duration. Now this is used to predict stock market trends. Assistive medical technology. Now, medical technology has been innovated. With the help of machine learning, diagnosing diseases has been easier, from which we can create 3D models that can predict where exactly there are lesions in the brain. It works just as well for brain tumors and ischemic stroke lesions. They can also be used in fetal imaging and cardiac analysis. Now, some of the medical fields that machine learning will help assist in is disease identification, personalized treatment, drug discovery, clinical research, and radiology. And finally, we have automatic translation. Now, say you're in a foreign country and you see billboards and signs that you don't understand. That's where automatic translation comes of help. Now, how does automatic translation actually work? The technology behind it is the same as the sequence-to-sequence learning, which is the same thing that's used with chatbots. Here, the image recognition happens using convolutional neural networks, and the text is identified using optical character recognition. Furthermore, the sequence-to-sequence algorithm is also used to translate the text from one language to the other.
Hello and welcome to Machine Learning Tutorial Part 1. This is Part 1 of a machine learning series put on by Simplilearn. My name is Richard Kirschner. I'm with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. What's in it for you today? Well, we'll start off with a brief explanation of why machine learning and what is machine learning. And then we'll get into a few of the types of machine learning. Machine learning algorithms, linear regression, decision trees, support vector machine, and finally we'll do a use case where we're going to classify whether a recipe is of a cupcake or a muffin using the SVM or the support vector machine. Sounds like a delicious way to explore machine learning. So why machine learning? Why do we even care about having these computers come up and be able to do all these new things for us? Well, because machines can now drive your car for you. It's still very in the infant stage, but it's just exploding, as we see with Google's Waymo, and then Uber had their program, which unfortunately crashed. They know that this is huge. This is going to be the huge industry to change our whole transportation infrastructure. Machine learning is now used to detect over 50 eye diseases. Do you know how amazing that is, to have a computer that double checks for the doctor for things they might miss? That's just huge in the health industry. Pretty soon they actually do already have that in some areas where maybe not for eyes, but for other diseases where they're using the camera on your phone to help pre-diagnose before you go in and see the doctor. And because the machine can now unlock your phone with your face. I mean, that's just cool, having it being able to identify your face or your voice and be able to turn stuff on and off for you depending on where you're at and what you need. Talking about an ultimate automation, our world we live in. And as we dig in deeper, we have a nice example of Facebook. As you can see here, they have the Facebook post with Halloween. Comment yes if you want it. Order here. Nobody likes spam posts on Facebook that annoy them into interacting with likes, shares, comments, and other actions. I remember the original ones were all, if you don't click on here, you will have bad luck or some kind of fear factor. Well, this is a huge thing in a social media when people are getting spammed, and so this tactic, known as engagement bait, takes advantage of Facebook's newsfeed algorithm by choosing engagement in order to get the greater reach. To eliminate engagement bait, the company reviewed and categorized hundreds of thousands of posts to train a machine learning model that detects different types of engagement bait. So in this case we're using Facebook, but this is of course across all the different social media. They have different tools they're building, and the Facebook scroll GIF will be replaced. Kind of like a virus coming in there. It notices that there's a certain setup with Facebook and it's able to replace it. And they have like vote baiting, react baiting, share baiting. They have all these are kind of general titles, but there certainly are a lot of ways of baiting you to go in there and click on something. So they fed all this data was fed into the machine, and then they have the new post. The new post comes up that takes over part of the Facebook setup. And that's what you're looking at. You're looking at this new post that's replaced, like a virus has replaced that. So what Facebook did to eliminate this is they start scanning for keywords and phrases like this and checks the click-through rate. So it starts looking for people who are clicking through it without even looking at it, or clicking through it and it's not something that normally would be clicked through. Once Facebook has scanned for these keywords and phrases, it is now able to identify the spam coming in. And this makes your life easier, so you're not getting spammed. It's not like walking through an airport, and in a lot of countries you have like hundreds of people trying to sell you timeshare. Come join us, sign up for this. Eliminates that annoyingness, so now you can just enjoy your Facebook and your cat pictures, or maybe it's your family pictures. Mine is family. Certainly people like their cat pictures too. Another good example is Google's DeepMind project AlphaGo. A computer program that plays a board game Go has defeated the world's #1 Go player, and I hope I say his name right, Kiji. The Ultimate Go Challenge game of 3 of 3 was on May 27th, 2017, so it was just last year that this happened. And what makes this so important is that, Go is a game, so it's not like you're driving a car or something in our real world, but they are using games to learn how to get the machine learning program to learn. They want it to learn how to learn. And that is a huge step. A lot of this is still in its infant stage as far as development, as we saw what happened with the, as I referred to earlier, the Uber cars. They lost their whole division because they jumped ahead too fast. So it's still an infant stage, but boy, is this like the beginning of just an amazing world that is automated in ways we can't even imagine what tomorrow's going to look like. We've looked at a lot of examples of machine learning, so let's see if we can give a little bit more of a concrete definition. What is machine learning? Machine learning is the science of making computers learn and act like humans by feeding data and information without being explicitly programmed. And we see here we have a nice little diagram where we have our ordinary system. Your computer, nowadays you can even run a lot of this stuff on a cell phone because cell phones have advanced so much. And then with artificial intelligence and machine learning, it now takes the data and it learns from what happened before. And then it predicts what's going to come next. And then really the biggest part right now in machine learning that's going on is it improves on that. How do we find a new solution? So we go from descriptive, where it's learning about stuff and understanding how it fits together, to predicting what it's going to do, to post-scripting, coming up with a new solution. And when we're working on machine learning, there's a number of different diagrams that people have posted for what steps to go through. A lot of it might be very domain specific. So if you're working on photo identification versus language versus medical or physics, some of these are switched around a little bit or new things are put in. They're very specific to the domain. This is kind of a very general diagram. First, you want to define your objective. Very important to know what it is you're wanting to predict. Then you're going to be collecting the data. So once you've defined an objective, you need to collect the data that matches. You spend a lot of time in data science collecting data, and the next step, preparing the data. You got to make sure that your data is clean going in. There's the old saying, bad data in, bad answer out, or bad data out. And then once you've gone through and we've cleaned all this stuff coming in, then you're going to select the algorithm. Which algorithm are you going to use? You're going to train that algorithm. In this case, I think we're going to be working with SVM, the support vector machine. Then you have to test the model. Does this model work? Is this a valid model for what we're doing? And then once you've tested it, you want to run your prediction. You want to run your prediction or your choice or whatever output it's going to come up with. And then once everything is set and you've done lots of testing, then you want to go ahead and deploy the model. And remember I said domain specific. This is very general as far as the scope of doing something. A lot of models, you get halfway through and you realize that your data is missing something and you have to go collect new data because you've run a test in here someplace along the line. You're saying, hey, I'm not really getting the answers I need. So there's a lot of things that are domain specific that become part of this model. This is a very general model, but it's a very good model to start with. And we do have some basic divisions of what machine learning does that's important to know. For instance, do you want to predict a category? Well, if you're categorizing things, that's classification. For instance, whether the stock price will increase or decrease. So in other words, I'm looking for a yes-no answer. Is it going up or is it going down? And in that case, we'd actually say, is it going up? True. If it's not going up, it's false, meaning it's going down. This way, it's a yes-no, 0, 1. Do you want to predict a quantity? That's regression. So remember, we just did classification. Now we're looking at regression. These are the two major divisions in what data is doing. For instance, predicting the age of a person based on the height, weight, health, and other factors. So based on these different factors, you might guess how old a person is. And then there are a lot of domain-specific things, like do you want to detect an anomaly? That's anomaly detection. And this is actually very popular right now. For instance, you want to detect money withdrawal anomalies. You want to know when someone's making a withdrawal that might not be their own account. We've actually brought this up because this is really big right now. If you're predicting the stock, whether to buy stock or not, you want to be able to know if what's going on in the stock market is an anomaly. Use a different prediction model because something else is going on. You got to pull out new information in there. Or is this just the norm? I'm going to get my normal return on my money invested. So being able to detect anomalies is very big in data science these days. Another question that comes up, which is on what we call untrained data, is do you want to discover structure in unexplored data? And that's called clustering. For instance, finding groups of customers with similar behavior given a large database of customer data containing their demographics and past buying records. And in this case, we might notice that anybody who's wearing a certain set of shoes goes shopping at certain stores, or whatever it is, they're going to make certain purchases. By having that information, it helps us to market or group people together so that we can now explore that group and find out what it is we want to market to them if you're in the marketing world. And that might also work in just about any arena. You might want to group people together, whether they're based on their different areas and investments and financial background, whether you're going to give them a loan or not. Before you even start looking at whether they're a valid customer for the bank, you might want to look at all these different areas and group them together based on unknown data. So you don't know what the data is going to tell you, but you want to cluster people together that come together. Let's take a quick detour for quiz time. Oh, my favorite. So we're going to have a couple questions here under our quiz time. And we'll be posting the answers in the part 2 of this tutorial. So let's go ahead and take a look at these quiz times questions, and hopefully you'll get them all right, and it'll get you thinking about how to process data and what's going on. Can you tell what's happening in the following cases? Of course, you're sitting there with your cup of coffee, and you have your checkbox and your pen trying to figure out what's your next step in your data science analysis. So the first one is grouping documents into different categories based on the topic and content of each document. Very big these days. You have legal documents, you have maybe it's a sports group documents, maybe you're analyzing newspaper postings. But certainly having that automated is a huge thing in today's world. B, identifying handwritten digits in images correctly. So we want to know whether they're writing an A or capital A, B, C. What are they writing out in their handwriting? C, behavior of a website indicating that the site is not working as designed. D, predicting salary of an individual based on his or her years of experience. Boy, HR hiring set up there. So stay tuned for part 2. We'll go ahead and answer these questions when we get to the part 2 of this tutorial. Or you can just simply write at the bottom and send a note to Simplilearn, and they'll follow up with you on it. Back to our regular content. And these last few bring us into the next topic, which is another way of dividing our types of machine learning, and that is with supervised, unsupervised, and reinforcement learning. Supervised learning is a method used to enable machines to classify, predict objects, problems, or situations based on labeled data fed to the machine. And in here you see we have a jumble of data with circles, triangles, and squares, and we label them. We have what's a circle, what's a triangle, what's a square. And we have our model training, and it trains it so we know the answer. Very important, when you're doing supervised learning, you already know the answer to a lot of your information coming in. So you have a huge group of data coming in, and then you have new data coming in. So we've trained our model. The model now knows the difference between a circle, a square, a triangle. And now that we've trained it, we can send in this case, a square and a circle goes in, and it predicts that the top one's a square and the next one's a circle. And you can see that this is being able to predict whether someone's going to default on a loan, because I was talking about banks earlier. Supervised learning on stock market, whether you're going to make money or not. That's always important. And if you are looking to make a fortune in the stock market, keep in mind it is very difficult to get all the data correct on the stock market. It is it fluctuates in ways really hard to predict. So it's quite a roller coaster ride. If you're running machine learning on the stock market, you start realizing you really have to dig for new data. So we have supervised learning, and if you have supervised, we should need unsupervised learning. In unsupervised learning, machine learning model finds the hidden pattern in an unlabeled data. So in this case, instead of telling it what the circle is, and what a triangle is, and what a square is, it goes in there and looks at them and says, for whatever reason, it groups them together. Maybe it'll group it by the number of corners. And it notices that a number of them all have 3 corners, a number of them all have 4 corners, and a number of them all have no corners. And it's able to filter those through and group them together. We talked about that earlier with looking at a group of people who are out shopping. We want to group them together to find out what they have in common. And of course, once you understand what people have in common, maybe you have one of them who's a customer at your store, or you have 5 of them are a customer at your store, and they have a lot in common with 5 others who are not customers at your store, how do you market to those 5 who aren't customers at your store yet? They fit the demographics of who's going to shop there, and you'd like them to shop at your store, not the one next door. Of course, this is a simplified version. You can see very easily the difference between a triangle and a circle, which might not be so easy in marketing. Reinforcement learning. Reinforcement learning is an important type of machine learning where an agent learns how to behave in an environment by performing actions and seeing the result. And we have here where in this case, a baby. It's actually great that they used an infant for this slide because the reinforcement learning is very much in its infant stages. But it's also probably the biggest machine learning demand out there right now, or in the future. It's going to be coming up over the next few years, is reinforcement learning and how to make that work for us. And you can see here where we have our action. In the action in this one, it goes into the fire. Hopefully the baby it was just a little candle, not a giant fire pit like it looks like here. When the baby comes out, and the new state is the baby is sad and crying because they got burned on the fire. And then maybe they take another action. The baby's called the agent because it's the one taking the actions. And in this case, they didn't go into the fire. They went a different direction, and now the baby's happy and laughing and playing. Reinforcement learning is very easy to understand because that's how, as humans, that's one of the ways we learn. We learn whether it is, you burn yourself on the stove, don't do that anymore. Don't touch the stove. In the big picture, being able to have a machine learning program or an AI be able to do this is huge because now it's starting to learn how to learn. That's a big jump in the world of computer and machine learning. And we're going to go back and just kind of go back over supervised versus unsupervised learning. Understanding this is huge because this is going to come up in any project you're working on. We have in supervised learning, we have labeled data, we have direct feedback. So someone's already gone in there and said, yes, that's a triangle. No, that's not a triangle. And then you predict an outcome. So you have a nice prediction. This new set of data is coming in and we know what it's going to be. And then with unsupervised training, it's not labeled. So we really don't know what it is. There's no feedback. So we're not telling it whether it's right or wrong. We're not telling it whether it's a triangle or a square. We're not telling it to go left or right. All we do is we're finding hidden structure in the data, grouping the data together to find out what connects to each other. And then you can use these together. So imagine you have an image and you're not sure what you're looking for. So you go in and you have the unstructured data, find all these things that are connected together. And then somebody looks at those and labels them. Now you can take that labeled data and program something to predict what's in the picture. So you can see how they go back and forth and you can start connecting all these different tools together to make a bigger picture. There are many interesting machine learning algorithms. Let's have a look at a few of them. Hopefully this gives you a little flavor of what's out there. And these are some of the most important ones that are currently being used. We'll take a look at linear regression, decision tree, and the support vector machine. Let's start with a closer look at linear regression. Linear regression is perhaps one of the most well-known and well-understood algorithms in statistics and machine learning. Linear regression is a linear model. For example, a model that assumes a linear relationship between the input variables x and the single output variable y. And you'll see this if you remember from your algebra classes, y equals mx plus c. Imagine we are predicting distance traveled y from speed x. Our linear regression model representation for this problem would be y equals m times x plus c, or distance equals m times speed plus c, where m is the coefficient and c is the y-intercept. And we're going to look at two different variations of this. First, we're going to start with time is constant. And you can see we have a bicyclist. He's got his safety gear on, thank goodness. Speed equals 10 meters per second. And so over a certain amount of time, his distance equals 36 kilometers. We have a second bicyclist who's going twice the speed, or 20 meters per second. And you can guess if he's going twice the speed and time is a constant, then he's going to go twice the distance. And that's easily to compute. 36 times 2, you get 72 kilometers. And so if you had the question of how fast would somebody who's going 3 times that speed, or 30 meters per second is, you can easily compute the distance in our head. We can do that without needing a computer. But we want to do this for more complicated data. So it's kind of nice to compare the two. But let's just take a look at that and what that looks like in a graph. So in a linear regression model, we have our distance to the speed, and we have our m equals the VE slope of the line. And we'll notice that the line has a plus slope. And as the speed increases, distance also increases, hence the variables have a positive relationship. And so your speed of the person, which equals y equals mx plus c, distance traveled in a fixed interval of time. And we could very easily compute, either following the line or just knowing it's 3 times 10 meters per second, that this is roughly 102 kilometers distance that this third bicyclist has traveled. One of the key definitions on here is positive relationship. So the slope of the line is positive. As distance increase, so does speed increase. Let's take a look at our second example where we put distance is a constant. So we have speed equals 10 meters per second. They have a certain distance to go, and it takes them 100 seconds to travel that distance. And we have our second bicyclist who's still doing 20 meters per second. Since he's going twice the speed, we can guess that he'll cover the distance in about half the time, 50 seconds. And of course you could probably guess on the third one, 100 divided by 30, since he's going 3 times the speed. You could easily guess that this is 33.333 seconds time. When we put that into a linear regression model or a graph, if the distance is assumed to be constant, let's see the relationship between speed and time. And as time goes up, the amount of speed to go that same distance goes down. So now your m equals a minus VE slope of the line. As the speed increases, time decreases, hence the variable has a negative relationship. Again, there's our definition, positive relationship and negative relationship dependent on the slope of the line. And with a simple formula like this, and even a significant amount of data, let's see with the mathematical implementation of linear regression. And we'll take this data. So suppose we have this data set where we have x, y, x equals 1, 2, 3, 4, 5, standard series, and the y value is 3, 2, 2, 4, 3. When we take that and we go ahead and plot these points on a graph, you can see there's kind of a nice scattering, and you could probably eyeball a line through the middle of it. But we're going to calculate that exact line for linear regression. And the first thing we do is we come up here and we have the mean of xi. And remember, mean is basically the average. So we added 5 plus 4 plus 3 plus 2 plus 1 and divide by 5. And that simply comes out as 3. And then we'll do the same for y. We'll go ahead and add up all those numbers and divide by 5. And we end up with the mean value of y of I equals 2.8. Where the xi references it's an average or means value, and the yi also equals a means value of y. And when we plot that, you'll see that we can put in the y equals 2.8 and the x equals 3 in there on our graph. We kind of gave it a little different color so you could sort it out with the dashed lines on it. And it's important to note that when we do the linear regression model should go through that dot. Now let's find our regression equation to find the best fit line. Remember, we go ahead and take our y equals mx plus c, so we're looking for m and c. So to find this equation for our data, we need to find our slope of m and our coefficient of c. And we have y equals mx plus c, where m equals the sum of x minus x average times y minus y average, or y means and x means, over the sum of x minus x means squared. That's how we get the slope of the value of the line. And we can easily do that by creating some columns here where we have x, y. Computers are really good about iterating through data, and so we can easily compute this and fill in a graph of data. And in our graph, you can easily see that if we have our x value of 1, and if you remember the xi, or the means value, is 3, 1 minus 3 equals a negative 2, and 2 minus 3 equals a negative 1, so on and so forth. And we can easily fill in the column of x minus xi, y minus yi, and then from those we can compute x minus xi squared and x minus xi times y minus yi. And you can guess it that the next step is to go ahead and sum the different columns for the answers we need. So we get a total of 10 for our x minus xi squared, and a total of 2 for x minus xi times y minus yi. And we plug those in, we get 2/10, which equals 0.2. So now we know the slope of our line equals 0.2. So we can calculate the value of c. That'd be the next step, is we need to know where it crosses the y-axis. And if you remember, I mentioned earlier that the linear regression line has to pass through the means value, the one that we showed earlier. We can just flip back up there to that graph, and you can see right here there's our means value, which is 3, x equals 3 and y equals 2.8. And since we know that value, we can simply plug that into our formula, y equals 0.2x plus c. So we plug that in and we get 2.8 equals 0.2 times 3 plus c, and you can just solve for c. So now we know that our coefficient equals 2.2. And once we have all that, we can go ahead and plot our regression line. y equals 0.2 times x plus 2.2. And then from this equation, we can compute new values. So let's predict the values of y using x equals 1, 2, 3, 4, 5 and plot the points. Remember, the 1, 2, 3, 4, 5 was our original x values. So now we're going to see what y thinks they are, not what they actually are. And when we plug those in, we get y of designated with y of p. You can see that x equals 1 equals 2.4, x equals 2 equals 2.6, and so on and so on. So we have our y predicted values of what we think it's going to be when we plug those numbers in. And when we plot the predicted values along with the actual values, we can see the difference. And this is one of the things that's very important with linear regression in any of these models, is to understand the error. And so we can calculate the error on all of our different values. And you can see over here we plotted x and y predict. And we draw in a little line so you can sort of see what the error looks like there between the different points. So our goal is to reduce this error. We want to minimize that error value on our linear regression model. Minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. We keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. So to recap with a very simple linear regression model, we first figure out the formula of our line through the middle, and then we slowly adjust the line to minimize the error. Keep in mind this is a very simple formula. The math gets, even though the math is very much the same, it gets much more complex as we add in different dimensions. So this is only 2 dimensions, y equals mx plus c, but you can take that out to x, z, I, j, q, all the different features in there, and they can plot a linear regression model on all of those using the different formulas to minimize the error. Let's go ahead and take a look at decision trees, a very different way to solve problems in the linear regression model. Decision tree is a tree-shaped algorithm used to determine a course of action. Each branch of a tree represents a possible decision, occurrence, or reaction. We have data which tells us if it is a good day to play golf. And if we were to open this data up in a general spreadsheet, you can see we have the outlook, whether it's rainy, overcast, sunny, temperature, hot, mild, cool, humidity, windy, and did I like to play golf that day, yes or no? So we're taking a census. And certainly I wouldn't want a computer telling me when I should go play golf or not. But you can imagine if you got up in the night before, you're trying to plan your day, and it comes up and says tomorrow would be a good day for golf for you in the morning, and not a good day in the afternoon, or something like that. This becomes very beneficial, and we see this in a lot of applications coming out now where it gives you suggestions and lets you know what would fit the match for you for the next day or the next purchase or the next whatever, next meal out. In this case, is tomorrow a good day for playing golf based on the weather coming in? And so we come up and let's determine if you should play golf when the day is sunny and windy. So we found out the forecast tomorrow is going to be sunny and windy. And suppose we draw our tree like this. We're going to have our humidity, and then we have our normal, which is if you have a normal humidity, you're going to go play golf. And if the humidity is really high, then we look at the outlook. And if the outlook is sunny, overcast, or rainy, it's going to change what you choose to do. So if you know that it's a very high humidity and it's sunny, you're probably not going to play golf because you're going to be out there miserable, fighting off the mosquitoes that are out joining you to play golf with you. Maybe if it's rainy, you probably don't want to play in the rain. But if it's slightly overcast and you get just the right shadow, that's a good day to play golf and be outside, out on the green. Now in this example, you can probably make your own tree pretty easily because it's a very simple set of data going in. But the question is, how do you know what to split? Where do you split your data? What if this is much more complicated data where it's not something that you would particularly understand? Like studying cancer, they take about 36 measurements of the cancerous cells, and then each one of those measurements represents how bulbous it is, how extended it is, how sharp the edges are. Something that as a human we would have no understanding of. So how do we decide how to split that data up? And is that the right decision tree? So that's a question that's going to come up. Is this the right decision tree? For that, we should calculate entropy and information gain. Two important vocabulary words there are the entropy and the information gain. Entropy. Entropy is a measure of randomness or impurity in the data set. Entropy should be low. So we want the chaos to be as low as possible. We don't want to look at it and be confused by the images or what's going on there with mixed data. And the information gain. It is the measure of decrease in entropy after the data set is split, also known as entropy reduction. Information gain should be high, so we want our information that we get out of the split to be as high as possible. Let's take a look at entropy from the mathematical side. In this case, we're going to denote entropy as I of P of and N, where P is the probability that you're going to play a game of golf, and N is the probability where you're not going to play the game of golf. Now, you don't really have to memorize these formulas. There's a few of them out there depending on what you're working with. But it's important to note that this is where this formula is coming from, so when you see it, you're not lost when you're running your programming, unless you're building your own decision tree code in the back. And we simply have a log squared of P over P plus N minus N over P plus N times the log squared of N of P plus N. But let's break that down and see what it actually looks like when we're computing that from the computer script side. Entropy of a target class of the data set is the whole entropy. So we have entropy play golf. And when we look at this, if we go back to the data, you can simply count how many yeses and no in our complete data set for playing golf days. In our complete set, we find we have 5 days we did play golf and 9 days we did not play golf. And so our I equals, if you add those together, 9 plus 5 is 14. And so our I equals 5 over 14 and 9 over 14. That's our P and N values that we plug into that formula. And you can go to 5 over 14 equals 0.36, 9 over 14 equals 0.64. And when you do the whole equation, you get the minus 0.36 log root squared of 0.36 minus 0.64 log squared root of 0.64. And we get a set value. We get 0.94. So we now have a full entropy value for the whole set of data that we're working with. And we want to make that entropy go down. And just like we calculated the entropy out for the whole set, we can also calculate entropy for playing golf and the outlook. Is it going to be overcast or rainy or sunny? And so when we look at the entropy, we have P of sunny times E of 3 of 2. And that just comes out how many sunny days yes and how many sunny days no over the total, which is 5. Don't forget to put we'll divide that 5 out later on. Equals P overcast equals 4, 0 plus rainy equals 2, 3. And then when you do the whole setup, we have 5 over 14. Remember I said there was a total of 5? 5 over 14 times the I of 3 of 2 plus 4 over 14 times the 4, 0 and 514 over I of 2, 3. And so we can now compute the entropy of just the part that has to do with the forecast. And we get 0.693. Similarly, we can calculate the entropy of other predictors like temperature, humidity, and wind. And so we look at the gain outlook. How much are we going to gain from this? Entropy play golf minus entropy play golf outlook. And we can take the original 0.94 for the whole set minus the entropy of just the rainy day and temperature, and we end up with a gain of 0.247. So this is our information gain. Remember, we define entropy and we define information gain. The higher the information gain, the lower the entropy, the better. The information gain of the other 3 attributes can be calculated in the same way. So we have our gain for temperature equals 0.029. We have our gain for humidity equals 0.152, and our gain for a windy day equals 0.048. And if you do a quick comparison, you'll see the 0.247 is the greatest gain of information, so that's the split we want. Now let's build the decision tree. So we have the outlook. Is it going to be sunny, overcast, or rainy? That's our first split because that gives us the most information gain. And we can continue to go down the tree using the different information gains with the largest information. We can continue down the nodes of the tree where we choose the attribute with the largest information gain as the root node and then continue to split each subnode with the largest information gain that we can compute. And although it's a little bit of a tongue twister to say all that, you can see that it's a very easy to view visual model. We have our outlook, we split it 3 different directions. If the outlook is overcast, we're going to play. And then we can split those further down if we want. So if the outlook is sunny, but then it's also windy, if it's windy, we're not going to play. If it's not windy, we'll play. So we can easily build a nice decision tree to guess what we would like to do tomorrow and give us a nice recommendation for the day. So we want to know if it's a good day to play golf when it's sunny and windy. Remember the original question that came out? Tomorrow's weather report is sunny and windy. You can see by going down the tree, we go outlook sunny, outlook windy, we're not going to play golf tomorrow. So our little smartwatch pops up and says, I'm sorry, tomorrow's not a good day for golf. It's going to be sunny and windy. And if you're a huge golf fan, you might go, uh-oh, it's not a good day to play golf. We can go in and watch a golf game at home. So we'll sit in front of the TV instead of being out playing golf in the wind. Now that we looked at our decision tree, let's look at the third one of our algorithms we're investigating. Support vector machine. Support vector machine is a widely used classification algorithm. The idea of support vector machine is simple. The algorithm creates a separation line which divides the classes in the best possible manner. For example, dog or cat, disease or no disease. Suppose we have a labeled sample data which tells height and weight of males and females. A new data point arrives and we want to know whether it's going to be a male or a female. So we start by drawing a line. We draw decision lines, but if we consider decision line 1, then we will classify the individual as a male. And if we consider decision line 2, then it will be a female. So you can see this person kind of lies in the middle of the two groups, so it's a little confusing trying to figure out which line they should be under. We need to know which line divides the classes correctly, but how? The goal is to choose a hyperplane, and that is one of the key words they use when we talk about support vector machines. Choose a hyperplane with the greatest possible margin between the decision line and the nearest point within the training set. So you can see here we have our support vector, we have the two nearest points to it, and we draw a line between those 2 points. And the distance margin is the distance between the hyperplane and the nearest data point from either set. So we actually have a value, and it should be equally distant between the two points that we're comparing it to. When we draw the hyperplanes, we observe that line 1 has a maximum distance. So we observe that line 1 has a maximum distance margin, so we'll classify the new data point correctly. And our result on this one is going to be that the new data point is male. One of the reasons we call it a hyperplane versus a line is that a lot of times we're not looking at just weight and height. We might be looking at 36 different features or dimensions. And so when we cut it with a hyperplane, it's more of a three-dimensional cut in the data, or multi-dimensional. It cuts the data a certain way. And each plane continues to cut it down until we get the best fit or match. Let's understand this with the help of an example. Problem statement. I always start with a problem statement when you're going to put some code together. We're going to do some coding now. Classifying muffin and cupcake recipes using support vector machines. So the cupcake versus the muffin. Let's have a look at our data set. And we have the different recipes here. We have a muffin recipe that has so much flour. I'm not sure what measurement 55 is in, but it has 55, maybe it's ounces? But it has a certain amount of flour, a certain amount of milk, sugar, butter, egg, baking powder, vanilla, and salt. And so based on these measurements, we want to guess whether we're making a muffin or a cupcake. And you can see in this one, we don't have just two features. We don't just have height and weight as we did before between the male and female. In here, we have a number of features. In fact, in this, we're looking at 8 different features to guess whether it's a muffin or a cupcake. What's the difference between a muffin and a cupcake? Turns out muffins have more flour, while cupcakes have more butter and sugar. So basically the cupcake's a little bit more of a dessert, where the muffin's a little bit more of a fancy bread. But how do we do that in Python? How do we code that to go through recipes and figure out what the recipe is? And I really just want to say cupcakes versus muffins, like some big professional wrestling thing. Before we start in our cupcakes versus muffins, we are going to be working in Python. There's many versions of Python, many different editors. That is one of the strengths and weaknesses of Python, is it just has so much stuff attached to it, and it's one of the more popular data science programming packages you can use. In this case, we're going to go ahead and use Anaconda and Jupyter Notebook. The Anaconda Navigator has all kinds of fun tools. Once you're into the Anaconda Navigator, you can change environments. I actually have a number of environments on here. We'll be using Python 3.6 environment. So this is in Python version 3.6. Although it doesn't matter too much which version you use. I usually try to stay with the 3x because they're current, unless you have a project that's very specifically in version 2x. 2.7 I think is usually what most people use in the version 2. And then once we're in our Jupyter Notebook editor, I can go up and create a new file. And we'll just jump in here. In this case, we're doing SVM muffin versus cupcake. And then let's start with our packages for data analysis. And we almost always use there's a few very standard packages we use. We use import numpy, that's for number Python. And they usually denote it as NP, that's very common. And then we're going to import pandas as PD. And numpy deals with number arrays. There's a lot of cool things you can do with the numpy setup as far as multiplying all the values in an array, in a numpy array, data array. Pandas, I can't remember if we're using it actually in this data set. I think we do as an import. It makes a nice data frame. And the difference between a data frame and a numpy array is that a data frame is more like your Excel spreadsheet. You have columns, you have indexes, so you have different ways of referencing it, easily viewing it, and there's additional features you can run on a data frame. And Pandas kind of sits on numpy, so you need them both in there. And then finally, we're working with the support vector machine. So from sklearn, we're going to use the sklearn model, import svm, support vector machine. And then as a data scientist, you should always try to visualize your data. Some data obviously is too complicated or doesn't make any sense to the human. But if it's possible, it's good to take a second look at it so that you can actually see what you're doing. Now for that, we're going to use two packages. We're going to import matplotlibary.pyplot as PLT. Again, very common. And we're going to import Seaborn as SNS. And we'll go ahead and set the font scale in the SNS right in our import line. That's what this semicolon followed by a line of data. We're going to set the SNS. And these are great because the Seaborn sits on top of matplotlibary, just like Pandas sits on numpy. So it adds a lot more features and uses and control. We're obviously not going to get into matplotlibary and Seaborn. That'd be its own tutorial. We're really just focusing on the SVM, the support vector machine from sklearn. And since we're in Jupyter Notebook, we have to add a special line in here for our matplotlibary. And that's your percentage sign or ampersand matplotlibary in line. Now, if you're doing this in just a straight code project, a lot of times I use like Notepad++, and I'll run it from there. You don't have to have that line in there because it'll just pop up as its own window on your computer, depending on how your computer's set up. Because we're running this in the Jupyter Notebook as a browser setup, this tells it to display all of our graphics right below on the page. So that's what that line is for. I remember the first time I ran this, I didn't know that, and I had to go look that up years ago. It was quite a headache. So matplotlibary inline is just because we're running this on the web setup. And we can go ahead and run this, make sure all our modules are in. They're all imported, which is great. If you don't have them import, you'll need to go ahead and pip, use the PIP or however you do it. There's a lot of other install packages out there, although pip is the most common. And you have to make sure these are all installed on your Python setup. The next step, of course, is we got to look at the data. You can't run a model for predicting data if you don't have actual data. So to do that, let me go ahead and open this up and take a look. And we have our cupcakes versus muffins. And it's a CSV file, or .csv, meaning that it's comma-separated variable. And it's going to open it up in a nice spreadsheet for me. And you can see up here we have the type. We have muffin, 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 cupcake, cupcake, cupcake. And then it's broken up into flour, milk, sugar, butter, egg, baking powder, vanilla, and salt. So what we can do is we can go ahead and look at this data also in our Python. Let us create a variable recipes equals, we're going to use our pandas module, .read CSV. Remember, it's a comma-separated variable. And the file name happened to be cupcakes versus muffins. Oops, I got double brackets there. Do it this way. There we go. Cupcakes versus muffins. Because the program I loaded, or the place I saved this particular Python program is in the same folder, we can get by with just the file name. But remember, if you're storing it in a different location, you have to also put down the full path on there. And then because we're in pandas, we're going to go ahead and you can actually, inline you can do this, but let me do the full print. You can just type in recipes.head in the Jupyter Notebook. But if you're running in code in a different script, you need to go ahead and type out the whole print recipes.head. And Pandas knows that that's going to do the first 5 lines of data. And if we flip back on over to the spreadsheet where we opened up our CSV file, you can see where it starts on line 2. This one calls it 0, and then 2, 3, 4, 5, 6 is going to match. Go and close that out because we don't need that anymore. And it always starts at 0. And it automatically indexes it since we didn't tell it to use an index in here. So that's the index number for the left-hand side. And it automatically took the top row as labels. So Pandas using it to read a CSV is just really slick and fast. One of the reasons we love our pandas. Not just because they're cute and cuddly teddy bears. And let's go ahead and plot our data. And I'm not going to plot all of it. I'm just going to plot the sugar and flour. Now obviously you can see where they get really complicated if we have tons of different features. And so you'll break them up and maybe look at just 2 of them at a time to see how they connect. And to plot them, we're going to go ahead and use Seaborn. So that's our SNS. And the command for that is sns.lmplot. And then the 2 different variables I'm going to plot is flour and sugar. Data equals recipes. The hue equals type. And this is a lot of fun because it knows that this is pandas coming in. So this is one of the powerful things about pandas mixed with Seaborn and doing graphing. And then we're going to use a palette set 1. There's a lot of different sets in there. You can go look them up for Seaborn. We'll do a fit regular equals false, so we're not really trying to fit anything. And it's a scatter, KWS. A lot of these settings you can look up in Seaborn. Half of these you could probably leave off when you run them. Somebody played with this and found out that these were the best settings for doing a Seaborn plot. And let's go ahead and run that. And because it does it in line, it just puts it right on the page. And you can see right here that just based on sugar and flour alone, there's a definite split. And we use these models because you can actually look at it and say, hey, if I drew a line right between the middle of the blue dots and the red dots, we'd be able to do an SVM and a hyperplane right there in the middle. Then the next step is to format or pre-process our data. And we're going to break that up into 2 parts. We need a type label, and remember, we're going to decide whether it's a muffin or a cupcake. Well, a computer doesn't know muffin or cupcake, it knows 0 and 1. So, what we're going to do is we're going to create a type label, and from this we'll create a numpy array, np, where, and this is where we can do some logic. We take our recipes from our panda, and wherever type equals muffin, it's going to be 0. And then if it doesn't equal muffin, which is cupcakes, it's going to be 1. So we create our type label. This is the answer. So when we're doing our training model, remember we have to have a training data. This is what we're going to train it with, is that it's 0 or 1. It's a muffin or it's not. And then we're going to create our recipe features. And if you remember correctly from right up here, the first column is type. So we really don't need the type column because that's our muffin or cupcake. And in pandas, we can easily sort that out. We take our value recipes dot columns. That's a pandas function built into pandas. Dot values, converting them to values. So it's just the column titles going across the top. And we don't want the first one. So what we do is, since it always starts at 0, we want 1 colon till the end. And then we want to go ahead and make this a list, and this converts it to a list of strings. And then we can go ahead and just take a look and see what we're looking at for the features, make sure it looks right. Let me go ahead and run that. And I forgot the S on recipes, so we'll go ahead and add the S in there and then run that. And we can see we have flour, milk, sugar, butter, egg, baking powder, vanilla, and salt. And that matches what we have up here, right where we printed out everything but the type. So we have our features and we have our label. Now, the recipe features is just the titles of the columns, and we actually need the ingredients. And at this point, we have a couple options. One, we could run it over all the ingredients. And when you're doing this, usually you do. But for our example, we want to limit it so you can easily see what's going on. Because if we did all the ingredients, we have, that's what, 7, 8 different hyperplanes that would be built into it. We only want to look at one so you can see what the SVM is doing. And so we'll take our recipes and we'll do just flour and sugar. Again, you can replace that with your recipe features and do all of them, but we're going to do just flour and sugar, and we're going to convert that to values. We don't need to make a list out of it because it's not string values. These are actual values on there. And we can go ahead and just print ingredients, and you can see what that looks like. And so we have just the amount of flour and sugar, just the 2 sets of plots. And just for fun, let's go ahead and take this over here and take our recipe features. And so if we decided to use all the recipe features, you'll see that it makes a nice column of different data. So it just strips out all the labels and everything, and we just have just the values. But because we want to be able to view this easily in a plot later on, we'll go ahead and take that and just do flour and sugar. And we'll run that and you'll see it's just the 2 columns. So the next step is to go ahead and fit our model. We'll go ahead and just call it model. And it's a SVM. We're using a package called SVC. In this case, we're going to go ahead and set the kernel equals linear. So it's using a specific setup on there. And if we go to the reference on their website for the SVM, you'll see that there's 8 of them here. 3 of them are for regression. 3 are for classification. The SVC, support vector classification, is probably one of the most commonly used. And then there's also one for detecting outliers, and another one that has to do with something a little bit more specific on the model. But SVC and SVR are the 2 most commonly used, standing for support vector classifier and support vector regression. Remember, regression is an actual value, a float value or whatever you're trying to work on. And SVC is a classifier, so it's a yes, no, true, false. But for this, we want to know 0, 1, muffin, cupcake. We go ahead and create our model. And once we have our model created, we're going to do model.fit. And this is very common, especially in the sklearn. All their models are followed with the fit command. And what we put into the fit, what we're training with it, is we're putting in the ingredients, which in this case we limited to just flour and sugar. And the type label, is it a muffin or a cupcake? Now, in more complicated data science series, you'd want to split into, we won't get into that today, we split it into training data and test data. And they even do something where they split it into thirds, where a third is used for, where you switch between which one's training and test. There's all kinds of things that go into that. It gets very complicated when you get to the higher end. Not overly complicated, just an extra step which we're not going to do today because this is a very simple set of data. And let's go ahead and run this, and now we have our model fit. And I got an error here, so let me fix that real quick. It's capital SVC, it turns out. I did it lowercase. Support vector classifier. There we go. Let's go ahead and run that. And you'll see it comes up with all this information that it prints out automatically. These are the defaults of the model. You notice that we changed the kernel to linear, and there's our kernel linear on the printout. And there's other different settings you can mess with. We're going to just leave that alone for right now. For this, we don't really need to mess with any of those. So next, we're going to dig a little bit into our newly trained model. And we're going to do this so we can show you on a graph. And let's go ahead and get the separating. And we're going to say we're going to use a W for our variable on here. We're going to do model.coefficient _0. So what the heck is that? Again, we're digging into the model. So we've already got a prediction and a train. This is the math behind it that we're looking at right now. And so the W is going to represent 2 different coefficients. And if you remember, we had y equals mx plus c. So these coefficients are connected to that, but in 2-dimensional. It's a plane. We don't want to spend too much time on this because you can get lost in the confusion of the math. So if you're a math whiz, this is great. You can go through here and you'll see that we have a equals minus w of 0 over w of 1. Remember, there's two different values there. And that's basically the slope that we're generating. And then we're going to build an xx. What is xx? We're going to set it up to a numpy array. There's our np dot line space. So we're creating a line plus the intercept. Well, to make this work, we can do this as yy equals the slope times each value in that array. That's the neat thing about numpy. So when I do a times xx, which is a whole numpy array of values, it multiplies a across all of them. And then it takes those same values and we subtract the model intercept. That's your, remember we had mx plus c, so that'd be the c from the formula, y equals mx plus c. And that's where all these numbers come from. A little bit confusing because it's digging out of these different arrays. And then what we want to do is we're going to take this and we're going to go ahead and plot it. So plot the parallels to separating hyperplane that pass through the support vectors. And so we're going to create B equals a model support vectors. Pulling our support vectors out there. Here's our YY, which we now know is a set of data. And we have we're going to create YY down equals A times XX plus B1 minus A times B0. And then model support vector B is going to be set that to a new value, the -1 setup. And YY up equals A times XX plus B1 minus A times B0. And we can go ahead and just run this to load these variables up. If you wanted to understand a little bit more of what's going on, you can see if we print YY, we just run that, you can see it's an array. This is a line. It's going to have, in this case, between 30 and 60, so it's going to be 30 variables in here. And the same thing with YY up, YY down. And we'll plot those in just a minute on a graph so you can see what those look like. You just go ahead and delete that out of here and run that so it loads up the variables. Nice clean slate. I'm just going to copy this from before. Remember this, our SNS, our seaborn plot, LM plot, flour, sugar. And I'll just go ahead and run that real quick so you can see remember what that looks like. It's just a straight graph on there. And then one of the neat things is because seaborn sits on top of pie plot, we can do the pie plot for the line going through. And that is simply plt.plot. And that's our XX and YY, our two corresponding values, XY. And then somebody played with this to figure out that the line width equals 2 and the color black would look nice. So let's go ahead and run this whole thing with the pie plot on there. And you can see when we do this, it's just doing flour and sugar on here. Corresponding line between the sugar and the flour and the muffin versus cupcake. And then we generated the support vectors, the YY down and YY up. So let's take a look and see what that looks like. So we'll do our PL plot. And again, this is all against XX, our X value. But this time we have YY down. And let's do something a little fun with this. We can put in a K dash dash. That just tells it to make it a dotted line. And if we're going to do the down one, we also want to do the up one. So here's our YY up. And when we run that, it adds both sets of line. And so here's our support, and this is what you expect. You expect these two lines to go through the nearest data point. So the dashed lines go through the nearest muffin and the nearest cupcake when it's plotting it. And then your SVM goes right down the middle. So it gives it a nice split in our data. And you can see how easy it is to see, based just on sugar and flour, which one's a muffin or a cupcake. Let's go ahead and create a function to predict muffin or cupcake. I've got my recipes I pulled off the internet, and I want to see the difference between a muffin or a cupcake. And so we need a function to push that through. And we'll create a function with def. And let's call it muffin or cupcake. Now remember, we're just doing flour and sugar today. We're not doing all the ingredients. And that actually is a pretty good split. You really don't need all the ingredients to know it's flour and sugar. And let's go ahead and do an if-else statement. So if model predict is of flour and sugar equals 0. So we take our model and we run a predict. It's very common in sklearn where you have a dot predict. You put the data in and it's going to return a value. In this case, if it equals 0, then print you're looking at a muffin recipe. Else, if it's not 0, that means it's 1, then you're looking at a cupcake recipe. That's pretty straightforward for a function, or def for definition. DEF is how you do that in Python. And of course, if you're going to create a function, you should run something in it. And so let's run a cupcake, and we're going to send it values 50 and 20, a muffin or a cupcake. I don't know what it is. And let's run this and just see what it gives us. And it says, oh, it's a muffin. You're looking at a muffin recipe. So it very easily predicts whether we're looking at a muffin or a cupcake recipe. Let's plot this. There we go. Plot this on the graph so we can see what that actually looks like. And I'm just going to copy it and paste it from below where we're plotting all the points in there. So this is nothing different than what we did before. If I run it, you'll see it has all the points and the lines on there. And what we want to do is we want to add another point. And we'll do plt plot. And if you remember correctly, we did, for our test, we did 50 and 20. And then somebody went in here and decided we'll do YO for yellow, or it's kind of an orangish yellow color is going to come out. Marker size 9. Those are settings you can play with. Somebody else played with them to come up with the right setup so it looks good. And you can see there it is graphed, clearly a muffin. In this case, in cupcakes versus muffins, the muffin has won. And if you'd like to do your own muffin cupcake contender series, you certainly can send a note down below, and the team at Simplilearn will send you over the data they use for the muffin and cupcake. And that's true of any of the data. We didn't actually run a plot on it earlier. We had men versus women. You can also request that information to run it on your data setup so you can test that out. So to go back over our setup, we went ahead for our support vector machine code. We did a predict 40 parts flour, 20 parts sugar. I think it was different than the one we did, whether it's a muffin or a cupcake. Hence, we have built a classifier using SVM, which is able to classify if a recipe is of a cupcake or a muffin, which wraps up our cupcake versus muffin. Today, in our second tutorial, we're going to cover k-means and linear regression, along with going over the quiz questions we had during our first tutorial. What's in it for you? We're going to cover clustering. What is clustering? K-means clustering, which is one of the most common used clustering tools out there, including a flowchart to understand k-means clustering and how it functions. And then we'll do an actual Python live demo on clustering of cars based on brands. Then we're going to cover logistic regression. What is logistic regression? Logistic regression curve and sigmoid function. And then we'll do another Python code demo to classify a tumor as malignant or benign based on features. And let's start with clustering. Suppose we have a pile of books of different genres. Now we divide them into different groups like fiction, horror, education, and as we can see from this young lady, she definitely is into heavy horror. You can just tell by those eyes and the maple Canadian leaf on her shirt. But we have fiction, horror, and education, and we want to go ahead and divide our books up. Well, organizing objects into groups based on similarity is clustering. And in this case, as we're looking at the books, we're talking about clustering things with known categories. But you can also use it to explore data. So you might not know the categories, you just know that you need to divide it up in some way to conquer the data and to organize it better. But in this case, we're going to be looking at clustering in specific categories. And let's just take a deeper look at that. We're going to use k-means clustering. K-means clustering is probably the most commonly used clustering tool in the machine learning library. K-means clustering is an example of unsupervised learning. If you remember from our previous thing, it is used when you have unlabeled data. So we don't know the answer yet. We have a bunch of data that we want to cluster into different groups. Define clusters in the data based on feature similarity. So we've introduced a couple terms here. We've already talked about unsupervised learning and unlabeled data. So we don't know the answer yet. We're just going to group stuff together and see if we can find an answer of how things connect. We've also introduced feature similarity, features being different features of the data. Now with books, we can easily see fiction and horror and history books, but a lot of times with data, some of that information isn't so easy to see right when we first look at it. And so k-means is one of those tools where we can start finding things that connect, that match with each other. Suppose we have these data points and want to assign them into a cluster. Now when I look at these data points, I would probably group them into two clusters just by looking at them. I'd say two of these group of data kind of come together. But in k-means, we pick k-clusters and assign random centroids to clusters, where the k-clusters represents two different clusters. We pick k-clusters and assign random centroids to the clusters, then we compute distance from objects to the centroids. Now we form new clusters based on minimum distances and calculate the centroids. So we figure out what the best distance is for the centroid, then we move the centroid and recalculate those distances. Repeat previous two steps iteratively till the cluster centroids stop changing their positions and become static. Repeat previous two steps iteratively till the cluster centroids stop changing and the positions become static. Once the clusters become static, then k-means clustering algorithm is said to be converged. And there's another term we see throughout machine learning is converged. That means whatever math we're using to figure out the answer has come to a solution, or it's converged on an answer. Shall we see the flow chart to understand? Make a little bit more sense by putting it into a nice easy step-by-step. So we start, we choose k, we'll look at the elbow method in just a moment. We assign random centroids to clusters, and sometimes you pick the centroids, because you might look at the data in a graph and say, oh, these are probably the central points. Then we compute the distance from the objects to the centroids. We take that and we form new clusters based on minimum distance and calculate their centroids. Then we compute the distance from objects to the new centroids. And then we go back and repeat those last two steps. We calculate the distances. So as we're doing it, it brings into the new centroid, and then we move the centroid around and we figure out which objects are closest to each centroid. So the objects can switch from one centroid to the other as the centroids are moved around. And we continue that until it is converged. Let's see an example of this. Suppose we have this data set of 7 individuals and their score on two topics, A and B. So here's our subject. In this case, referring to the person taking the test. And then we have subject A, where we see what they've scored on their first subject, and we have subject B, and we can see what they score on the second subject. Now let's take two farthest apart points as initial cluster centroids. Now remember, we talked about selecting them randomly, or we can also just put them in different points and pick the furthest one apart so they move together. Either one works okay, depending on what kind of data you're working on and what you know about it. So we took the two furthest points, 1 and 1, and 5 and 7. And now let's take the two farthest apart points as initial cluster centroids. Each point is then assigned to the closest cluster with respect to the distance from the centroids. So we take each one of these points in there, we measure that distance, and you can see that if we measured each of those distances, and you use the Pythagorean theorem for a triangle in this case, because you know the x and the y, and you can figure out the diagonal line from that. Or you can just take a ruler and put it on your monitor. That'd be kind of silly, but it would work if you're just eyeballing it. You can see how they naturally come together in certain areas. Now we again calculate the centroids of each cluster. So cluster 1 and then cluster 2, and we look at each individual dot. There's 1, 2, 3, we're in one cluster. The centroid then moves over. It becomes 1.8, 2.3. So remember, it was at 1 and 1? Well, the very center of the data we're looking at would put it at the roughly 2, 2, but 1.8 and 2.3. And the second one, if we wanted to make the overall mean vector, the average vector of all the different distances to that centroid, we come up with 4, 1 and 5, 4. So we've now moved the centroids. We compare each individual's distance to its own cluster, mean, and to that of the opposite cluster, and we find, we can build a nice chart on here, that as we move that centroid around, we now have a new different kind of clustering of groups, and using Euclidean distance between the points and the mean, we get the same formula. You see new formulas coming up. So we have our individual dots, distance to the mean, centroid of the cluster, and distance to the mean, centroid of the cluster. Only individual 3 is nearer to the mean of the opposite cluster, cluster 2, than its own cluster 1. And you can see here in the diagram where we've kind of circled that 1 in the middle. So when we've moved the centroids of the clusters over, one of the points shifted to the other cluster because it's closer to that group of individuals. Thus, individual 3 is relocated to cluster 2, resulting in a new partition. And we regenerate all those numbers of how close they are to the different clusters. For the new clusters, we will find the actual cluster centroids. So now we move the centroids over, and you can see that we've now formed two very distinct clusters on here. On comparing the distance of each individual's distance to its own cluster mean and to that of the opposite cluster, we find that the data points are stable, hence we have our final clusters. Now, if you remember, I brought up a concept earlier, k-mean on the k-means algorithm. Choosing the right value of k will help in less number of iterations. And to find the appropriate number of clusters in a data set, we use the elbow method. And within sum of squares, WSS, is defined as the sum of the squared distance between each member of the cluster and its centroid. And so you see what we've done here is we have the number of clusters. And as you do the same k-means algorithm over the different clusters, and you calculate what that centroid looks like, and you find the optimal, you can actually find the optimal number of clusters using the elbow. The graph is called as the elbow method. And on this, we guessed at 2 just by looking at the data. But as you can see, the slope, you actually just look for right there where the elbow is in the slope, and you have a clear answer that we want 2 different, to start with k-means equals 2. A lot of times people end up computing k-means equals 2, 3, 4, 5 until they find the value which fits on the elbow joint. Sometimes you can just look at the data, and if you're really good with that specific domain, remember domain, I mentioned that last time, you'll know that where to pick those numbers or where to start guessing at what that k value is. So let's take this, and we're going to use a use case using k-means clustering to cluster cars into brands using parameters such as horsepower, cubic inches, make, year, etc. So we're going to use the dataset cars data, having information about 3 brands of cars: Toyota, Honda, and Nissan. We'll go back to my favorite tool, the Anaconda Navigator with the Jupyter Notebook. And let's go ahead and flip over to our Jupyter Notebook. And in our Jupyter Notebook, I'm going to go ahead and just paste the basic code that we usually start a lot of these off with. We're not going to go too much into this code because we've already discussed NumPy, we've already discussed Matplotlib, and pandas. NumPy being the number array, pandas being the pandas data frame, and Matplot for the graphing. And don't forget, since if you're using the Jupyter Notebook, you do need the Matplotlib inline so that it plots everything on the screen. If you're using a different Python editor, then you probably don't need that because it'll have a pop-up window on your computer. And we'll go ahead and run this just to load our libraries and our setup into here. The next step is, of course, to look at our data, which I've already opened up in a spreadsheet. And you can see here we have the miles per gallon, cylinders, cubic inches, horsepower, weight pounds, how heavy it is, time it takes to get to 60. My card is probably on this one at about 80 or 90. What year it is. So this is, you can actually see this is kind of older cars, and then the brand, Toyota, Honda, Nissan. So the different cars are coming from all the way from 1971, if we scroll down, to the 80s. We have between the 70s and 80s a number of cars that they've put out. And let's, when we come back here, we're going to do importing the data. So we'll go ahead and do dataset equals, and we'll use pandas to read this in, and it's from a CSV file. Remember, you can always post this in the comments and request the data files for these, either in the comments here on the YouTube video or go to Simplilearn.com and request that. The cars CSV, I put it in the same folder as the code that I've stored. So my Python code is stored in the same folder, so I don't have to put the full path. If you store them in different folders, you do have to change this and double check your name variables. And we'll go ahead and run this, and we've chosen dataset arbitrarily because it's a dataset we're importing, and we've now imported our cars CSV into the dataset. As you know, you have to prep the data, so we're going to create the X data. This is the one that we're going to try to figure out what's going on with. And then there's a number of ways to do this, but we'll do it in a simple loop so you can actually see what's going on. So we'll do for I in x.columns. So we're going to go through each of the columns, and a lot of times it's important. I'll make lists of the columns and do this because I might remove certain columns, or there might be columns that I want to be processed differently. But for this, we can go ahead and take x of I, and we want to go fill NA, and that's a pandas command. But the question is, what are we going to fill the missing data with? We definitely don't want to just put in a number that doesn't actually mean something. And so one of the tricks you can do with this is we can take x of I And then in addition to that, we want to go ahead and turn this into an integer, because a lot of these are integers. So we'll go ahead and keep it integers. And we add the bracket here. And a lot of editors will do this. They'll think that you're closing one bracket. Make sure you get that second bracket in there if it's a double bracket. That's always something that happens regularly. So once we have our integer of x of y, this is going to fill in any missing data with the average. And I was so busy closing one set of brackets, I forgot that the mean also has brackets in there for the pandas. So we can see here we're going to fill in all the data with the average value for that column. So if there's missing data, it's in the average of the data it does have. And then once we've done that, we'll go ahead and loop through it again and just check and see to make sure everything is filled in correctly. And we'll print, and then we take x is null, and this returns a set of the null value, or the how many lines are null, and we'll just sum that up to see what that looks like. And so when I run this, and so with the x, what we want to do is we want to remove the last column because that had the models. That's what we're trying to see, if we can cluster these things and figure out the models. There is so many different ways to sort the x out. For one, we could take the x and we could go data set, our variable we're using, and use the iLocation, one of the features that's in pandas. And we could take that and then take all the rows and all but the last column of the data set. And at this time we could do values. We just convert it to values. So that's one way to do this. And if let me just put this down here and print x, it's a capital X we chose, and I run this, you can see it's just the values. We could also take out the values and it's not going to return anything because there's no values connected to it. What I like to do with this is, instead of doing the iLocation, which does integers, more common is to come in here and we have our data set, and we're going to do dataset dot columns. And remember, that lists all the columns. So if I come in here, let me just mark that as red, and I print dataset dot columns. You can see that I have my index here. I have my MPG, cylinders, everything, including the brand, which we don't want. So the way to get rid of the brand would be to do data columns of everything but the last one, -1. So now if I print this, you'll see the brand disappears. And so I can actually just take dataset columns -1, and I'll put it right in here for the columns we're going to look at. And let's unmark this. And unmark this. And now if I do an x.head, I now have a new data frame, and you can see right here we have all the different columns except for the brand at the end of the year. And it turns out when you start playing with the data set, you're going to get an error later on, and it'll say cannot convert string to float value. And that's because for some reason these things, the way they recorded them, must have been recorded as strings. So we have a neat feature in here on pandas to convert. And it is simply convert objects. And for this we're going to do convert underscore numeric equals true. And yes, I did have to go look that up. I don't have it memorized, the convert numeric in there. If I'm working with a lot of these things, I remember them, but depending on where I'm at, what I'm doing, I usually have to look it up. And we run that. Oops, I must have missed something in here. Let me double check my spelling. And when I double check my spelling, you'll see I missed the first underscore in the convert objects. And when I run this, it now has everything converted into a numeric value, because that's what we're going to be working with, is numeric values down here. And the next part is that we need to go through the data and eliminate null values. Most people, when they're doing small amounts, working with small data pools, discover afterwards that they have a null value and they have to go back and do this. So, be aware, whenever we're formatting this data, things are going to pop up, and sometimes you go backwards to fix it. And that's fine. That's just part of exploring the data and understanding what you have. And I should have done this earlier, but let me go ahead and increase the size of my window one notch. There we go. Easier to see. So we'll do for I in working with x dot columns. We'll page through all the columns. And we want to take x of I, and we're going to change that, and we're going to alter it. And so with this, we want to go ahead and fill in x of I. Pandas has the fill in A. and that just fills in any non-existent missing data. And we'll put my brackets up, and there's a lot of different ways to fill this data. If you have a really large data set, some people just void out that data and then look at it later in a separate exploration of data. One of the tricks we can do is we can take our column and we can find the means. And the means is in our quotation marks. So we take the columns, we're going to fill in the non-existing one with the means. The problem is that returns a decimal float. So some of these aren't decimals. Certainly, we need to be a little careful of doing this, but for this example, we're just going to fill it in with the integer version of this. It keeps it on par with the other data that isn't a decimal point. And then what we also want to do is we want to double check. Ways you can do that is simply go in here and take our x of I column. So it's going to go through the x of I column. It says is null. So it's going to return any place there's a null value. It actually goes through all the rows of each column is null, and then we want to go ahead and sum that. So we take that and we add the sum value, and these are all pandas. So is null is a panda command, and so is sum. And if we go through that and we go ahead and run it, and we go ahead and take and run that, you'll see that all the columns have 0 null values. So we've now tested and double checked, and our data is nice and clean. We have no null values. Everything is now a number value. We turned it into numeric. And we've removed the last column in our data. And at this point, we're actually going to start using the elbow method to find the optimal number of clusters. So we're now actually getting into the sklearn part, the k-means clustering on here. I guess we'll go ahead and zoom it up one more notch so you can see what I'm typing in here. And then from sklearn, we're going to our sklearn cluster, we're going to import k-means. I always forget to capitalize the k and the m when I do this. So it's capital K, capital M, k-means. And we'll go ahead and create a array, WCSS equals, we'll make it an empty array. If you remember from the elbow method from our slide, within the sum of squares, WSS is defined as the sum of square distance between each member of the cluster and its centroid. So we're looking at that change in differences as far as a square distance. And we're going to run this over a number of k-mean values. In fact, let's go for I in range, we'll do 11 of them. Range 0 of 11. And the first thing we're going to do is we're going to create the actual, we'll do it all lowercase. And so we're going to create this object from the k-means that we just imported. And the variable that we want to put into this is in clusters. And we're going to set that equals to I. That's the most important one because we're looking at how increasing the number of clusters changes our answer. There are a lot of settings to the k-means. Our guys in the back did a great job just kind of playing with some of them. The most common ones that you see in a lot of stuff is how you init your k-means. So we have k-means plus plus. This is just a tool to let the model itself be smart how it picks its centroids to start with, its initial centroids. We only want to iterate no more than 300 times. We have a max iteration we put in there. We have the nth init, the random state equals 0. You really don't need to worry too much about these when you're first learning this. As you start digging in deeper, you start finding that these are shortcuts that will speed up the process as far as the setup. But the big one that we're working with is the in clusters equals I. So we're going to literally train our k-means 11 times. We're going to do this process 11 times. And if you're working with big data, you know the first thing you do is you run a small sample of the data so you can test all your stuff on it. And you can already see the problem that if I'm going to iterate through a terabyte of data 11 times, and then the k-means itself is iterating through the data multiple times, that's a heck of a process. So you got to be a little careful with this. A lot of times, though, you can find your elbow, using the elbow method, find your optimal number on a sample of data, especially if you're working with larger data sources. So we want to go ahead and take our k-means and we're just going to fit it. If you're looking at any of the sklearn very common. You fit your model. And if you remember correctly, our variable we're using is the capital X. And once we fit this value, we go back to the array we made, and we want to go ahead and just append that value on the end. And it's not the actual fit we're appending in there, it's when it generates the value you're looking for is inertia. So k-means.inertia will pull that specific value out that we need. And let's get a visual on this. We'll do our PLT plot, and what we're plotting here is first the x-axis, which is range 0, 11, so that will generate a nice little plot there, and the WCSS for our y-axis. It's always nice to give our plot a title, and let's see, we'll just give it the elbow method for the title, and let's get some labels. So let's go ahead and do PLT X label, and what we'll do number of clusters for that, and PLT Y label, and for that we can do, oops, there we go, WCSS, since that's what we're doing on the plot on there. And finally we want to go ahead and display our graph, which is simply PLT dot show. There we go. And because we have it set to inline, it'll appear inline. Hopefully I didn't make a type error on there. And you can see we get a very nice graph. You can see a very nice elbow joint there at 2, and again right around 3 and 4, and then after that there's not very much. Now, as a data scientist, if I was looking at this, I would do either 3 or 4, and I'd actually try both of them to see what the output looked like. And they've already tried this in the back, so we're just going to use 3 as a setup on here. And let's go ahead and see what that looks like when we actually use this to show the different kinds of cars. And so let's go ahead and apply the k-means to the cars data set. And basically we're going to copy the code that we looped through up above, where k-means equals k-means number of clusters, and we're just going to set the number of clusters to 3, since that's what we're going to look for. And you could do 3 and 4 on this and graph them just to see how they come up differently. It'd be kind of curious to look at that. But for this, we're just going to set it to 3. Go ahead and create our own variable, y k-means, for our answers. And we're going to set that equal to, whoops, a double equal there, to k-means. But we're not going to do a fit. We're going to do a fit predict is the setup you want to use. And when you're using untrained models, you'll see a slightly different, because usually you see fit and then you see just the predict. But we want to both fit and predict the k-means on this. And that's fit underscore predict, and then our capital X is the data we're working with. And before we plot this data, we're going to do a little pandas trick. We're going to take our X value and we're going to set X as matrix. So we're converting this into a nice rows and columns kind of setup, but we're going to have columns equals none, so it's just going to be a matrix of data in here. And let's go ahead and run that. A little warning. You'll see these warnings pop up because things are always being updated. So there's like minor changes in the versions and future versions. Instead of matrix, now it's more common to set it dot values instead of doing as matrix. But as matrix works just fine for right now, and you'll want to update that later on. But let's go ahead and dive in and plot this and see what that looks like. And before we dive into plotting this data, I always like to take a look and see what I am plotting. So let's take a look at y k-means, and I'm just going to print that out down here. And we see we have an array of answers. We have 2, 1, 0, 2, 1, 2. So it's clustering these different rows of data based on the 3 different spaces it thinks it's going to be. And then let's go ahead and print x and see what we have for x. And we'll see that x is an array, it's a matrix, so we have our different values in the array. And what we're going to do, it's very hard to plot all the different values in the array. So we're only going to be looking at the first 2, or positions 0 and 1. And if you were doing a full presentation in front of the board meeting, you might actually do a little different and dig a little deeper into the different aspects, because this is all the different columns we looked at. But we'll only look at columns 1 and 2 for this to make it easy. So let's go ahead and clear this data out of here, and let's bring up our plot. And we're going to do a scatter plot here. So PLT scatter, and this looks a little complicated, so let's explain what's going on with this. we're going to take the x values, and we're only interested in y of k-means equals 0, the first cluster. Okay? And then we're going to take value 0 for the x-axis, and then we're going to do the same thing here. We're only interested in k-means equals 0, but we're going to take the second column. So we're only looking at the first two columns in our answer, or in the data. And then the guys in the back played with this a little bit to make it pretty. And they discovered that it looks good if it has a size equals 100. That's the size of the dots. We're going to use red for this one. And when they were looking at the data and what came out, it was definitely the Toyota on this. We're just going to go ahead and label it Toyota. Again, that's something you really have to explore in here as far as playing with those numbers and see what looks good. We'll go ahead and hit enter in there. And I'm just going to paste in the next two lines, which is the next two cars. And this is our Nissan and Honda. And you'll see with our scatter plot, we're now looking at where y underscore k means equals 1. And we want the 0 column, and y k means equals 2. Again, we're looking at just the first two columns, 0 and 1. And each of these rows then corresponds to Nissan and Honda. And I'll go ahead and hit enter on there. And finally, let's take a look and put the centroids on there. Again, we're going to do a scatter plot. And on the centroids, you can just pull that from our k-means, the model we created, dot cluster centers, and we're going to just do all of them in the first number and all of them in the second number, which is 0, 1, because you always start with 0 and 1. And then they were playing with the size and everything to make it look good. We'll do a size of 300. We're going to make the color yellow, and we'll label them. It's always good to have some good labels, centroids. And then we do want to do a title, PLT title, and pop up there. PLT title, because you always want to make your graphs look pretty, and we'll call it clusters of car make. And one of the features of the plot library is you can add a legend. It'll automatically bring in it since we've already labeled the different aspects of the legend with Toyota, Nissan, and Honda. And finally, we want to go ahead and show, so we can actually see it. And remember, it's inline, so if you're using a different editor that's not the Jupyter Notebook, you'll get a pop-up of this. And you should have a nice set of clusters here. So we can look at this, and we have clusters of Honda in green, Toyota in red, Nissan in purple. And you can see where they put the centroids to separate them. Now, when we're looking at this, we can also plot a lot of other different data on here, because we only looked at the first two columns. This is just column 1 and 2. Or 0, 1 as you label them in computer scripting. But you can see here we have nice clusters of car make, and we were able to pull out the data, and you can see how just these two columns form very distinct clusters of data. So if you were exploring new data, you might take a look and say, well, what makes these different? Almost going in reverse, you start looking at the data and pulling apart the columns to find out why is the first group set up the way it is. Maybe you're doing loans, and you want to go, well, why is this group not defaulting on their loans? And why is the last group defaulting on their loans? And why is the middle group 50% defaulting on their bank loans? And you start finding ways to manipulate the data and pull out the answers you want. So now that you've seen how to use k-mean for clustering, let's move on to the next topic. Now let's look into logistic regression. The logistic regression algorithm is the simplest classification algorithm used for binary or multi-classification problems. And we can see we have our little girl from Canada who's into horror books is back. That's actually really scary when you think about that with those big eyes. In the previous tutorial, we learned about linear regression, dependent and independent variables. So, to brush up, y equals mx plus c. A very basic algebraic function of y and x. The dependent variable is the target class variable we are going to predict. The independent variables, x1 all the way up to xn, are the features or attributes we're going to use to predict the target class. We know what a linear regression looks like, but using the graph we cannot divide the outcome into categories. It's really hard to categorize 1.5, 3.6, 9.8. For example, a linear regression graph can tell us that with increase in number of hours studied, the marks of a student will increase, but it will not tell us whether the student will pass or not. In such cases where we need the output as categorical value, we will use logistic regression. And for that, we're going to use the sigmoid function. So you can see here we have our marks, 0 to 100, number of hours studied. That's going to be what they're comparing it to in this example. And we usually form a line that says y equals mx plus c. And when we use the sigmoid function, we have p equals 1 over 1 plus e to the minus y. It generates a sigmoid curve. And so you can see right here, when you take the ln, which is the natural logarithm, I always thought it should be nl, not ln. That's just the inverse of e, or e to the minus y. And so when we do this, we get ln of p over 1 minus p equals m times x plus c. That's the sigmoid curve function we're looking for. And we can zoom in on the function, and you'll see that the function, as it derives, goes to 1 or to 0, depending on what your x value is. And the probability, if it's greater than 0.5, the value is automatically rounded off to 1, indicating that the student will pass. So if they're doing a certain amount of studying, they will probably pass. Then you have a threshold value at the 0.5. It automatically puts that right in the middle usually. And your probability, if it's less than 0.5, the value rounded off to 0, indicating the student will fail. So if they're not studying very hard, they're probably going to fail. This, of course, is ignoring the outliers of that one student who's just a natural genius and doesn't need any studying to memorize everything. That's not me, unfortunately. I have to study hard to learn new stuff. Problem statement. To classify whether a tumor is malignant or benign. And this is actually one of my favorite data sets to play with because it has so many features, and when you look at them, you really are hard to understand. You can't just look at them and know the answer. So it gives you a chance to kind of dive into what data looks like when you aren't able to understand the specific domain of the data. But I also want you to remind you that in the domain of medicine, if I told you that my probability was really good, it classified things at say 90% or 95%, and I'm classifying whether you're going to have a malignant or a benign tumor, I'm guessing that you're going to go get it tested anyways. So you got to remember the domain we're working with. So why would you want to do that if you know you're just going to go get a biopsy because, you know, it's that serious? This is like an all or nothing. Just referencing the domain, it's important. It might help the doctor know where to look just by understanding what kind of tumor it is. So it might help them or aid them in something they missed from before. So let's go ahead and dive into the code, and I'll come back to the domain part of it in just a minute. So use case, and we're going to do our normal imports here, where we're importing NumPy, Pandas, Seaborn, the Matplot library, and we're going to do Matplot library inline since I'm going to switch over to Anaconda. So let's go ahead and flip over there and get this started. So I've opened up a new window in my Anaconda Jupyter Notebook. And by the way, Jupyter Notebook, you don't have to use Anaconda for the Jupyter Notebook. I just love the interface and all the tools that Anaconda brings. So we got our import NumPy as in P for our NumPy number array. We have our Pandas PD. We're going to bring in Seaborn to help us with our graphs as SNS. So many really nice tools in both Seaborn and Matplot library. Then we'll do our Matplot library.pyplot as PLT, and then of course we want to let it know to do it in line. And let's go ahead and just run that so it's all set up. And we're just going to call our data, not creative today, equals PD, and this happens to be in a CSV file. So we'll use the pd.read_CSV, and I happen to name the file, I renamed it, data for p2.csv. You can, of course, write in the comments below the YouTube and request for the data set itself, or go to the Simplilearn website, and we'll be happy to supply that for you. And let's just open up the data before we go any further, and let's just see what it looks like in a spreadsheet. So when I pop it open in a local spreadsheet, and this is just a CSV file, comma separated variables, we have an ID, so I guess they categorize this for reference or what ID, which test was done. The diagnosis, M for malignant, B for benign, so there's two different options on there. And that's what we're going to try to predict is the M and B and test it. And then we have like the radius mean or average, the texture average, perimeter mean, area mean, smoothness. I don't know about you, but unless you're a doctor in the field, most of the stuff, I mean, you can guess what concave means just by the term concave, but I really wouldn't know what that means in the measurements they're taking. So they have all kinds of stuff like how smooth it is, the symmetry, and these are all float values. We can just page through them real quick, and you'll see there's, I believe, 36, if I remember correctly, in this one. So there's a lot of different values they take and all these measurements they take when they go in there and they take a look at the different growth, the tumorous growth. So back in our data, and I put this in the same folder as the code. So I saved this code in that folder. Obviously, if you have it in a different location, you want to put the full path in there. And we'll just do pandas first 5 lines of data with the data.head. When we run that, we can see that we have pretty much what we just looked at. We have an ID, we have a diagnosis. If we go all the way across, you'll see all the different columns coming across displayed nicely for our data. And while we're exploring the data, our Seaborn, which we referenced as SNS, makes it very easy to go in here and do a joint plot. You'll notice very similar to, because it is sitting on top of the plot library. So the joint plot does a lot of work for us. And we're just going to look at the first 2 columns that we're interested in, the radius mean and the texture mean. We'll just look at those 2 columns. And data equals data. So that tells it which 2 columns we're plotting and that we're going to use the data that we pulled in. And let's just run that. And it generates a really nice graph on here. And there's all kinds of cool things on this graph to look at. I mean, we have the texture mean and the radius mean, obviously the axes. You can also see, and one of the cool things on here is you can also see the histogram. They show that for the radius mean. Where is the most common radius mean come up and where the most common texture is. So we're looking at on each growth its average texture and on each radius its average radius on there. It gets a little confusing because we're talking about the individual objects average, and then we can also look over here and see the histogram showing us the median or how common each measurement is. And that's only 2 columns, so let's dig a little deeper into Seaborn. They also have a heat map. And if you're not familiar with heat maps, a heat map just means it's in color. That's all that means. Heat map. I guess the original ones were plotting heat density on something, and so ever since then it's just called a heat map. And we're going to take our data and get our corresponding numbers to put that into the heat map. And that's simply data.corr for that. That's a pandas expression. So remember, we're working in a pandas data frame, so that's one of the cool tools in pandas for our data. And let's just pull that information into a heat map and see what that looks like. And you'll see that we're now looking at all the different features. We have our ID, we have our texture, we have our area, our compactness, concave points. And if you look down the middle of this chart, diagonal, going from the upper left to bottom right, it's all white. That's because when you compare texture to texture, they're identical. So they're 100%, or in this case, a perfect 1 in their correspondence. And you'll see that when you look at, say, area, or right below it, it has almost a black on there when you compare it to texture. So these have almost no corresponding data. They don't really form a linear graph or something that you can look at and say how connected they are. They're very scattered data. This is really just a really nice graph to get a quick look at your data. It doesn't so much change what you do, but it changes verifying. So when you get an answer or something like that, or you start looking at some of these individual pieces, you might go, hey, that doesn't match. According to showing our heat map, this should not correlate with each other. And if it is, you're going to have to start asking, well, why? What's going on? What else is coming in there? But it does show some really cool information on here. I mean, we can see from the ID, there's no real one feature that just says, if you go across the top line, that lights up. There's no one feature that says, hey, if the area is a certain size, then it's going to be benign or malignant. It says there's some that sort of add up. And that's a big hint in the data that we're trying to ID this, whether it's malignant or benign. That's a big hint to us as data scientists to go, okay, we can't solve this with any one feature. It's going to be something that includes all the features, or many of the different features, to come up with a solution for it. And while we're exploring the data, let's explore one more area, and let's look at data.isNull. We want to check for null values in our data. And if you remember from earlier in this tutorial, we did it a little differently where we added stuff up and summed them up. You can actually, with pandas, do it really quickly, data.isNull, and sum it, and it's going to go across all the columns. So when I run this, you're going to see all the columns come up with no null data. So we've just to rehash these last few steps, we've done a lot of exploration. We have looked at the first two columns and seen how they plot with the seaborn, with a joint plot which shows both the histogram and the data plotted on the XY coordinates. And obviously you can do that more in detail with different columns and see how they plot together. And then we took and did the seaborn heat map, the SNS heat map of the data. And you can see right here where it did a nice job showing us some bright spots where stuff correlates with each other and forms a very nice combination or points of scattering points. And you can also see areas that don't. And then finally we went ahead and checked the data. Is the data null value? Do we have any missing data in there? Very important step because it'll crash later on. If you forget to do this step, it will remind you when you get that nice error code that says null values. Okay, so not a big deal if you miss it, but it's no fun having to go back when you're in a huge process and you've missed this step and now you're 10 steps later and you got to go remember where you were pulling the data in. So we need to go ahead and pull out our x and our y. So we just put that down here and we'll set the x equal to, and there's a lot of different options here. Certainly we could do x equals all the columns except for the first two, because if you remember the first two is the ID and the diagnosis. So that certainly would be an option. But what we're going to do is we're actually going to focus on the worst radius, the worst texture, parameter, area, smoothness, compactness, and so on. One of the reasons to start dividing your data up when you're looking at this information is sometimes the data will be the same data coming in. So if I have two measurements coming into my model, it might overweigh them. It might overpower the other measurements because it's basically taking that information in twice. That's a little bit past the scope of this tutorial. What I want you to take away from this though is that we are dividing the data up into pieces, and our team in the back went ahead and said, hey, let's just look at the worst. So I'm going to create an array, and you'll see this array, radius worst, texture worst, perimeter worst. We've just taken the worst of the worst, and I'm just going to put that in my X. So this X is still a pandas data frame, but it's just those columns. And our Y, if you remember correctly, is going to be, oops, hold on one second. It's not X, it's data. There we go. So X equals data, and then it's a list of the different columns, the worst of the worst. And if we're going to take that, then we have to have our answer for our Y, for the stuff we know. And if you remember correctly, we're just going to be looking at the diagnosis. That's all we care about is what is it diagnosed? Is it benign or malignant? And since it's a single column, we can just do diagnosis. Oh, I forgot to put the brackets. There we go. Okay. So it's just diagnosis on there. And we can also real quickly do like x dot head if you want to see what that looks like. And y dot head. And run this. And you'll see it only does the last one. I forgot about that if you don't do print. You can see that the y dot head is just MMM because the first ones are all malignant. And if I run this, the x dot head is just the first 5 values of radius worst, texture worst, parameter worst, area worst, and so on. I'll go ahead and take that out. So moving down to the next step, we've built our two data sets, our answer and then the features we want to look at. In data science, it's very important to test your model. So we do that by splitting the data. And from sklearn model selection, we're going to import train test split. So we're going to split it into two groups. There are so many ways to do this. I noticed in one of the more modern ways, they actually split it into 3 groups, and then you model each group and test it against the other groups. So you have all kinds of, and there's reasons for that, which is past the scope of this, and for this particular example isn't necessary. For this, we're just going to split it into 2 groups, one to train our data and one to test our data. And the sklearn model selection, we have train test split. You could write your own quick code to do this where you just randomly divide the data up into 2 groups, but they do it for us nicely. And we can actually do it in one statement with this, where we're going to generate 4 variables, capital X train, capital X test. So we have our training data we're going to use to fit the model, and then we need something to test it. And then we have our Y train, so we're going to train the answer, and then we have our test. So this is the stuff we want to see how good it did on our model. And we'll go ahead and take our train test split that we just imported, And we're going to do X and our Y, our two different data that's going in for our split. And then the guys in the back came up and wanted us to go ahead and use a test size equals 0.3. That's test underscore size. Random state, it's always nice to kind of switch your random state around, but not that important. What this means is that the test size is we're going to take 30% of the data and we're going to put that into our test variables, our Y test and our X test. And we're going to do 70% into the X train and the Y train. So we're going to use 70% of the data to train our model and 30% to test it. Let's go ahead and run that and load those up. So now we have all our stuff split up and all our data ready to go. And now we get to the actual logistics part. We're actually going to create our model. So let's go ahead and bring that in from sklearn. We're going to bring in our linear model and we're going to import logistic regression. That's the actual model we're using. And this, we'll call it log model. Oops, there we go, model. And let's just set this equal to our logistic regression that we just imported. So now we have a variable log model set to that class for us to use. And with most of the models in the sklearn, we just need to go ahead and do a fit on there. And we use our X train that we separated out with our Y train. Now let's go ahead and run this. So once we've run this, we'll have a model that fits this data, that 70% of our training data. And of course it prints this out that tells us all the different variables that you can set on there. There's a lot of different choices you can make. But for what we're doing, we're just going to let all the defaults sit. We don't really need to mess with those on this particular example. And there's nothing in here that really stands out as super important until you start fine-tuning it. But for what we're doing, the basics will work just fine. And then we need to go ahead and test out our model. Is it working? So let's create a variable yPredict. And this is going to be equal to our log model. And we want to do a predict. Again, very standard format for the sklearn library is taking your model and doing a predict on it. And we're going to test yPredict against the Y test. So we want to know what the model thinks it's going to be. That's what our yPredict is. And with that, we want the capital X test. So we have our train set and our test set, and now we're going to do our yPredict. And let's go ahead and run that. And if we print yPredict, let me go ahead and run that, you'll see it comes up and it prints a nice array of B and M for benign and malignant for all the different test data we put in there. So it does pretty good. We're not sure exactly how good it does, but we can see that it actually works and is functional. It was very easy to create. You'll always discover with our data science that as you explore this, you spend a significant amount of time prepping your data and making sure your data coming in is good. There's a saying, good data in, good answers out. Bad data in, bad answers out. That's only half the thing. That's only half of it. Selecting your models becomes the next part as far as how good your models are. And then, of course, fine-tuning it depending on what model you're using. So we come in here, we want to know how good this came out. So we have our yPredict here, logModel.predictXtest. So for deciding how good our model is, we're going to go from the sklearn.metrics, we're going to import classification report. And that just reports how good our model is doing. And then we're going to feed it the model data. And let's just print this out. And we'll take our classification report. And we're going to put into there our test, our actual data. So this is what we actually know is true. And our prediction, what our model predicted for that data on the test side. And let's run that and see what that does. So we pull that up, you'll see that we have a precision for benign and malignant, B and M. And we have a precision of 93 and 91, a total of 92. So it's kind of the average between these two of 92. There's all kinds of different information on here. Your F1 score, your recall, your support coming through on this. And for this, I'll go ahead and just flip back to our slides that they put together for describing it. And so here we're going to look at the precision using the classification report. And you see this is the same printout I had up above. Some of the numbers might be different because it does randomly pick out which data we're using. So this model is able to predict the type of tumor with 91% accuracy. So when we look back here, you'll see where we have benign and malignant. It actually is 92 coming up here. But we're looking at about a 91% precision. And remember, I reminded you about domains. So when we're talking about the domain of a medical domain with a very catastrophic outcome, at 91 or 92% precision, you're still going to go in there and have somebody do a biopsy on it. Very different than if you're investing money and there's a 92% chance you're going to earn 10% and 8% chance you're going to lose 8%. You're probably going to bet the money, because at that odds it's pretty good that you'll make some money, and in the long run, you do that enough, you definitely will make money. And also with this domain, I've actually seen them use this to identify different forms of cancer. That's one of the things that they're starting to use these models for, because then it helps the doctor know what to investigate. So that wraps up this section. We're going to go in there and let's discuss the answer to the quiz asked in Machine Learning Tutorial Part 1. Can you tell what's happening in the following cases? Grouping documents into different categories based on the topic and content of each document. This is an example of clustering where k-means clustering can be used to group the documents by topics using bag of words approach. So if you've gotten in there that you're looking for clustering, and hopefully you had at least one or two examples like k-means that are used for clustering different things, then give yourself a 2 thumbs up. B. Identifying handwritten digits in images correctly. This is an example of classification. The traditional approach to solving this would be to extract digit-dependent features like curvature of different digits, etc., and then use a classifier like SVM to distinguish between images. Again, if you got the fact that it's a classification example, give yourself a thumb up, and if you're able to go, hey, let's use SVM or another model for this, give yourself those 2 thumbs up on it. C. Behavior of a website indicating that the site is not working as designed. This is an example of anomaly detection. In this case, the algorithm learns what is normal and what is not normal, usually by observing the logs of the website. Give yourself a thumbs up if you got that one. And just for a bonus, can you think of another example of anomaly detection? One of the ones I use it for in my own business is detecting anomalies in stock markets. Stock markets are very fickle and they behave very erratic. So finding those erratic areas and then finding ways to track down why they're erratic. Was something released in social media? Was something released? You can see where knowing where that anomaly is can help you to figure out what the answer is to it in another area. D. Predicting salary of an individual based on his or her years of experience. This is an example of regression. This problem can be mathematically defined as a function between independent, years of experience, and dependent variables, salary of an individual. And if you guessed that this was a regression model, give yourself a thumbs up. And if you're able to remember that it is between independent and dependent variables and that terms, give yourself 2 thumbs up.
We're going to cover mathematics for machine learning. So today's agenda is going to cover data and its types. Then we're going to dive into linear algebra and its concepts, calculus, statistics for machine learning, probability for machine learning, hands-on demos. And of course, thrown in there in the middle is going to be your matrices and a few other things to go along with all this. Data and its types. Data denotes the individual pieces of factual information collected from various sources. It is stored, processed, and later used for analysis. And so we see here just a huge grouping of information, a lot of text stuff, money, dollar signs, numbers, and then you have your performing analytics to drive insights. And hopefully you have a nice your shareholders gathered at the meeting and you're able to explain it in something they can understand. So we talk about types of data. We have, in our types of data, we have a qualitative, categorical. You think nominal or ordinal. And then you have your quantitative or numerical, which is discrete or continuous. And let's look a little closer at those data types. Vocabulary, always people's favorite is the vocabulary words. Okay, not mine. But let's dive into this, what we mean by nominal. Nominal, they are used to label label our variables without providing any measurable value. Country, gender, race, hair, color, etc. It's something that you either mark true or false. This is a label. It's on or off. Either they have a red hat on or they do not. So a lot of times when you're thinking nominal data labels, think of it as a true-false kind of setup. And we look at ordinal. This is categorical data with a set order or a scale to it. And you can think of salary range as a great one. Movie ratings, etc. You can see here the salary range. If you have 10,000 to 20,000, number of employees earning that rate is 150. 20,000 to 30,000, 100, and so forth. Some of the terms you'll hear is bucket. This is where you have 10 different buckets and you want to separate it into something that makes sense into those 10 buckets. And so when we start talking about ordinal, a lot of times when you get down to the brass bones, again, we're talking true false. So if you're a member of the 10 to 20K range, so forth. Those would each be either part of that group or you're not. But now we're talking about buckets and we want to count how many people are in that bucket. Quantitative numerical data falls into two classes, discrete or continuous. And so data with a final set of values which can be categorized. Class strength, questions answered correctly, and runs hit in cricket. A lot of times when you see this, you can think integer, and a very restricted integer, i.e. you can only have 100 questions on a test, so it's very discrete. I only have 100 different values that it can attain. So usually you're talking about integers, but within a very small range. They don't have an open end or anything like that. So discrete is very solid, simple to count, set number. Continuous, on the other hand, continuous data can take any numerical value within a range. So water pressure, weight of a person, etc. Usually we start thinking about float values where they can get phenomenally small in what they're worth. And there's a whole series of values that falls right between discrete and continuous. You can think of the stock market. You have dollar amounts. It's still discrete, but it starts to get complicated enough when you have jump in the stock market from $525.33 to $580.67. There's a lot of point values in there. It'd still be called discrete, but you start looking at it as almost continuous because it does have such a variance in it. Now, we talk about we went over nominal and ordinal, almost true-false charts, and we looked at quantitative and numerical data, which we're starting to get into numbers. Discrete, you can usually, a lot of times discrete could be put into true-false, but usually it's not. So we want to address this stuff, and the first thing we want to look at is the very basic, which is your algebra. So we're going to take a look at linear algebra. You can remember back when your Euclidean geometry. We have a line. Well, let's go through this. We have a linear algebra is the domain of mathematics concerning linear equations and their representations in vector spaces and through matrices. I told you we're going to talk about matrices. So a linear equation is simply 2x plus 4y minus 3z equals 10. Very linear. 10x plus 12.4y equals z. And now you can actually solve these two equations by combining them. And that's where we're talking about a linear equation. In the vectors, we have a plus b equals c. Now we're starting to look at a direction. And these values usually think of an x, y, z plot. So each one is a direction. And the actual distance of like a triangle AB is c. And then your matrix can describe all kinds of things. I find matrices confuse a lot of people, not because they're particularly difficult, but because of the magnitude and the different things they're used for. And a matrix is a chart or think of a spreadsheet, but you have your rows and your columns. And you'll see here we have A times B equals C. Very important to know your counts. So depending on how the math is being done, what you're using it for, making sure you have the same rows and number of columns or a single number. There's all kinds of things that play in that can make matrices confusing. But really it has a lot more to do with what domain you're working in. Are you adding in multiple polynomials where you have like ax squared plus by plus, you start to see that it can be very confusing versus a very straightforward matrix. And let's just go a little deeper into these because these are such primary. This is what we're here to talk about is these different mathematical computations that come up. So when we're looking at linear equations, let's dig deeper into that one. An equation having a maximum order of 1 is called a linear equation. So it's linear because when you look at this, we have ax plus b equals c, which is a 1 variable. We have two variable ax plus by equals c, ax plus by plus cz equals d, and so forth. But all of these are to the power of 1. You don't see x squared. You don't see x cubed. So when we're talking about linear equations, that's what we're talking about. In their addition, if you have already dived into, say, neural networks, you should recognize this ax plus by plus cz setup plus the intercept, which is basically your neural network, each node adding up all the different inputs. And we can drill down into that. Most common formula is your y equals mx plus c. So you have your y equals the m, which is your slope, your x value plus c, which is your y-intercept. They kind of labeled it wrong here. Threw me for a loop. But the c would be your y-intercept. So when you set x equal to 0, y equals c. And that's your y-intercept right there. And they just had reversed value of y when x equals 0. It equals the y-intercept, which is c. And your slope gradient line, which is your m. So you get your y equals 2x plus 3. And there's lots of easy ways to compute this. This is why we always start with the most basic one when we're solving one of these problems. And then, of course, one of the most important takeaways is the slope gradient of the line. So the slope is very important, that m value. In this case, we went ahead and solved this. If you have y equals 2x plus 3, you can see how it has a nice line graph here on the right. So, matrices. A matrix refers to a rectangular representation of an array of numbers arranged in columns and rows. So we're talking m rows by n columns. Here, A11 denotes the element of the first row in the first column. Similarly, A12, and it's really pronounced A11 in this particular setup. So it's row 1, column 1. A12 is A row 1, column 2. First row and second column, and so on. And there's a lot of ways to denote this. I've seen these as like a capital letter A, smaller case a for the top row. Or, I mean, you can see where they can go all kinds of different directions as far as the value. You just take a moment to realize there needs to be some designation as far as what row it's in and what column it's in. And we have our basic operations. We have addition. So when you think about addition, you have two matrices of 2 by 2, and you just add each individual number in that matrix, and then when you get to the bottom, you have, in this case, the solution is 12, 10 plus 2 is 12, 5 plus 3 is 8, and so on. And the same thing with subtraction. Now again, you're counting matrices, you want to check your dimensions of the matrix. The shape, you'll see shape come up a lot in programming, so we're talking about dimensions, we're talking about the shape. If the two shapes are equal, this is what happens when you add them together or subtract them. And we have multiplication. When you look at the multiplication, you end up with a very slightly different setup going. Now, if we look at our last one, we're like, why? This always gets to me when we get to matrices, because they don't really say why you multiply matrices. My first thought is 1 times 2, 4 times 3. But if you look at this, we get 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5, 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5. If you're looking at these matrices, think of this more as an equation. And so we have, if you remember, when we back up here for our multiple line equations, let's just go back up a couple slides where we were looking at 2 variable. So this is a 2 variable equation, ax plus by equals c. And this is a way to make it very quick to solve these variables, and that's why you have the matrix, and that's why you do the multiplication the way they do. And this is the dot product of 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5, 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5, and it gives us a nice little 14, 23, 21, and 33 over here, which then can be used and reduced down to a simple formula as far as solving the variables as you have enough inputs. And then in matrix operations, when you're dealing with a lot of matrices, now keep in mind, multiplying matrices is different than finding the product of 2 matrices, okay? So when we're talking about multiplication, we're talking about solving for equations. When you're finding the product, you are just finding 1 times 2. Keep that in mind because that does come up. I've had that come up a number of times where I am altering data and I get confused as to what I'm doing with it. Transpose, flipping the matrix over its diagonal. Comes up all the time where you still have 12, but instead of it being 12, 8, it's now 12, 14, 8, 21. You're just flipping the columns and the rows. And then, of course, you can do an inverse, changing the signs of the values across this main diagonal. And you can see here we have the inverse a to the minus 1, and it ends up with, instead of 12, 8, 14, 12, it's now minus 22, minus 12. Vectors. Vector just means we have a value and a direction. And we have down 4 numbers here on our vector. In mathematics, a one-dimensional matrix is called a vector. So if you have your x plot and you have a single value, that value is along the x-axis and it's a single dimension. If you have 2 dimensions, you can think about putting them on a graph. You might have x and you might have y, and each value denotes a direction. And then, of course, the actual distance is going to be the hypothesis of that triangle. And you can do that with 3 dimensionals, x, y, and z. And you can do it all the way to nth dimensions. So when they talk about the k-means for categorizing and how close data is together, they will compute that based on the Pythagorean theorem. So you would take the square of each value, add them all together, and find the square root, and that gives you a distance as far as where that point is, where that vector exists, or an actual point value. And then you can compare that point value to another one, and it makes a very easy comparison versus comparing 50 or 60 different numbers. And that brings us up to eigenvectors and eigenvalues. Eigenvectors, the vectors that don't change their span while transformation, and eigenvalues, the scalar values that are associated to the vectors. Conceptually, you can think of the vector as your picture. You have a picture, it's 2 dimensions, x and y. And so when you do those 2 dimensions and those 2 values, or whatever that value is, that is that point. But the values change when you skew it. And so if we take and we have a vector A, and that's a set value, B is you have A and B, which is your eigenvector. 2 is the eigenvalue. So we're altering all the values by 2. That means maybe we're stretching it out one direction, making it tall, if you're doing picture editing. That's one of the places this comes in. But you can see when you're transforming your different information, how you transform it is then your eigenvalue. And you can see here, vector after line transition, we have 3a. A is the eigenvector, 3 is the eigenvalue. So A doesn't change. That's whatever we started with. That's your original picture. And 3 is skewing it one direction, and maybe B is being skewed another direction. And so you have a nice tilted picture because you've altered it by the eigenvalues. So let's go ahead and pull up a demo on linear algebra. And to do this, I'm going to go through my trusted Anaconda into my Jupyter notebook, and we'll create a new notebook called linear algebra. Since we are working in Python, we're going to use our NumPy. I always import that as NP, our NumPy array. Probably the most popular module for doing matrices and things in. Given that this is part of a series, I'm not going to go too much into NumPy. We are going to go ahead and create 2 different variables, A for a NumPy array 10, 15, and B 29. We'll go ahead and run this, and you can see there's our 2 arrays, 10, 15, 29. And I went in and added a space there in between, so it's easier to read. And since it's the last line, we don't have to put the print statement on it unless you want. We can simply do A plus B. So when I run this, we have 10, 15, 29, and we get 30, 24, which is what you expect. 10 plus 20, 15 plus 9. You could almost look at this addition as being just adding up the columns on here coming down. And if we wanted to do it a different way, we could also do A dot T plus B dot T. Remember that T flips them. And so if we do that, we now get them, we now have 30, 24 going the other way. We could also do something kind of fun. There's a lot of different ways to do this. As far as a plus b, I can also do a plus b dot t. And you're going to see that that will come out the same, the 30, 24, whether I transpose a and b or transpose them both at the end. And likewise, we can very easily subtract two vectors. I can go a minus b. And we run that, and we get minus 10, 6. Now remember, this is the last line in this particular section, so I don't have to put the print around it. And just like we did before, we can transpose either the individual or we can transpose the main setup, and then we get a minus 10, 6 going the other way. Now, we didn't mention this in our notes, but you can also do a scalar multiplication. Let me just put down the scalar so you can remember that. And what we're talking about here is I have this array here, u, and if I go a times u, we'll take the value 2, we'll multiply it by every value in here. So 2 times 30 is 60, 2 times 15. And just like we did before, this happens a lot because when you're doing matrices, you do need to flip them. You get 60, 30 coming this way. So in NumPy, we have what they call dot product. And with this is in a two-dimensional vectors. It is the equivalent to matrix multiplication. And remember, we were talking about matrix multiplication, where it is the, well, let's walk through it. We'll go ahead and start by defining two NumPy arrays. We'll have 10, 20, 25, 6, or our u and our v. And then we're going to go ahead and do, if we take the values, and if you remember correctly, an array like this would be 10 times 25 plus 20 times 6. We'll go ahead and print that. There we go. And then we'll go ahead and do the np dot of u comma v. And we'll find when we do this, we go ahead and run this, we're going to get 370, 370. So this is a strain multiplication where they use it to solve linear algebra when you have multiple numbers going across. And so this could be very complicated. We could have a whole string of different variables going in here. But for this, we get a nice value for our dot multiplication. And we did addition earlier, which was just your basic addition. And of course, the matrix, you can get very complicated on these, or in this case, we'll go ahead and do, let's create two complex matrices. This one is a matrix of 12, 10, 4, 6, 4, 31. We'll just print out A so you can see what that looks like. Here's print A. When we print A out, you can see that we have a 2 by 3 layer matrix for A. And we can also put together, always kind of fun when you're playing with print values, we could do something like this. We could go in here. There we go. We could print A, we have it end with equals A, run, and this kind of gives it a nice look. Here's your matrix. That's all this is. Comma n means it just tags it on the end. That's all that is doing on there. And then we can simply add in what is A plus B, and you should already guess, because this is the same as what we did before. There's no difference. When we do a simple vector addition, we have 12 plus 2 is 14, 10 plus 8 is 18, and so on. And just like we did the matrix addition, we can also do A minus B and do our matrix subtraction. And we look at this, we have what? 12 minus 2 is 10, 10 minus 8, where are we? Oh, there we go. 8 minus, confusing what I'm looking at. I should have reprinted out the original numbers. But we can see here 12 minus 2 is, of course, 10. 10 minus 8 is 2. 4 minus 46 is minus 42, and so forth. So same as the subtraction as before, we just call it matrix subtraction. It's identical. Now, if you remember up here, we had scalar addition, where we're adding just one number to a matrix. You can also do scalar multiplication. And so simply, if you have a single value A and you have B, which is your array, we can also do A times B. When we run that, you can see here we have 2 times 4 is 8, 5 times 4 is 20, and so forth. You're just multiplying the 4 across each one of these values. And this is an interesting one that comes up. A little bit of a brain teaser is matrix and vector multiplication. And so when we're looking at this, we are, just do a regular arrays. It doesn't necessarily have to be a numpy array. We have A, which has our array of arrays, and B, which is a single array. And so we can, from here, do the dot AB, and this is going to return 2 values. And the first value is that, you could say it's like we're doing this array, B array, first with A and then with a second one. And so it splits it up. So you have a matrix of vector multiplication, and you can mix and match. When you get into really complicated back-end stuff, this becomes more common because you've got layers upon layers of data, and so you'll end up with a matrix and a set of vector matrices that you want to multiply. Now, keep in mind that if you're doing data science, a lot of times you're not looking at this. This is what's going on behind the scenes. So if you're in the scikit looking at sklearn, where you're doing linear regression models, this is some of the math that's hidden behind the scenes that's going on. Other times, you might find yourself having to do part of this and manipulate the data around so it fits right, and then you go back in and you run it through the scikit. And if we can do, up here where we did a matrix and vector multiplication, we can also do matrix to matrix multiplication. And if we run this where we have the 2 matrices, you can see we have a very complicated array that, of course, comes out on there for our dot. And just to reiterate it, we have our transpose of matrix, which is your dot T. And so if we create a matrix A and then we do transpose it, you can see how it flips it from 5, 10, 15, 20, 25, 30 to 5, 15, 25, 10, 20, 30, rows and columns. And certainly with the math, this comes up a lot. It also comes up a lot with XY plotting. When you put it into PyPlot, you have one format where they're looking at pairs of numbers, and then they want all of X's and all Y's. So, the transpose is an important tool both for your math and for plotting and all kinds of things. Another tool that we didn't discuss is your identity matrix. And this one is more definition. The identity matrix, we have here one where we just did 2. So it comes down as 1, 0, 0, 1, 1, 0, 0, 0, 1, 0. It creates a diagonal of 1. And what that is when you're doing your identities, you could be comparing all your different features to the different features and how they correlate. And of course, when you have feature 1 compared to feature 1 to itself, it is always 1, where usually it's between 0 and 1, depending on how well it correlates. So when we're talking about identity matrix, that's what we're talking about right here, is that you create this preset matrix and then you might adjust these numbers depending on what you're working with and what the domain is. And then another thing we can do to kind of wrap this up, we'll hit you with the most complicated piece of this puzzle here, is an inverse A matrix. And let's just go ahead and put the, it's a lengthy description. Let's go ahead and put the description. This is straight out of the website for NumPy. So given a square matrix A, here's our square matrix A, which is 2, 1, 0, 0, 1, 0, 1, 2, 1. Keep in mind, 3 by 3, it's square. It's got to be equal. It's going to return the matrix A inverse satisfying dot A inverse. So here's our matrix multiplication. And then, of course, it equals the dot, A inverse of A, with an identity shape of A dot shape 0. This is just reshaping the identity. That's a little complicated there. So we're going to have here's our array. We'll go ahead and run this, and you can see what we end up with is we end up with an array 0.5 minus 0.5 and so forth, with our 2, 1, 1 going down to 1, 0, 0, 1, 0, 1, 2, 1. Getting into a little deep on the math, understanding when you need this is probably is what's really important when you're doing data science versus handwriting this out and looking up the math and handwriting all the pieces out. You do need to know about the linear algorithm inverse of A. So if it comes up, you can easily pull it up, or at least remember where to look it up. We took a look at the algebra side of it. Let's go ahead and take a look at the calculus side of what's going on here with the machine learning. So calculus, oh my goodness, and differential equations, you got to throw that in there because that's all part of the bag of tricks, especially when you're doing large neural networks, but it also comes up in many other areas. The good news is most of it's already done for you in the back end. So when it comes up, you really do need to understand from the data science, not data analytics. Data analytics means you're digging deep into actually solving these math equations. And a neural network is just a giant differential equation. So when we talk about calculus, we're going to go ahead and understand it by talking about cars versus time and speed. So it helps to calculate the spontaneous rate of change. So suppose we plot a graph of the speed of a car with respect to time. So as you can see here, going down the highway, probably merged into the highway from an on-ramp. So I had to accelerate, so my speed went way up. Stuck in traffic, merged into the traffic. Traffic opens up, and I accelerate again up to the speed limit, and maybe it peters off up there. So you can look at this as the speed versus time. I'm getting faster and faster because I'm continually accelerating, and if I hit the brakes, it'd go the other way. So the rate of change of speed with respect of time is nothing but acceleration. How fast are we accelerating? The acceleration is the area between the start point of x and the end point of delta x. So we can calculate a simple, if you had x and delta x, we could put a line there, and that slope of the line is our acceleration. Now, that's pretty easy when you're doing linear algebra, but I don't want to know it just for that line and those 2 points. I want to know it across the whole of what I'm working with. That's where we get into calculus. So when we talk about the distance between x and delta x, it has to be the smallest possible near to 0 in order to approximate the acceleration. So the idea is that instead of, if you ever took a basic calculus class, they would draw bars down here, and you would divide this area up. Let's go back up a screen. You divide this area of this time period up into maybe 10 sections, and you'd use that, and you could calculate the acceleration between each one of those 10 sections kind of thing. And then we just keep making that space smaller and smaller until delta x is almost infinitesimally small. And so we get a function of a equals a limit as h goes to 0 of a function of a plus h minus a function of a over h. And that is you're computing the slope of the line. We're just computing that slope under smaller and smaller and smaller samples. And that's what calculus is. Calculus is the integral. You can see down here we have our nice integral sign. Looks like a giant S. And that's what that means, is that we've taken this down to as small as we can for that sampling. So we're talking about calculus. We're finding the area under the slope is the main process in the integration. Similar, small intervals are made of the smallest possible length of x plus delta x, where delta x approaches almost an infinitesimally small space. And then it helps to find the overall acceleration by summing up all the lengths together. So we're summing up all the accelerations from the beginning to the end. And so here's our integral. We sum of a of x times d of x equals a plus c. That is our basic calculus here. So when we talk about multivariate calculus deals with functions that have multiple variables. And you can see here we start getting into some very complicated equations. Change in w over change of time equals change of w over change of z. The differential of z to dx, the differential of x to dt. It gets pretty complicated. And it really translates into the multivariate integration using double integrals. And so you have the sum of f of x of y of d of a equals the sum from c to d and a to b of f of x of y dx dy equals the sum of a to b, sum of c to d of f x of y dy dx. Understanding the very specifics of everything going on in here and actually doing the math is usually calculus 1, calculus 2, and differential equations. So you're talking about 3 full-length courses to dig into and solve these math equations. What we want to take from here is when we're talking about calculus, we're talking about summing of all these different slopes. And so we're still solving a linear expression. We're still solving y equals mx plus b. But we're doing this for infinitesimally small x's, and then we want to sum them up. That's what this integral sign means. The sum of a of x d of x equals a plus c. And when you see these very complicated multivariate differentiation using the chain rule, when we come in here and we have the change of w to the change of t equals the change of w dz, and so forth. That's what's going on here. That's what these means. We're basically looking for the area under the curve, which really comes to how is the change changing? Speed's going up. How is that changing? And then you end up with a multiple layer. So if I have 3 layers of neural networks, how is the third layer changing based on the second layer changing, which is based on the first layer changing? And you get the picture here that now we have a very complicated multivariate integration with integrals. The good news is we can solve this mathematically, and that's what we do when you do neural networks and reverse propagation. So the nice thing is that you don't have to solve this on paper unless you're a data analysis and you're working on the back end of integrating these formulas and building the script to actually build them. So we talk about applications of calculus. It provides us the tools to build an accurate predictive model. So it's really behind the scenes. We want to guess at what the change of the change of the change is. That's a little goofy. I know. I just threw that out there. It's kind of a meta term. But if you can guess how things are going to change, then you can guess what the new numbers are. Multivariate calculus explains the change in our target variable in relation to the rate of change in the input variables. So there's our multiple variables going in there. If one variable is changing, how does it affect the other variable? And then in gradient descent, calculus is used to find the local and global maxima. And this is really big. We're actually going to have a whole section here on gradient descent because it is really, I talked about neural networks and how you can see how the different layers go in there, but gradient descent is one of the most key things for trying to guess the best answer to something. So let's take a look at the code behind gradient descent. And before we open up the code, let's just do real quick gradient descent. Let's say we have a curve like this. And most common is that this is going to represent your error. Oops. Error. There we go. Error. Hard to read there. And I want to make the error as low as possible. And so when I'm looking at it is I want to find this line here, which is the minimum value. So we're looking for the minimum. And it does that by sampling there. And then based on this, it guesses it might be someplace here. And it goes, hey, this is still going down. It goes here, and then goes back over here, and then goes a little bit closer. And it's just playing a high-low until it gets to that spot, that bottom spot. And so we want to minimize the error. And on the flip note, you could also want to be maximizing something. You want to get the best output of it. That's simply minus the value. So if you're looking for where the peak is, this is the same as a negative for where the valley is. I'm looking for that valley. That's all that is. And this is a way of finding it. So the cool thing is all the heavy lifting's done. I actually ended up putting together one of these a while back when I didn't know about Sidekick and I was just starting. Boy, it's a long while back. And is playing high-low. How do you play high-low, not get stuck in the valleys, figure out these curves and things like that? Well, you do that, and the back end is all the calculus and differential equations to calculate this out. The good news is you don't have to do those. So instead, we're going to put together the code. And let's go ahead and see what we can do with that. So, guys in the back put together a nice little piece of code here, which is kind of fun. Some things we're going to note, and this is really important stuff, because when you start doing your data science and digging into your machine learning models, you're going to find these things are stumbling blocks. The first one is current X. Where do we start at? Keep in mind, your model that you're working with is very generic. So whatever you use to minimize it, the first question is, where do we start? And we started at this because the algorithm starts at x equals 3. So we arbitrarily picked 5. Learning rate is how many bars to skip going one way or the other. In fact, I'm going to separate that a little bit because these two are really important. If we're dealing with something like this where we're talking about, well, here's the function we're going to use. Our gradient of our function, 2 times x plus 5, keep it simple. So that's the function we're going to work with. So if I'm dealing with increments of 1,000, 0.1 is going to be a very long time. And if I'm dealing with increments of 0.001, 0.1 is going to skip over my answer. So I won't get a very good answer. And then we look at precision. This tells us when to stop the algorithm. So again, very specific to what you're working on. If you're working with money and you don't convert it into a float value, you might be dealing with 0.01, which is a penny. That might be your precision you're working with. And then, of course, the previous step size, max iterations. We want something to cut out at a certain point. Usually that's built into a lot of minimization functions. And then here's our actual formula we're going to be working with. And then we come in and we go, while previous step size is greater than precision and iters is less than max iters. Say that 10 times fast. We're just saying if it's if we're still greater than our precision level, we still got to keep digging deeper. And then we also don't want to go past 1,000 or whatever this is, 1,000,000 or 10,000 running. That's actually pretty high. We almost never do max iterations more than like 100 or 200. Rare occasions you might go up to 400 or 500 if it's depending on the problem you're working with. So we have our previous equals our current. That way we can track time-wise. The current now equals the current minus the rate times the formula of our previous x. So now we've generated our new version. Previous step size equals the absolute current previous. So we're looking for the change in x. Iters equals iterations plus 1. That's so we know to stop if we get too far. And then we're just going to print the local minimum occurs at x on here. And if we go ahead and run this, you can see right here it gets down to this point and it says, hey, local minimum is minus 3.3222 for this particular series we created. And this is created off of our formula here, lambda x 2 times x plus 5. Now, when I'm running this stuff, you'll see this come up a lot in with the sklearn kit. And one of the nice reasons of breaking this down the way we did is I could go over those top pieces. Those top pieces are everything when you start looking at these minimization toolkits in built-in code. And so from, we'll just do, it's actually docs.scipy.org, and we're looking at the scikit. There we go. Optimize, minimize. You can only minimize one value. You have the function that's going in. This function can be very complicated. So we used a very simple function up here. It could be, there's all kinds of things that could be on there. And there's a number of methods to solve this as far as how they shrink down. And your x naught. There's your start value. So your function, your start value, there's all kinds of things that come in here that you can look at, which we're not going to. Optimization automatically creates, constraints, bounds. Some of this it does automatically, but the big thing I want to point out here is you need to have a starting point. You want to start with something that you already know is mostly the answer. If you don't, then it's going to have a heck of a time trying to calculate it out. Or you can write your own little script that does this and does a high-low guessing and tries to find the max value. That brings us to statistics. what this is kind of all about is figuring things out. A lot of vocabulary in statistics. So statistics, well, I guess it's all relative. It's definitely not an EDL class. So a bunch of stuff going on in statistics. Statistics concerns with the collection, organization, analysis, interpretation, and presentation of data. That is a mouthful. So we have from end to end, where does it come from? Is it valid? What does it mean? How do we organize it? How do we analyze it? And then you got to take those analyses and interpret it into something that people can use, kind of reduce it to understandable. And nowadays you have to be able to present it. If you can't present it, then no one else is going to understand what the heck you did. So when we look at the terminologies, there's a lot of terminologies depending on what domain you're working in. So clearly if you're working in a domain that deals with viruses and T cells and how does, where does it come from, and you're studying the different people, then you're going to have a population. If you are working with mechanical gear, a little bit different. If you're looking for the wobbling statistics to know when to replace a rotor on a machine or something like that, that can be a big deal. We have these huge fans that turn in our sewage processing systems. And so those fans, they start to wobble and hum and do different things that the sensors pick up. At one point, do you replace them instead of waiting for it to break, in which case it costs a lot of money. Instead of replacing a bushing, you're replacing the whole fan unit. An interesting project that came up for our city a while back. So population. All objects or measurements whose properties are being observed. So that's your population, all the objects. It's easy to see it with people because we have our population in large. But in the case of the sewer fans, we're talking about the fan units. That's the population of fans that we're working with. You have a parameter, a metric that is used to represent a population or characteristic. You have your sample, a subset of the population studied. You don't want to do them all because then you don't have if you come up with a conclusion for everyone, you don't have a way of testing it. So you take a sample. Sometimes you don't have a choice. You can only take a sample of what's going on. You can't study the whole population. And a variable, a metric of interest for each person or object in a population. Types of sampling. We have a probabilistic approach, selecting samples from a larger population using a method based on the theory of probability. And we'll go into a little bit more deeper on these. We have random, systematic, stratified. And then you have a non-probabilistic approach, selecting samples based on the subjective judgment of the researcher rather than random selection. It has to do with convenience, trying to reach a quota, or snowball. And they're very biased. That's one of the reasons you'll see this big stamp on it that says biased. So you gotta be very careful on that. So probabilistic sampling. When we talk about a random sampling, we select random size samples from each group or category. So it's as random as you can get. When we talk about systematic sampling, we're selecting random size samples from each group or category with a fixed periodic interval. So we kind of split it up. This would be like a time setup where our different categories. And you might ask your question, well, what is a category or a group? If you look at, I'm going to go back a window. Let's say we're studying economics of an area. We know pretty much that based on their culture and where they came from, they might need to be separated. And so, and when I say separated, I don't mean separated from their place where they live. I mean, as far as the analysis, we want to look at the different groups and make sure they're all represented. So if we had like an 80% of a group that is, say, Hispanic or Indian, and also in that same area, we have 20% who are, let's call her expatriates. They left America and they're nice, and your Caucasian group. We might want to sample a group that is representative of both. So we're talking about stratified sampling, and we're talking about groups. Those are the groups we're talking about. And that brings us to stratified sampling, selecting approximately equal size samples from each group or category. This way we can actually separate the categories and give us an insight into the different cultures and how that might affect them in that area. So you can see these are very, very different, kind of depends on what you're working with as far as your data and what you're studying. And so we can see here, just to go a little bit more, we'd have selecting 25 employees from a company of 250 employees randomly. Don't care anything about them, what groups they're in, which office they're in, nothing. And we might be selecting one employee from every 50 unique employees in a company of 250 employees. And then we have selecting one employee from every branch in the company office. So we have all the different branches. There's our group, or our categories by the branch. And the category could depend on what you're studying. So it has a lot of variation on there. You see this kind of grouping and categorizing is also used to generate a lot of misinformation. So if you only study one group and you say this is what it is, then everybody assumes that's what it is for everybody. And so you got to be very careful of that, and it's a very unethical thing to kind of do. So types of statistics. When we talk about statistics, we're going to talk about descriptive and inferential statistics. There are so many different terms in statistics to break it up. So we're talking about a particular setup. So we're talking about descriptive and inferential statistics. The base of the word describe is pretty solid. You're describing the data. What does it look like? With inferential statistics, we're going to take that from the small population to a large population. So if you're working with a drug company, you might look at the data and say, these people were helped by this drug. They did 80% better as far as their health, or 80% better survival rate than the people who did not have the drug. So we can infer that that drug will work in the greater populace and will help people. So that's where you get your inferential. So we are predicting how it's going to affect the greater population. So descriptive statistics. It is used to describe the basic features of data and form the basis of quantitative analysis of data. So we have a measure of central tendencies. We have your mean, median, and mode. And then we have a measure of spread, like your range, your interquartile range, your variance, and your standard deviation. And we're going to look at all these a little deeper here in a second. But one of them you can think of is how the data differences, what's the max, min range, all that stuff is your spread. And anything that's just a single number is usually your central tendencies, measure of central tendencies. So we talk about the mean. It is the average of the set of values considered. What is the average outcome of whatever's going on? And then your median separates the higher half and the lower half of data. So where's the center point of all your different data points? So your mean might have a couple really big numbers that skew it so that the average is much higher than if you took those outliers out, where the median would, by separating the high from the low, might give you a much lower number. You might look at it and say, oh, that's odd. Why is the average so much higher than the median? Well, it's because you have some outliers. Or why is it so much lower? And then the mode is the most frequent appearing value. This is really interesting if you're studying economics and how people are doing. You might find that the most common income, like in the U.S., was at one point $24,000 a year, where the average was closer to $80,000. And it's like, wow, what a difference. Well, there's some people who have a lot of money, and so that skews that way up. So the average person is not making that kind of money. And then you look at the median income, and you're like, well, the median income is a little bit closer to the average. So it does create a very interesting way of looking at the data. Again, these are all central tendencies, single numbers you can look at for the whole spread of the data. And we look at the measure of central tendencies. The mean is the average marks of a student in a classroom. So here we have the mean, sum of the marks of the students, total number of students. And as we talked about the median, if we have 0 through 10, and we take half the numbers and put them on one side of the line, half the numbers on the other side of the line, we end up with 5 in the middle. And then the mode. What mark was scored by most of the students in a test? In a simple case where most people scored like an 82% and got certain problems wrong, easy to figure out. Not so easy when you have different areas where like you have like the, let's go back to economy. A little bit more difficult to calculate if you have a large group that makes 30,000 and a slightly bigger group that makes 26,000. So what do you put down for the mode? Certainly there's a number of ways to calculate that, and there's actually different variations depending on what you're doing. So now we're looking at a measure of spread, range. What's the difference between the highest and the lowest value? First thing you want to look at, it's we had everybody in the test scored between 60 and 100%. Somebody got 100%, or maybe 60 to 90%. It was so hard that a lot of people could not get 100%. Then you have your interquartile range. Quartiles divide a rank-ordered data set into 4 equal parts. Very common thing to do as part of all the basic packages, whether you're working in data frames with pandas, whether you're working in Scala, whether you're working in R. You'll see this come up where they have range, your min, your max, and then it'll have your interquartile range. How does it look like in each quarter of data? Variance measures how far each number in the set is from the mean and therefore from every other number in the set. So you have like how much turbulence is going on in this data. And then the standard deviation. It is the measure of the variance or the dispersion of a set of values from the mean. And you'll usually see, if I'm doing a graph, I might have the value graphed, and then based on the error, I might graph the standard deviation and the error on the graph as a background, so you can see how far off it is. So standard deviation is used a lot. So measurement of spread. Marks of a student out of 100. We have here from 50 to 63 or 50 to 90. So the range, maximum marks, minimum marks, we have 90 to 45, and the spread of that is 45, 90 minus 45. And then we have the interquartile range using the same marks over there. You can see here where the median is. And then there's the first quarter, the second quarter, and the third quarter based on splitting it apart by those values. And to understand the variance and standard deviation, we first need to find out the mean. So here's our calculating the average there. We end up at approximately 66 for the average. And then we look at that and the variance. Once we know the means, we can do equals the marks minus the mean squared. Why is it squared? Because one, you want to make sure you don't have like if you're putting all this stuff together, you end up with an error as far as one's negative, one's positive, one's a little higher, one's a little lower. So you always see the squared value and over the total observations. And so the standard deviation equals the square root of the variance, which is approximately 16. And if you were looking at a predictable model, you would be looking at the deviation based on the error. How much error does it have? And that's, again, really important to know. If your prediction is predicting something, what's the chance of it being way off or just a little bit off? Now that we've looked at the tools as far as some of the basics for doing your statistics and what we're talking about, let's go ahead and pull up a little demo and show you what that looks like in Python code, so you can get some little hands-on here. For that, let's go back into our Jupyter Notebook in Python. Now, almost all of this you can do in NumPy. Last time we worked in NumPy. This time we're going to go ahead and use pandas. And if you remember from pandas on here, this is basically a data frame, rows, columns. Let's just go ahead and do a print df.head and run that. And you can see we have the name Jane, Michael, William, Rosie, Hannah, and their salaries on here. And of course, instead of having to do all those hand calculations and add everything together and divide by the total, we can do something very simple on this, like use the command mean in pandas. And so if I go ahead and do this, print df, pick our column, salary, because we want to find the means of that column. We want to find the means of that column. And we go ahead and print this out, and you can see that the average income on here is 71,000. And let's just go ahead and do this. We'll go ahead and put in means. And if we're going to do that, we also might want to find the median. And the median is very similar, except it actually is just median. We're used to means and average. It's kind of interesting that they use the two different words. There can be, in some computations, slight differences, but for the most part, the means is the average. And then the median, let's put a median here, df salary, that way it displays a little better. We can see the median is 54,000. So the halfway mark is significantly below the average. Why? Because we have somebody in here who makes $189,000. Darn you, Rosie, for throwing off our numbers. But that's something you'd want to notice. This is the difference between these is huge, and so is what is the meaning behind that when you're studying a populace and looking at the different data coming in. And of course, we also want to find out, hey, what's the most common income that people make in this little tiny sample? And so we'll go ahead and do the mode. And you can see here with the mode, it's at 50,000. So this is very telling that most people are making 50,000. The middle point is at 54,000, so half the people are making more than that. What that tells me is that if the most common income is below the median, then there's a lot of high salaries going up, but there's some really low salaries in there. And so this trend, which is very common in statistics, when you're analyzing the economy and different people's income, is pretty common. And the bigger difference between these is also very important when we're studying statistics. And when you hear someone just say, hey, the average income was, you might start asking questions at that point. Why aren't you talking about the median income? Why aren't you talking about the mode, the most common income? What are you hiding? And if you're doing these analyses, you should be looking at these saying, hey, why are these discrepancies? Why are these so different? And of course, with any analysis, it's important to find out the minimum and the maximum. So we'll go ahead. It's just simply dot min will pull up your minimum, and then dot max pulls up the maximum. Pretty straightforward on as far as translating it and knowing what what your lowest value and what your highest value is here, which you'll use to generate like a spread later on. And real quick on mode, note that it puts mode 0. Like I said, there's a couple different ways you can compute the mode, although the standard one's pretty good. We can, of course, do the range, which is your max minus your min. So now we have a range of 149,000 between the upper end and the lower end. And you might want to be looking up the individual values on all of these. But it turns out there is a describe feature in pandas. And so in pandas, we can actually do df salary describe. And if we do this, you can see we have that there's 7 setups. Here's our mean, our standard deviation, which we didn't compute yet, which would just be a .std. And you got to be a little careful because when it computes it, it looks for axes and things like that. We have our minimum value, and here's our quartiles, our maximum value, and then of course the name salary. So these are the basic statistics. You can pull them up and like just describe. This is a dictionary, so I could actually do something like in here I could actually go count and run, and now it just prints the count. So because this is a dictionary, you can pull any one of these values out of here. It's kind of a quick and dirty way to pull all the different information and then split it up depending on what you need. Now, if I just walked in and gave you this information in a meeting, at some point you would just kind of fall asleep. That's what I would do anyway. So we want to go ahead and see about graphing it here. And we'll go ahead and put it into a histogram and plot that graph on it of the salaries. And let's just go ahead and put that in here. So we do our matplot inline. Remember, that's a Jupyter's Notebook thing. A lot of the new version of the matplot library does it automatically, but just in case, I always put it in there. Import matplot library, pyplot is PLT, that's my plotting. And then we have our data frame. I guess I really don't need to respell the data frame. Maybe we could just remind ourselves what's in it. So we'll go ahead and just print df. That way we still have it. And then we have our salary df salary, salary.plot history title, salary distribution, color gray, plot AXV line, salary the mean value. So we're going to take the mean value, color violet, line style dash. This is just all making it pretty. What color, dash line, line width of 2, that kind of thing. And the median. And let's go ahead and run this just so you can see what we're talking about. And so up here we are taking on our plot. So here's the data. Here's our data frame printed out so you can see it with the salaries. And we're looking at the salary distribution. And just look at this, the way the salary is distributed. You have our In this case, we did, let's see, we had red for the median. We have violet for our average or mean. And you can just see how it really, I mean, here's our outlier. Here's our person who makes a lot of money. Here's the average, and here's the median. And so as you look at this, you can say, wow, based on the average, it really doesn't tell you much about what people are really taking home. All it does is tell you how much money is in this, what the average salary is. So some of the things you want to take away in addition to this is that it's very easy to plot an AX V line. These are these up and down lines for your markers. And as you display the data, I mean, you can add all kinds of things to this and get really complicated. Keeping it simple is pretty straightforward. I look at this and I can see we have a major outlier out here. We can definitely do a histogram and stuff like that. But, picture's worth 1,000 words. What you really want to make sure you take away is that we can do a basic describe, which pulls all this information out, and we can print any of the individual information from the describe, because this is a dictionary. And so if we want to go ahead and look up the mean value, we can also do describe mean. So if you're doing a lot of statistics, being able to, it doesn't have the print on there, so it's only going to print the last one, which happens to be the mean. You can very easily reference any one of these. And then you can also, if you're doing something a little bit more complicated and you don't need just the basics, you can come through and pull any one of the individual references from the pandas on here. So now we've had a chance to describe our data. Let's get into inferential statistics. Inferential statistics allows you to make predictions or inferences from data. And you can see here we have a nice little picture of movie ratings, and if we took this group of people and said, hey, how many people like the movie, dislike it, can't say, and then you ask just a random person who comes out of the movie who hasn't been in this study, you can infer that 55% chance of saying liked, 35% chance of saying disliked, or a 10 or 11% chance of can't say. So that's real basics of what we're talking about, is you're going to infer that the next person is going to follow these statistics. So let's look at point estimation. It is a process of finding an approximate value for a population's parameter, like mean or average, from random samples of the population. Let's take an example of testing vaccines for COVID-19. Vaccines and flu bugs, all of that, it's a pretty big thing of how do you test these out and make sure they're going to work on the populace. A group of people are chosen from the population. Medical trials are performed. Results are generalized for the whole population. So here's our small group up here where we've selected them. We run medical trials on them, and then the results work for the population. Nice diagram with the arrows going back and forth and the very scary COVID virus in the middle of one. And let's take a look at the applications of inferential statistics. Very central is what they call hypotheses testing, and the confidence interval, which go with that. And then as we get into probability, we get into our binomial theorem, our normal distribution, and central limit theorem. Hypothesis testing. Hypothesis testing is used to measure the plausibility of a hypothesis, assumption, by using sample data. Now, when we talk about theorems, theory, hypothesis, keep in mind that if you are in a philosophy class, theory is the same as hypothesis, where theorem is a scientific statement that is something that has been proven, although it is always up for debate, because in science we always want to make sure things are up to debate. So a hypothesis is the same as a philosophical class calling a theory, where theory in science is not the same. Theory in science says this has been well proven. Gravity is a theory. So if you want to debate the theory of gravity, try jumping up and down. If you want to have a theory about why the economy is collapsing in your area, that is a philosophical debate. Very important. I've heard people mix those up, and it is a pet peeve of mine. When we talk about hypotheses testing, the steps involved in hypotheses testing is first we formulate a hypothesis. We figure out the right test to test our hypothesis. We execute the test, and we make a decision. And so when you're talking about hypothesis, you're usually trying to disprove it. If you can't disprove it and it works for all the facts, then you might call that a theorem at some point. So in a use case, let's consider an example. We have 4 students who are given a task to clean a room every day. Sounds like working with my kids. They decided to distribute the job of cleaning the room among themselves. They did so by making 4 chits, which has their names on it, and the name that gets picked up has to do the cleaning for that day. Rob took the opportunity to make chits and wrote everyone's name on it. So here's our 4 people: Nick, Rob, Imlia, and Summer. Now, Rick, Imlia, and Summer are asking us to decide whether Rob has done some mischief in preparing the chits, i.e., whether Rob has written his name on one of the chit. For that, we will find out the probability of Rob getting the cleaning job on first day, second day, third day, and so on till 12 days. The probability of Rob getting the job decreases every day, i.e., his turn never comes up, then definitely he has done some mischief while making the chits. So the probability of Rob not doing work on day 1 is 3 out of 4. There's a 0.75 chance that he didn't do work. 2 days, 3/4 times 3/4 equals 0.56. 3 days, you have 3/4, 3/4, 3/4, which equals 0.42. When you get to day 12, it's 0.032, which is less than 0.05. Remember this 0.05. That comes up a lot when we're talking about certain values, when we're looking at statistics. Rob is cheating as he wasn't chosen for 12 consecutive days. That's a very high probability when on day 12 he still hasn't gotten the job cleaning the room. So we come up to our important terminologies. We have null hypothesis, a general statement that states that there is no relationship between 2 measured phenomena or no association among the groups. Alternative hypothesis. Contrary to the null hypothesis, it states whenever something is happening, a new theory is preferred instead of an old one. And so the 2 hypotheses go hand in hand. So your null, this is always interesting in when we're talking about data science and the math behind it, it's about proving that the things have no correlation. Null hypothesis says these 2 have 0 relation to each other. Where the alternative hypothesis says, hey, we found a relation, this is what it is. We have p-value. The p-value is the probability of finding the observed or more extreme results when the null hypothesis of a study question is true. And the t-value. It is simply the calculated difference represented in units of standard error. The greater the magnitude of t, the greater the evidence against the null hypothesis. And you can look at the t-value as being specific to the test you're doing, where the p-value is derived from your t-value, and you're looking for what they call the 5% or the 0.05, showing that it has a high correlation. So digging in deeper, let's assume that a new drug is developed with the goal of lowering the blood pressure more than the existing drug. And this is a good one because the null value here isn't that you don't have any drug. The null value here is that it's better than the existing drug. The new drug doesn't lower the blood pressure more than the existing drug. Now, if we get that, that says our null hypothesis is correct. There is no correlation, and the new drug is not doing its job. The alternative hypothesis, the new drug does significantly lower the blood pressure more than the existing drug. Yay, we got a new drug out there. And that's our alternative hypothesis, or the H1 or HA. And we look at the p-value, results from the evidence like medical trials showing positive results which will reject the null hypothesis. And again, they're looking for a 0.05 or 5%. And the t-value, comparing all the positive test results and finding means of different samples in order to test hypothesis. So this is specific to the test. What percentage of increase did they have? And this leads us to the confidence intervals. A confidence interval is a range of values we are sure are true values of observations lie in. Let's say you asked a dog owner around you and asked them, how many cans of food do you buy for your per year for your dog? Through calculations, you got to know that on an average, around 95% of the people bought around 200 to 300 cans of food. Hence, we can say that we have a confidence interval of 2-300, where 95% of our values lie in that data spread. And the graph really helps a lot, so you can start seeing what you're looking at here, where you have the 95%, you have your peak. In this case, it's a normal distribution, so you have the nice bell curve equal on both sides. It's not asymmetrical. And 95% of all the values lie within a very small range, and then you have your outliers, the 2.5% going each way. So we touched upon hypothesis, and we're going to move into probability. So you have your hypothesis. Once you've generated your hypothesis, we want to know the probability of something occurring. Probability is a measure of the likelihood of an event to occur. Any event can be predicted with total certainty and can only be predicted as a likelihood of its occurrence. So any event cannot be predicted with total certainty. It can only be predicted as a likelihood of its occurrence. Score prediction, how good you're going to do in whatever sport you're in, weather prediction, stock prediction. If you've studied physics and chaos theory, even the location of the chair you're sitting on has a probability that it might move 3 feet over. Granted, that probability is 1 in I think we calculated it as under 1 in trillions upon trillions. So it's the better the probability, the more likely it's going to happen. There are some things that have such a low probability that we don't see them. So we talk about a random variable. Random variable is a variable whose possible values are numerical outcomes of a random phenomena. So we have the coin toss. How many heads will occur in the series of 20 coin flips? Probably, on average they're 10, but you really can't know because it's very random. How many times a red ball is picked from a bag of balls, if there's equal number of red balls and blue balls and green balls in there. How many times the sum of digits on 2 dice result are 5 each. There's how often you're going to roll 2 5s on your pair of dice. So in a use case, let's consider the example of rolling 2 dice. We have a random variable outcome equals y. You can take values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a random variable and a combination of dice. And instead of looking at how many times both dice will roll 5, let's go ahead and look at total sum of 5. And you have, as far as your random variables, you can have a 1, 4 equals 5, 4, 1, 2, 3, 3, 2. So 4 of those rolls can be 4. If you look at all the different options you have, 4 of those random rolls can be a 5. And if we look at the total number, which happens to be 36 different options, you can see that we have 4 out of 36 chance every time you roll the dice that you're going to roll a total of 5. You're going to have an outcome of 5. And we'll look a little deeper as to what that means. But you could think of that at what point, if someone never rolls a 5 or they always roll a 5, can you say, hey, that person's probably cheating? We'll look a little closer at the math behind that. But let's just consider this as one of the cases is rolling 2 dice and gambling. There's also a binomial distribution. It is the probability of getting success or failure as an outcome in an experiment or trial that is repeated multiple times. And the key is bi, meaning 2, binomial. So passing or failing an exam, winning or losing a game, and getting either head or tails. So if you ever see binomial distribution, it's based on a true-false kind of setup. You win or lose. Let's consider a use case, and let's consider the game of football between 2 clubs, Barcelona and Dortmund. The teams will have to play a total of 4 matches, and we have to find out the chances of Barcelona winning the series. So we look at the total games, and we're looking at 5 different games or matches. Let's say that the winning chance for Barcelona is 75% or 0.75. That means at each game, they have a 75% chance that they're going to win that game. And losing chances are 25% or 0.25. Clearly 0.75 plus 0.25 equals 1. So that accounts for 100% of the game. Probability for getting K wins in N matches is calculated. And we're talking so if you have 5 games and you want to know if I play how many wins in those 5 games should I get? What's a percentage on those? And the probability for getting K wins in N matches is calculated by Px equals K equals NCK, P to the K, Q to the N minus K. Here, P is the probability of success and Q is the probability of failure. And so we can do total games of N equals 5, where K equals 0, 1, 2, 3, 4, 5. P, which is the chance of winning, is 0.75. Q, the chance of losing, equals 1 minus P, which equals 1 minus 0.075, which equals 0.25. The probability that Barcelona will lose all of the matches can then just plug in the numbers. and we end up with a 0.0009765,625. So very small chance they're going to lose all their matches. And we can plug in the value for 2 matches. Probability that Barcelona will win at least 2 matches is 0.0878. And of course we can go on to the probability that Barcelona will win 3 matches, the 0.26, and of course 4 matches, and so on. And it's always nice to take this information and let's find the cumulative discrete probabilities for each of the outcomes. Where Barcelona has won 3 or more matches, x equals 3, x equals 4, x equals 5. And we end up with the p equals 0.264 plus 0.395 plus 237, which equals 0.89. In reality, the probability of Barcelona winning the series is much higher than 0.75. And it's always nice to put out a nice graph so you can actually see the number of wins to the probability and how that pans out with our binomial case. Continuing in our important terminology, location. The location of the center of the graph depends on the mean value. And this is some very important things. So much of the data we look at, and when you start looking at probabilities, almost always has a normalized look, like the graph in the middle. But you do have left skewed, where the data is skewed off to the left, and you have more stuff happening off to the left, and you have right skewed data. And so when this comes up and these probabilities come up where they're skewed, it's really important to take a closer look at that. Mostly you end up with a normalized set of data, but you got to also be aware that sometimes it's a skewed data. And then the height. Height of the slope inversely depends upon the standard deviation. So you can see down here the standard deviation is really large. It kind of squishes it out. And if the standard deviation is small, then most of your data is going to hit right there in the middle. You're going to have a nice peak. And so being aware of this, that you might have a probability that fits certain data, but it has a lot of outliers. So if you have a really high standard deviation, if you're doing stock market analysis, this means your predictions are probably not going to make you much money. Where if you have a very small deviation, you might be right on target and set to become a millionaire. Which leads us to the z-score. Z-score tells you how far from the mean a data point is. It is measured in terms of standard deviations from the mean. Around 68% of the results are found between 1 standard deviation. Around 95% of the results are found between 2 standard deviations. And you read the symbols. Of course, they love to throw some Greek letters in there. We have mu minus 2 sigma. Mu is just a quick way. It's that kind of funky U. It just means the mean. And then the sigma is the standard deviation. And that's the O with the little arrow off to the right, or the little waggly tail going up. The O with a line on it. So mu minus 2 sigma is your 95% of the results are found between 2 standard deviations. Central limit theorem. This goes back to the skew. If you remember, we were looking at the skew values on this previous slide. Have left skewed, normalized, and right skewed. When we're talking about it being skewed or not skewed, the distribution of the sample means will be approximately normally distributed, evenly distributed, not skewed, if you take large random samples from the population with the mean, mu, and the standard deviation, sigma, with replacement. And you can see here, of course, we have our mu minus 2 sigma and the spread down here, the mean, the median, and the mode. And so when you're talking about very large populations, these numbers should come together and you shouldn't have a skewed value. If you do, that's a flag that something's wrong. That's why this is so important to be aware of what's going on with your data, where your samples are coming from, and the math behind it. And if we're going to do all this, we got to jump into conditional probability. The conditional probability of an event A is a probability that the event will occur given the knowledge that an event B has already occurred. And you'll see this as Bayes' theorem, B-A-Y-E-S, Bayes. And this is read, I mean, you have these funky looking little P brackets, A, B. This is the probability of A being true while B is already true. And you have the probability of B being true when A is already true, so P, B of A. The probability of A being true divided by the probability of B being true. And we talk about Bayes' theorem, which occurred back in the 1800s when he discovered this. This is such an important formula, and it's not, if you actually do the math, you could just kind of do xy equals jk, and then you divide them out, and you're going to see the same math, but it works with probabilities, which makes it really nice. And so if you have you might have 8 or 9 different studies going on in different areas. Different people have done the studies, they brought them together. If we look at today's COVID virus, the virus spread, certainly the studies done in China versus the studies the way they're done in the US, that data is different in each of those studies. But if you can find a place where it overlaps, where they're studying the same thing together, you can then compute the changes that you need to make in one study to make them equal. And this is also true if you have a study of one group and you want to find out more about it. So this formula is very powerful, and it really has to do with the data collection part of the math and data science, and understanding where your data is coming from and how you're going to combine different studies in different groups. And we'll go ahead and go into a use case. Let's find out the chance of a person getting lung disease due to smoking. And this is kind of interesting the way they word this. Let's say that according to medical report provided by the hospital, states that around 10% of all patients they treated suffered lung disease. So we have kind of a generic medical report. They further found out by a survey that 15% of the patients that visit them smoke. So we have 10% that are lung disease, and 15% of the patients smoke. And finally, 5% of the people continued smoke even when they had lung disease. Not the brightest choice, but it is an addiction, so it can be really difficult to kick. And so we can look at the probability of A, prior probability of 10% people having lung disease. And then probability B, probability that a patient smokes is 15%. And the probability of B, if B then A, the probability of a patient smokes even though they have lung disease is 5%. And probability of A is B, probability that the patient will have lung disease if they smoke. And then when you put the formulas together, you get a nice solution here. You get the probability of A of B, probability that the patient will have lung disease if they smoke. And you can just plug the numbers right in, and we get a 3.33% chance. Hence, there is a 3.33% chance that a person who smokes will get a lung disease. So we're going to pull up a little Python code. Always my favorite. Roll up the sleeves. Keep in mind, we're going to be doing this kind of like the back end way, so that you can see what's going on. And then later on, we're going to create, we'll get into another demo which shows you some of the tools that are already pre-built for this. Let's start by creating a set. So we're going to create a set with curly braces. This means that our set has only unique values. So you have a list, you have your tuples, which can never change, and then you have, in this case, the set. So 4, 7, you can't create a 4, 7, comma 4. It'll delete the 4 out. So it's only unique values. And if you use dictionaries, quick reminder, this should look familiar because it is a dictionary where you have a value, and that value is assigned to, or that key is assigned to a value. So you could have a key value set up as a dictionary. So it's like a dictionary without the value. It's just the keys, and they all have to be unique. And if we run this, we have a set of 4, 7. We can also take a list, a regular setup, and I'm going to go ahead and just throw in another number in here, 4, and run it. And you can see here, if I take my list 1, 2, 3, 4, 4, and I convert it to a set, and here it is, my set from list equals set, my list. The result is 1, 2, 3, 4. So it just deletes that last 4 right out of there. And with the sets, you can also go in there and print, here is my set, 3 is in the set, and then if you do 3 in my set, that's going to be a logic function. And 1 in my set, 6 is not in the set, and so forth. If we run this, we get 3 is in the set true, 1 is in the set false, because 3, 5, 7 is another 1. 6 is in the set, 6 is not in the set, so not in my set. You can also use this with a list. We could have just used 3, 5, 7, and it would have the same response on there. Is 3 in? Usually you do if 3 is in, but 3 in my set still works on just a regular list. And we'll go ahead and do a little iteration. We're going to do kind of the dice one. Remember 1, 2, 3, 4, 5, 6. And so we're going to bring in an iteration tool and import product as product. And I'll show you what that means in just a second. So we have our 2 dice. We have dice A, and it's going to be a set of values. You can only have 1 value for each one. That's why they put it in a set. And if you remember from range, it is up to 7. So this is going to be 1, 2, 3, 4, 5, 6. It will not include the 7. And the same thing for our dice B. And then what we're going to do is we're going to create a list, which is the product of A and B. So what's A plus B? And if we go ahead and run this, it'll print that out, and you'll see, in this case, when they say product, because it's an iteration tool, we're talking about creating a tuple of the 2. So we've now created a tuple of all possible outcomes of the dice, where dice A is 1, 2, 3, 1 to 6, and dice B is 1 to 6. And you can see 1 to 1, 1 to 2, 1 to 3, and so forth. You remember we had a slide on this earlier where we talked about all the different outcomes of a dice. We can play around with this a little bit. We can do in dice equals 2, dice faces 1, 2, 3, 4, 5, 6. Another way of doing what we did before, and then we can create an event space where we have a set, which is the product of the dice faces, repeat equals in dice. And we'll go ahead and just run this. And you can see here, it just again puts it through all the different possible variables we can have. And then if we wanted to take the same set on here and print them all out like we had before, we can just go through for outcome and event space, outcome and equals. So the event space is creating a sequence. And as you can see here, when we print it out, it stacks them versus going through and putting them in a nice line. And we'll go ahead and do something, let's go print. Since we have the end printing with a comma, that just means it's not going to hit the return going down to the next line. And we'll go ahead and do the length of our event space. That'll be an important variable we're going to want to know in a minute. And of course, if I get carried away with my typing of length, we'll print it twice and it'll give me an error. So we have 36 different possible variations here. And we might want to calculate something like, what about the multiple of 3? What if we want to have the probability of the multiple of 3 in our setup? And so we can put together the code for the outcome and event space of x, y equals outcome. If x plus y remainder 3, so we're going to divide by 3 and look at the remainder, and it equals 0, then it's a favorable outcome. And we're going to pop that outcome on the end there. And we'll turn it into a set. So the favorable outcome equals a set. Not necessary because we know it's not going to be repeating itself, but just in case, we'll go ahead and do that. And if we want to print out the outcome, we can go ahead and see what that looks like. And you can see here, these are all multiples of 3. 1 plus 2 is 3, 5 plus 4 is 9, which divided by 3 is 3, and so forth. And just like we looked up the length of the one before, let's go ahead and print the length of our F outcome so we can see what that looks like. There we go. And of course I did forget to add the print in the middle because we're looping through and putting an end on the setup on there, so we're going to put the print in there. And if I run this, you can see we end up with 12. So we have 36 total options. We have 12 that are multiple that add up to a multiple of 3. And we can easily compute the probability of this by simply taking the length of our favorable outcome over the length of the event space. And if we print it out, let me put that in there, probability last line, so we can just type it in. We end up with a 0.3333 chance. And it's roughly a third. And we might want to make this look nice. So let's go ahead and put in another line there. The probability of getting the sum, which is a multiple of 3, is 0.3333. We can compute the same thing for 5 dice. And if we do this for 5 dice and go ahead and run it, you can see we just have a huge amount of choices. So it just goes on and on down here. And we can look at the length of the event space. And we have over 7,776 choices. That's a lot of choices. And if we want to ask the question like we did above, what is the sum, where the sum is a multiple of 5 but not a multiple of 3, we can go through all of these different options, and then you can see here D1, D2, D3, D4, D5 equals the outcome. And if you add these all together and the division by 5 does not have a remainder of 0, but the remainder is also of a division by 3 is not equal to 0. So the multiple of 5 is equal to 0, but the multiple of 3 is not. We can just append that on here, and then we can look at that favorable outcome. We'll go ahead and set that, and we'll just take a look at this. What's our length of our favorable outcome? It's always good to see what we're working with. And so we have 904 out of 776. And then, of course, we can just do a simple division to get the probability on here. What's the probability that we're going to roll a multiple of 5 when you add them together, but not a multiple of 3? And so we're just going to divide those two numbers, and you can see here we get 0.116255, or 11.62%. And so you can really have a nice visual that this is not really complicated math right here on probabilities. It's just how many options do you have, and how many of those are you possibly going to be able to come up with the solution you're looking for. And this leads us to a confusion matrix. A confusion matrix is a table which is used to describe the performance of a classification model on a set of test data for which the true values are known. And so you'll see on the left we have the predicted and the actual. And we have a negative, false negative, positive, true positive, and then we have false positive and true negative. And you can think of this as your predicted model. What does that mean? That means if you divided your data and you used 2/3 of it to create the model, you might then test it against an actual case for the last third to see how well it comes out. How many times was it true positive versus false positive? It gave a false positive response. And you can imagine in medical situations, this is a pretty big deal. You don't want to give a false positive. So you might adjust your model accordingly so you don't have a false positive. Say with a COVID virus test, it'd be better to have a false negative and they go back and get retested than to have 30% false positives where then the test is pretty much invalid. So in a use case like cancer prediction, let's consider an example where a cancer prediction model is put to the test for its accuracy and precision. Actual result of a person's medical report is compared with the prediction made by the machine learning model. And so you can see here, here's our actual predicted, whether they have cancer or not. You know, cancer, a big one. You don't want to have a false positive. A false negative. In other words, you don't want to have it tell you that you don't have cancer when you do. So that would be something you'd really be looking for in this particular domain. You don't want a false negative. And this is, again, you've created a model. You have hundreds of people or thousands of pieces of data that come in. There's a real famous case study where they have the imagery and all the measurements they take, and there's about 36 different measurements they take. And then if you run a basic model, you want to know just how accurate it is. How many negative results do you have that are either telling people they have cancer that don't, or telling people that don't have cancer that they do. And then we can take these numbers and we can feed them into our accuracy, our precision, and our recall. So accuracy, precision, and recall. Accuracy metric to measure how accurately the results are predicted. And this is your total true, where you got the right results, you add them together, the true positive, the true negative, over all the results. So what percentage of them were accurate versus what were wrong. When we talk about precision, is a metric to measure how many of the correctly predicted cases are actually turned out to be positive. So we have a precision on true positive. Again, if you're talking about like COVID testing with the viruses, you really want this to be a high number. You want this true that to be the center point, where you might have the opposite if you're dealing with cancer, where you want no false negatives. So this is your metric on here. Precision is your test positive, true positive plus false positive. And then your recall, how many of the actual positive cases we were able to predict quickly with our model. So test positive is the test positive plus the false negative on there. And we'll want to go ahead and do a demo on the naive Bayes classifier. Before I get too far into naive Bayes classifier, because we're going to pull it from the sklearn or the scikit, let's go ahead. Kind of an interesting page here for classifiers. When you go into the sklearn kit, there's a lot of ways to do classification. And I'll just zoom up in here so you can see some of the titles. There's everything from the nearest neighbor, linear, but we're going to be focusing on the naive Bayes over here. And this is just a sample data set that they put together, and you can see how some of these have a very different output. The naive Bayes, remember, is set up as probably the most simplified calculator or set of predictions out there. And so what we've been talking about with the true false and stuff like that, where there's a belief that there is a independent assumption between the features, where the features are very assumed to have some kind of connection, then we can go ahead and use that for the prediction. And so that's what we're using as a naive Bayes classifier versus many of the other classifiers that are out there. For this, we're going to use the social network ads. It's a little data set on here. And let me go ahead and just open that up, the file. Here we go. It has user ID, gender, age, estimated salary, purchased. And so we have, you can see the user ID, male, 19, estimated salary, 19,000, and purchased 0. So it's either going to make a purchase or not. So look at that last one, 0, 1. We should be thinking of binomials. We should be thinking of simple naive Bayes classifier kind of setup. So if we close this out, we're going to go ahead and import our NumPy as NP. We're going to nice to have a good visual of our data, so we'll put in our matplot library. Here's our pandas, our data frame. And then we're going to go ahead and import the data set. And the data set's going to be, we're going to read it from the socialnetworkads.csv. Then we're going to print the head just so you can see it again, even though I showed you it in the file. And X equals the data set iLocation, 2, 3 values, and Y is going to be the 4, column 4. Let me just run this so it's a little easier to go over that. You can see right here, we're going to be looking at 0, 1, 2 is age and estimated salary, so 2, 3. And that's what iLocation just means, that we're looking at the number versus a regular location. Regular location, you'd actually say age and estimated salary. And then column 4 is, did they make a purchase? They purchased something. So those are the 3 columns we're going to be looking at when we do this. And we've gone ahead and imported these and imported the data. So now our data set is all set with this information in it. And we'll need to go ahead and split the data up. So we need from the sklearn model selection, we can import train test split. This does a nice job. We can set the random state so it randomly picks the data. And we're just going to take 25% of it's going to go into the test, our X test and our Y test, and the 75% will go to X train and Y train. And that way, once we create our model, we can then have data to see just how accurate or how well it has performed with our prediction. The next step in pre-processing our data is to go ahead and do feature scaling. Now, a lot of this will start to look familiar. If you've done a number of the other modules and setup, you should start noticing that we bring in our data, we take a look at what we're working with, we go ahead and split it up into training and testing. In this case, we're going to go ahead and scale it. Scale it means we're putting it between a value of -1 and 1, or someplace in the middle ground there. This way, if you have any huge you don't have this huge setup. If we go back up to here where salary, salary is 20,000 versus age 35. Well, there's a good chance with a lot of the back-end math that 20,000 will skew the results, and the estimated salary will have a higher impact than the age, instead of balancing them out and letting the calculations weigh them properly. And finally, we get to actually create our naive Bayes model. And then we're going to go ahead and import the Gaussian naive Bayes. And the Gaussian is the most basic one. That's what we're looking at now. It turns out, though, if you go to the Simplilearn kit, they have a number of different ones you can pull in there. There's Bernoulli. I've never used that one. Categorical, complement, and here's our Gaussian. So there's a number of different options you can look at. Gaussian, when you come to the naive Bayes, is the most commonly used. So we're talking about the naive Bayes. That's usually what people are talking about when they're pulling this in. And one of the nice things about the Gaussian, if you go to their website, to sklearn, the naive Bayes Gaussian, there's a lot of cool features. One of them is you can do partial fit on here. That means if you have a huge amount of data, you don't have to process it all at once. You can batch it into the Gaussian NB model. And there's many other different things you can do with it as far as fitting the data and how you manipulate it. We're just doing the basics. So we're going to go ahead and create our classifier. We're going to equal the Gaussian NB. And then we're going to do a fit. We're going to fit our training data and our training solution. So X train, Y train. And we'll go ahead and run this. It's going to tell us that it ran the code right there. And now we have our trained classifier model. So the next step is we need to go ahead and run a prediction. We're going to do our Y predict equals the classifier.predict X test. So here we fit the data, and now we're going to go ahead and predict. And now we get to our confusion matrix. So from the sklearn metrics, you can import your confusion matrix. Just as saves you from doing all the simple math, it does it all for you. And then we'll go ahead and create our confusion metrics with the Y test and the Y predict. So we have our actual and we have our predicted value. And you can see from here, this is the chart we looked at. Here's predicted, so true positive, false negative, true negative. And if we go ahead and run this, there we have it, 65, 3, 7, 25. And in this particular prediction, we had 65 were predicted the truth as far as a purchase. They're going to make a purchase. And we guessed 3 wrong. And then we had 25 we predicted would not purchase, and 7 of them did. So there's our confusion matrix. At this point, if you were with your shareholders or a board meeting, you would start to hear some snoozing if they were looking at the numbers. And you say, hey, here's my confusion matrix. So let's go ahead and visualize the results. We're going to pull from the matplot library colors, import listed color map. And this is actually, my machine's going to throw an error because this is being, because of the way the setup is. I have a newer version on here than when they put together the demo. And we need our X set and our Y set, which is our X train and Y train. And then we'll create our X1, X2. And we'll put that into a grid, and we set our X set minimum stop and our X set max stop. And if you come all the way over here, we're going to step 0.01. This is going to give us a nice line, is what that's doing. And then we're going to plot the contour, plot the X limit, plot the Y limit, and put the scatter plot in there. Now let's go ahead and run this. To be honest, when I'm doing these graphs, there's so many different ways to do that. There's so many different ways to put this code together. To show you what we're doing, it's a lot easier to pull up the graph and then go back up and explain it. So the first thing we want to note here when we're looking at the data is this is the training set. And so we have those who didn't make a purchase. We've drawn a nice area for that. That's defined by the naive Bayes setup. And then we have those who did make a purchase, the green. And you can see that some of the green dots fall into the red area and some of the red dots fall into the green. So even our training set isn't going to be 100%. We couldn't do that. And so when we're looking at our different data coming down, we can kind of arrange our x1, x2, so we have a nice plot going on, and then we're going to create the contour. That's that nice line that's drawn down the middle on here with the red-green. That's what this is doing right here with the reshape. And notice that we had to do the dot t. If you remember from NumPy, if you did the NumPy module, you end up with pairs, x1, x2, x1, x2, next row, and so forth. You have to flip it so it's all one row. You have all your x1s and all your x2s. So this is what we're kind of looking for right here on this setup. And then the scatter plot is, of course, your scattered data across there. We're just going through all the points. That puts these nice little dots onto our setup on here. And we have our estimated salary and our age. And then, of course, the dots are, did they make a purchase or not? And just a quick note, this is kind of funny. You can see up here where it says X set, Y set equals X train, Y train, which seems kind of a little weird to do. This is because this was probably originally a definition. So it's its own module that could be called over and over again. And which is really a good way to do it, because the next thing we're going to want to do is do the exact same thing where we're going to visualize the test set results. That way we can see what happened with our test group, our 25%. And you can see down here we have the test set, and if you look at the two graphs next to each other, this one obviously has 75% of the data, so it's going to show a lot more. This is only 25% of the data. You can see that there's a number that are kind of on the edge as to whether they could guess by age and income they're going to make a purchase or not. But that said, it still is pretty clear. It's pretty good as far as how much the estimate is and how good it does. Now, graphs are really effective for showing people what's going on, but you also need to have the numbers. And so we're going to do from sklearn, we're going to import metrics, and then we're going to print our metrics classification report from the y-test and the y-predict. And you can see here we have precision. Precision of zeros is 90. There's our recall, 0.96. We have an F1 score and a support. And we have our precision, the recall on getting it right. And then we can do our accuracy, the macro average, and the weighted average. So you can see that it pulls in pretty good as far as how accurate it is. You could say it's going to be about 90% is going to guess correctly that they're not going to purchase. And we had an 89% chance that they are going to purchase. And then the other numbers as you get down have a little bit different meaning, but it's pretty straightforward on here. Here's our accuracy, and here's our micro average and the weighted average and everything else you might need. And if you forgot the exact definition of accuracy, it is the true positive, true negative over all of the different setups. Precision is your true positive over all positives, true and false. And recall is a true positive over true positive plus false negative. And we can just real quick flip back there so you can see those numbers on here. Here's our precision, here's our recall, and here's our accuracy on this.
Multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have y equals m1 times x1 plus m2 times x2
so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that. We're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import NumPy as NP. And then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The NumPy, which stands for NumberPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT and then Seaborn as SNS. Seaborn works with the matplot library. So you have to always import matplotlibary and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplotlibary inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplilearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/Simplilearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row, that's what the first colon is, comma, except for the last column. That's what the second part is, where we have a :-1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what pandas, one of the things pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the pandas. You could also open this up in an Excel and it would separate it since it is a comma-separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is pandas. As you can see, we imported the matplot library, .pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplot library inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any 2 of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in 2 steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the sklearn pre-processing, where we're going to import the label encoder and the one-hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. We have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the 3rd row. And in there we're going to take the label coder and we're going to fit and transform the x, also the third row. So we're going to take that third row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally we need to do a one hot encoder, which equals one hot encoder categorical features equals 3. And then we take the x and we go ahead and do that equal to one hot encoder fit transform x to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print x and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have x equals x colon comma 1 colon. All this is doing is removing that one extra column we put in there when we did our one hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now, whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise, we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or 2 so it all fits on one line. So from the sklearn module selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit, because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train, test, split, we take X and we take Y. We've already created those. X has the columns with the data in it, and Y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn .linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom and we were doing all this summization? And then we also looked at setting it up with the different lines, and then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case, we do x train and y train because we're using the training data, x being the data in and y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy x equals true fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a y_predict variable, and we're going to put in the x_test. And let's see what that looks like. Scroll up a little bit, paste that in here. Predicting the test set results. So here we have y_predict equals regressor.predict, x_test going in, and this gives us y_predict. Now because I'm in Jupyter Inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print y_predict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print y_predict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. And we can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m into the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works and understand how good it works. So, calculating the r² value, that's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the r² value. We're looking at the error. So, in the R2 score, we take our y_test versus our y_predict. Y_test is the actual values we're testing. That was the one that was given to us so we know are true. The y_predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if r² value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression.
Let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. And then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images we can display using matplotlib, some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix, the heat map, and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. Alright, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting. So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 93-94%, because the diagonals should have the maximum numbers, and the others other than diagonals, the cells other than the diagonals, should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0, and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and 1 has been predicted as number 8, and another one has been predicted as number 9. So these are 2 misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information, or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has, there are, I think, 37 plus 5, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7, and 2 of them have been predicted as number 8, and so on and so forth. Okay, alright, so with that, let's go into Jupyter Notebook and see how the code looks.
So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like NumPy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code, and so that it becomes easy to understand. So these are about 5 images, sample images, that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number, what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test, so that the training data set is used to train the system. So we pass this probably multiple times, and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of that entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x_train and y_train for the training data set. And what is x_train? These are the features, right, which is like the independent variable, and y_train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x_train, and since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2. So this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this. Right? So this is the label. So the same way, x_train, y_train is for the training data set, x_test, y_test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of these. So x_train, the shape is 1383 by 64, and y_train has 1383 because there is nothing like the second part is not required here. And then x_test shape, we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay. Then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function. And let me go ahead and execute that, so that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these 2 lines. So the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right, this is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this, in this case the data is not large, but by and large the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose we use the fit method. There is a method called fit which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method, and we pass this particular image, and we see that the shape is or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So this confusion underscore matrix method takes 2 parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set, and then out of that the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations. That will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So let me run this piece of code, and this is how the heat map looks. And as you can see here, the diagonals again are all the values are here, most of the values. So which means this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. Alright, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value, and also the predicted value. Both are 4. This is an image of 0. So the predicted value is also 0. Actual value is of course 0. Then this is the image of 9. So this has also been predicted correctly, 9, and actual value is 9. And this is the image of 1. And again, this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
Need for confusion matrices. Classification models have multiple output categories. Most error measures will tell us the total error in our model, but we cannot use it to find out individual instances of errors in our models. So you have your input coming in, you have your classifier, it measures the error and it says, oh, 53 of these are correct. But we don't know which 53% are correct. Is it 53% correct on guessing on the spam? Is it 23% guessing on spam and 27% guessing on what's not spam? This is where the confusion matrix comes in. So during the classification, we also have to overcome the limitations of accuracy. Accuracy can be misleading for classification problems. If there is a significant class imbalance, a model might predict the majority class for all cases and have a high accuracy score. And so you can see here we have our email coming in and there's 2 spams. The classifier comes in and goes, hey, it only catches one of those spams and it misclassifies one that's not spam. So our model predicted 8 out of 10 instances and will have an accuracy of 80%. But is it classifying correctly? A confusion matrix represents a table layout of the different outcomes of prediction and results of a classification problem and helps visualize its outcomes. And so you see here we have our simple chart, predicted and actual. The confusion matrix helps us identify the correct predictions of a model for different individual classes as well as the errors. So you'll see here that the values predicted by our classifier are along the rows. This is what we're going to guess it is, or our model is guessing what this is based on its training. So we've already trained the model to guess whether it's spam or not spam or whatever it is you're working on. And then the actual values of our data set are along the columns. So this is the actual value that's supposed to be. People who can speak English will be classified as positives. So, because they have remember 0 or 1. Do you speak English? Yes, no. And you could extend this that they might have, do you speak French? Do you speak whatever languages? And so you might have a whole lot of classifiers that you would look at each one of these. People who cannot speak English will be classified as negatives. So there'll be a 0. So, 0 ones. The number of times our actual positive values are equal to predicted positive values gives us true positive, TP. The number of times our actual negative values are equal to predictive negative values gives us true negative, TN. The number of times our model wrongly predicts negative values as positives gives us a false positive, FP. And you'll see when you're working with these a lot, memorizing that it's false positive, you can easily figure out what that is, and pretty soon you're just looking at the FP or the TP, depending on what you're working on. And the number of times our model wrongly predicts positive values as negatives gives us a false negative, FP. Now, I'm going to do a quick step out here. Let's say you're working in the medical and we're talking about cancer. Do you really want a bunch of false negatives? You want 0 under false negative. So when we look at this confusion matrix, if you have 5% false positives and 5% false negatives, it'd be much better to even have 20% false positives because they go in and test it, and 0 false negatives. The same might be true if you're working on, say, a car driving. Is this a safe place for the car to go? Well, you really don't want any false positives. Yes, this is safe right over the cliff. So again, when you're working on the project or whatever it is you're working on, this chart suddenly has huge value. We were talking about spam email. How many important emails, say from your banking overdraft charge coming in, that you want to be a true false negative? You don't want it to go in the spam folder. Likewise, you want to get as much of the spam out of there, but you don't want to miss anything really important. Confusion matrix metrics are performance measures which help us find the accuracy of our classifier. There are 4 main metrics: accuracy, precision, recall, and F1 score. The F1 score is the one I usually hear the most, and accuracy is usually what you put on your chart when you're sending in front of the shareholders. How accurate is it? People understand accuracy. F1 score is a little bit more on the math side, and so you got to be a little careful when you're quoting F1 scores in the when you're sitting there with all the shareholders, because a lot of them will just glaze over. So confusion matrix metrics are performance measures which help us find the accuracy of our classifier. There are 4 main metrics. Accuracy. The accuracy is used to find the portion of the correctly classified values. It tells us how often our classifier is right. It is the sum of all true values divided by the total values. And this makes sense. Again, it's one of those things. I don't want to, it depends on what you're looking for. Are you looking for not to miss any spam mails? Are you looking to drive down the road and not run anybody over? Precision is used to calculate the model's ability to classify positive values correctly. It answers the question, when the model predicts a positive value, how often is it right? It is the true positive divided by the total number of predicted positive values. Again, this one depends on what project you're working on, whether this is what you're going to be focusing on. So recall, it is used to calculate the model's ability to predict positive values. How often does the model actually predict the correct positive values? It is the true positives divided by the total number of actual positive values. And then your F1 score. It is the harmonic mean of recall and precision. It is useful when you need to take both precision and recall into account. Consider the following 2 confusion matrices, derived from 2 different classifiers. To figure out which one performs better, we can find the confusion matrix for both of them. And you can see we're back to, does it classify whether they can speak English or non-speaker? They don't know the English language. And so we put these 2 confusion matrices out here. We can go ahead and do the math behind that. We can look up the accuracy. That's the TPN plus TN over the TF plus TN plus FP plus FN. And so we get an accuracy of 0.8125. And we have a precision If you do the precision, which is your TP, truth positive, over TP plus FP, we get 0.891. And if we do the recall, we'll end up with the 0.825. That's your TP over TP plus FN. And then, of course, your F1 score, which is 2 times precision times recall over precision plus recall. And we get the 0.857. And if we do that with another model, let's say we had 2 different models and we're trying to see which one we want to use for whatever reason, we might go ahead and compute the same things. We have our accuracy, our precision, and our recall, and our F1 score. And as we're looking at this, we might look at the accuracy, because that's really what we're interested in, is how many people are we able to classify as being able to speak English. I really don't want to know if I really don't want to know if they're non-speakers. I'd rather miss 10 people speaking English instead of 15. And so you can see from these charts, we'd probably go with the first model because it does a better job guessing who speaks English and has a higher accuracy, because in this case, that is what we're looking for. So with that, we'll go ahead and pull up a demo so you can see what this looks like in the Python setup and in the actual coding. For this, we'll go into Anaconda Navigator. If you're not familiar with Anaconda, it's a really good tool to use as far as doing display and demos, and for quick development. As a data scientist, I just love the package. Now, if you're going to do something heavier lifting, there's some limitations with Anaconda and with the setup, but in general, you can do just about anything in here with your Python. And for this, we'll go with Jupyter Notebook. Jupyter Lab is the same as Jupyter Notebook. You'll see they now have integration with PyCharm if you work in PyCharm. Certainly, there's a lot of other integrations that Anaconda has. And we've opened up my Simplilearn files I work on and create a new file called Confusion Matrix Demo. And the first thing we want to note is the data we're working with. Here I've opened it up in a WordPad or Notepad or whatever. You can see it's got a row of headers, comma separated, and then all the data going down below. And then I save this in the same file so I don't have to remember what path I'm working on. Of course, if you have your data separated and you're working with a lot of data, you probably want to put it into a different folder or file depending on what you're doing. And the first thing we want to do is go ahead and import our tools. We're going to use the pandas. That's our data frame. If you haven't had a chance to work with the data frame, please review pandas data frame and go into Simplilearn. You can pull up the pandas data frame tutorial on there. And then we're going to use the scikit framework, which is all denoted as sklearn. And I can just pull this in. You can see here's the scikit-learn.org with the stable version that you can import into your Python. And from here, we're going to use the train test split for splitting our data. We're going to do some pre-processing. We're going to use the logistic regression model. That's our actual machine learning model we're using. And then what this particular setup is about is we're going to do the accuracy score, the confusion matrix, and the classifier report. So let me go ahead and run that and bring all that information in. And just like we opened the file, we need to go ahead and load our data in here. So we're going to go ahead and do our pandas read CSV. And then just because we're in Jupyter Notebook, we can just put data to read the data in here. A lot of times we'll actually, let me just do this. I prefer to do just the head of the data, or the top part. And you can see we have age, sex, I'm not sure what CP stands for, test BPS, cholesterol. So a lot of different measurements. If you were in this domain, you'd want to know what all these different measurements mean. I don't want to focus on that too much because when we're talking about data science, a lot of times you have no idea what the data means. If you've ever looked up the breast cancer measurement, it's just a bunch of measurements and numbers. Unless you're a doctor, you're going to have no idea what those measurements mean. But if it's your specialty in your domain, you better know them. So we're going to go ahead and create y, and we're going to set it equal to the target. So here's our target value here. And it's either 1 or 0. So we have a classifier. If you're dealing with 1, 0, true, false, what do you have? You have a classifier. And then our x is going to be everything except for the target. So we're going to go ahead and drop the target. Axes equals 1. Remember, that's columns versus the index or rows. Axes equals 0 would give you an error, but you would drop like row 2. And then we'll go ahead and just print that out so you can see what we're looking at. And here we have y data, x data, and you can see from the x data we have the x head, and we can go ahead and just do print the y head data and run that. So this is all loading the data that we've done so far. If there's a confusion in there, go back and rewind the tape and review it. And then we need to go ahead and split our data into our x train, x test, y train, y test. And then keep in mind you always want to split the data before we do the scalar. And the reason is that you want the scalar on the training data to be set on the training data or fit to it, but not on the test data. Think of this as being out in the field. It could actually alter your results. So it's always important to make sure whatever you do to the training data or whatever fit you're doing is always done on the training, not on the test. And then we want to go ahead and scale the data. Now, we are working with linear regression model. And I'll mention this here in a minute when we get to the actual model. So sometimes you don't need to scale it when you're working with linear regression models. It's not going to change your result as much as, say, a neural network where it has a huge impact. But we're going to go ahead and here's our x train, x test, y train, y test. We create our scalar. We go ahead and scale. The scale is going to fit the x train. And then we're going to go ahead and take our x train and transform it. And then we also need to take our x test and transform it based on the scale on here so that our x is now between that nice -1 to 1. And so this is all our pre-data setup. And hopefully all of that looks fairly familiar to you if you've done a number of our other classes and you're up to the setup on here. And then what we want to go ahead and do is create our model. And we're going to use a logistic regression model. And from the logistic regression model, we're going to go ahead and fit our x train and y train, and then we'll run our predicted value on here. And so let's go ahead and run that. And so now we actually have like our x test and our prediction. So if you remember from our matrix, we're looking for the actual versus the prediction and how those compare. And if I take us back up here, you're going to notice that we imported the accuracy score, the confusion matrix, and the classification report. And there's, of course, our logistic regression, the model we're using for this. And I did mention I was going to talk a little bit about scalar and the regression model. The scalar, on a lot of your regression models, your basic math standard regression models, and I'd have to look it up for the logistic regression model. When you're using a standard regression model, you don't need to scale the data. It's already just built in by the way the model works in most cases. But if you're in a neural network and there's a lot of other different setups, then you really want to take this and fit that on there. And so we can go in and do the accuracy. And this is, if you remember correctly, we were looking at the accuracy with the English speaking. So this is saying our accuracy as to whether this person is, I believe this is the heart data set. It's going to be accurate about 85% of the time as far as whether it's going to predict the person's going to have a heart condition, or the 1 as it comes up with the 0, 1 on there. Which would mean at this point that you have an 85% being correct on telling someone they're extremely high risk for a heart attack kind of thing. And so we want to go ahead and create our confusion matrix. And let me just do that. Of course, the software does everything for us. So we'll go ahead and run this. And you can see right here, here's our 25 correct predictions right here. And if you remember from our slide, I'll just bring this over so it's a nice visual. We have our true positive, false positive. So we had 25 which were true, that it said, hey, this person's going to be high risk at heart. And we had 4 that were still high risk that it said were false. So out of these 25 people, or out of these 29 people, and that makes sense because you have 0.85, out of 29 people, it was correct on 25 of them. And so here's our accuracy score. We were just looking at that. Our accuracy is your true positive and your true negative over all of them. So how true is it? And there was our accuracy coming up here, 0.85. And then we have our nice matrix generated from that. And you can see right here is a similar matrix we had going for from the slide. And this should start asking questions at this point. So if you're in a board meeting or you're working with this, you really want to start looking at this data here and saying, well, is this good enough? Is this number of people, and hopefully you'd have a much larger data set, is my confusion matrix showing for the true positive and false positive, is that acceptable for what we're doing? And of course, if you're going to put together whatever data you're putting out, you might want to separate the true negative, false positive, false negative, true positive. And you can simply do that by doing the confusion matrix. And then, of course, the ravel part lets you set that up. So you can just split that right up into a nice tuple. And the final thing we want to show you here in the coding on this part is the confusion matrix metrics. And so we can come in here and just use the matrix equals classification report, the y-test and the predict. And then we're going to take that classification report and go ahead and print that out. And you can see here it does a nice job giving you your accuracy, your micro average, your weighted average, you have your precision, your recall, your F1 score, and your support all in one window, so you can start looking at this data and saying, oh, okay, our precision's at 0.83, 0.87 for getting a positive, and 0.83 for the negative side for a 0. And we start talking about whether this is a valid information or not to use. And when we're looking at a heart attack prediction, we're only looking at one aspect. What's the chances of this person having a heart attack or not? You might have something where we went back to the languages. Maybe you also want to know whether they speak English or Hindi or French. And you can see right here that we can now take our confusion matrix and just expand it as big as we need to, depending on how many different classifiers we're working on.
Decision tree, important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with a gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like and how do we split the data. We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is a measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I, would be the percentage of that animal, times the log base 2 of the same, the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as a condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need is something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here. We have to make a couple changes as we go through this first part of the import. The first thing we bring in is numpy as np. That's very standard. When we're dealing with mathematics, especially with very complicated machine learning tools, you almost always see the NumPy come in for your numbers. It's called NumPy. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this and it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and there's this very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is. And very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 1, 2, 3, 4, 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balance data from the Panda read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance underscore data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own, so it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, and let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or open Office Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into 2 groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our X and Y. Where do X and Y come from? Well, X is going to be our data, and Y is going to be the answer or the target. You can look at it source and target. In this case, we're using X and Y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in X equals the balance of the data.values. The first brackets means that we're going to select all the lines in the database. So it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, we always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for Y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into 2 different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have x going in where we're going to train it, and we have to know the answer to train it with. And then we have x test where we're going to test that data. And we have to know in the end what the y was supposed to be. And that's where this train test split comes in that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So it'll have at least 3 splits, or have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it, let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what's it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created. And then you'll see .predict. And it's very common in the sklearn modules that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X test data in here. Now, if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredictEn to print it. I could just as easily have put the print and put brackets around yPredictEn to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our yPredict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since sklearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y test. That's the one we ran the predict on. And then we put in our yPredictEn. That's the answers we got. And we're just going to multiply that by 100, because this is just going to give us an answer as a decimal. And we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We might not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not. How does a random forest work as a whole? So to begin our random forest classifier, let's say we already have built 3 trees. And we're going to start with the first tree that looks like this. Just like we did in the example, this tree looks at the diameter. If it's greater than or equal to 3, it's true, otherwise it's false. So one side goes to the smaller diameter, one side goes to larger diameter. And if the color is orange, it's going to go to the right, true. We're using oranges now instead of lemons. And if it's red, it's going to go to the left, false. We build a second tree very similar, but it's split differently. Instead of the first one being split by diameter, this one, when they created it, if you look at that first bowl, it has a lot of red objects. So it says, is the color red? Because that's going to bring our entropy down the fastest. And so, of course, if it's true, it goes to the left. If it's false, it goes to the right. And then it looks at the shape, false or true, and so on and so on. And tree 3, is the diameter equal to 1? And it came up with this because there's a lot of cherries in this bowl. So that would be the biggest split on there is the diameter equal to 1? That's going to drop the entropy the quickest. And as you can see, it splits it into true. If it goes false, and they've added another category, does it grow in the summer? And if it's false, it goes off to the left. If it's true, it goes off to the right. Let's go ahead and bring these 3 trees so you can see them all in one image. So this would be 3 completely different trees categorizing a fruit. And let's take a fruit. Now let's try this. And this fruit, if you look at it, we've blackened it out. You can't see the color on it, so it's missing data. Remember, one of the things we talked about earlier is that a random forest works really good if you're missing data, if you're missing pieces. So this fruit has an image, but maybe the person had a black and white camera when they took the picture. And we're going to take a look at this, and it's going to have, they put the color in there, so ignore the color down there. But the diameter equals 3. We find out it grows in the summer equals yes, and the shape is a circle. And if you go to the right, you can look at what one of the decision trees did. This is the third one. Is the diameter greater than or equal to 3? Is the color orange? Well, it doesn't really know on this one, but if you look at the value, it'd say true, and it'd go to the right. Tree 2 classifies it as cherries. Is the color equal red? Is the shape a circle? True, it is a circle. So this would look at it and say, oh, that's a cherry. And then we go to the other classifier and it says, is the diameter equal 1? Well, that's false. Does it grow in the summer? True. So it goes down and looks at as oranges. So how does this random forest work? The first one says it's an orange. The second one said it was a cherry. And the third one says, it's an orange. And you can guess that if you have 2 oranges and one says it's a cherry, when you add that all together, the majority of the vote says orange. So the answer is, it's classified as an orange, even though we didn't know the color and we're missing data on it. I don't know about you, but I'm getting tired of fruit. So let's switch, and I did promise you we'd start looking at a case example and get into some Python coding. Today we're going to use the case, the iris flower analysis. Ooh, this is the exciting part as we roll up our sleeves and actually look at some Python coding. Before we start the Python coding, we need to go ahead and create a problem statement. Wonder what species of iris do these flowers belong to? Let's try to predict the species of the flowers using machine learning in Python. Let's see how it can be done. So here we begin to go ahead and implement our Python code. And you'll find that the first half of our implementation is all about organizing and exploring the data coming in. Let's go ahead and take this first step, which is loading the different modules into Python, and let's go ahead and put that in our favorite editor, whatever your favorite editor is. In this case, I'm going to be using the Anaconda Jupyter Notebook, which is one of my favorites. Certainly there's Notepad++ and Eclipse and dozens of others, or just even using the Python terminal window. Any of those will work just fine to go ahead and explore this Python coding. So here we go. Let's go ahead and flip over to our Jupyter Notebook. And I've already opened up a new page for Python 3 code, and I'm just going to paste this right in there. And let's take a look and see what we're bringing into our Python. The first thing we're going to do is from the sklearn.datasets, import load iris. Now this isn't the actual data, this is just the module that allows us to bring in the data, the load iris. And the iris is so popular, it's been around since 1936 when Ronald Fisher published a paper on it, and they're measuring the different parts of the flower, and based on those measurements predicting what kind of flower it is. And then if we're going to do a random forest classifier, we need to go ahead and import a random forest classifier from the sklearn module. So sklearn.ensemble, import random forest classifier. And then we want to bring in two more modules. And these are probably the most commonly used modules in Python and data science with any of the other modules that we bring in. And one is going to be pandas. We're going to import pandas as PD. PD is the common term used for pandas. And pandas is basically creates a data format for us where when you create a pandas data frame, it looks like an Excel spreadsheet. And you'll see that in a minute when we start digging deeper into the code. Panda is just wonderful because it plays nice with all the other modules in there. And then we have NumPy, which is our numbers Python. And the numbers Python allows us to do different mathematical sets on here. We'll see right off the bat, we're going to take our NP and we're going to go ahead and seed the randomness with it with 0. So np.random.seed is seeding that as 0. This code doesn't actually show anything. We're going to go ahead and run it because I need to make sure I have all those loaded. And then let's take a look at the next module on here. The next 6 slides, including this one, are all about exploring the data. Remember I told you half of this is about looking at the data and getting it all set. So let's go ahead and take this code right here, the script, and let's get that over into our Jupyter notebook. And here we go. We've gone ahead and run the imports. And I'm going to paste the code down here. And let's take a look and see what's going on. The first thing we're doing is we're actually loading the iris data. And if you remember up here, we loaded the module that tells it how to get the iris data. Now we're actually assigning that data to the variable iris. And then we're going to go ahead and use the df to define data frame. And that's going to equal PD. And if you remember, that's pandas as PD. So that's our pandas. And panda data frame. And then we're looking at iris data. And columns equals iris feature names. And we're going to do the df head. And let's run this so you can understand what's going on here. The first thing you want to notice is that our df has created what looks like an Excel spreadsheet. And in this Excel spreadsheet we have set the columns. So up on the top you can see the 4 different columns. And then we have the data, iris.data, down below. It's a little confusing without knowing where this data is coming from. So let's look at the bigger picture. And I'm going to go print. I'm just going to change this for a moment. And we're going to print all of iris and see what that looks like. So when I print all of iris, I get this long list of information. And you can scroll through here and see all the different titles on there. What's important to notice is that first off, there's a brackets at the beginning. So this is a Python dictionary. And in a Python dictionary, you'll have a key or a label. And this label pulls up whatever information comes after it. So feature names, which we actually used over here under columns, is equal to an array of sepal length, sepal width, petal width. These are the different names they have for the 4 different columns. And if you scroll down far enough, you'll also see data down here. Oh goodness, it came up right towards the top. And data is equal to the different data we're looking at. Now there's a lot of other things in here like target. We're going to be pulling that up in a minute. And there's also the names, the target names, which is further down. And we'll show you that also in a minute. Let's go ahead and set that back to the head. And this is one of the neat features of pandas and panda data frames is when you do df.head or the panda data frame.head, it'll print the first 5 lines of the data set in there, along with the headers if you have it. In this case, we have the column headers set to iris features. And in here, you'll see that we have 0, 1, 2, 3, 4. In Python, most arrays always start at 0. So when you look at the first 5, it's going to be 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So now we've got our iris data imported into a data frame. Let's take a look at the next piece of code in here. And so in this section here of the code, we're going to take a look at the target. And let's go ahead and get this into our notebook, this piece of code, so we can discuss it a little bit more in detail. So here we are in our Jupyter notebook. I'm going to put the code in here. And before I run it, I want to look at a couple things going on. So we have df species. And this is interesting because right here you'll see where I have df species in brackets, which is the key code for creating another column. And here we have iris.target. Now these are both in the pandas setup on here. So in pandas we can do either one. I could have just as easily done iris and then in brackets target, depending on what I'm working on. Both are acceptable. Let's go ahead and run this code and see how this changes. And what we've done is we've added the target from the iris data set as another column on the end. Now what species is, this is what we're trying to predict. So we have our data, which tells us the answer for all these different pieces. And then we've added a column with the answer. That way when we do our final setup, we'll have the ability to program our neural network to look for this different data and know what a setosa is, or a varicolor, which we'll see in just a minute, or virginica. Those are the three that are in there. And now we're going to add one more column. I know, we're organizing all this data over and over again. It's kind of fun. There's a lot of ways to organize it. What's nice about putting everything onto one data frame is I can then do a printout and it shows me exactly what I'm looking at. And I'll show you where that's different, where you can alter that and do it slightly differently. But let's go ahead and put this into our script up to date now. And here we go. We're going to put that down here. And we're going to run that. And let's talk a little bit about what we're doing. Now, we're exploring data, and one of the challenges is knowing how good your model is. Did your model work? And to do this, we need to split the data up. And we split it into two different parts. They usually call it the training and the testing. And so in here, we're going to go ahead and put that in our database so you can see it clearly. And we've set it df. And remember, you can put brackets. This is creating another column. Is train, so we're going to use part of it for training. And this equals np, remember that stands for numpy, .random.uniform. So we're generating a random number between 0 and 1. And we're going to do it for each of the rows. That's where the length df comes from. So each row gets a generated number. And if it's less than 0.75, it's true. And if it's greater than 0.75, it's false. This means we're going to take 75% of the data, roughly, because there's a randomness involved, and we're going to use that to train it. And then the other 25% we're going to hold off to the side and use that to test it later on. So let's flip back on over and see what the next step is. So now that we've labeled our database for which is training and which is testing, let's go ahead and sort that into two different variables, train and test. And let's take this code and let's bring it into our project. And here we go, let's paste it on down here. And before I run this, let's just take a quick look at what's going on here. Is we have up above, we created, remember there's our def.head, which prints the first 5 rows. And we've added a column is train at the end. And so we're going to take that, we're going to create two variables. We're going to create two new data frames. One's called train. One's called test, 75% in train, 25% in test. And then to sort that out, we're going to do that by doing df, our main original data frame with the iris data in it. And if df is train equals true, that's going to go in the train. And if df is train equals false, it goes in the test. And so when I run this, we're going to print out the number in each one. Let's see what that looks like. And you'll see that it puts 118 in the training module, and it puts 32 in the testing module, which lets us know that there was 150 lines of data in here. So if you went and looked at the original data, you could see that there's 150 lines. And that's roughly 75% in one and 25% for us to test our model on afterward. So let's jump back to our code and see where this goes. In the next two steps, we want to do one more thing with our data, and that's make it readable to humans. I don't know about you, but I hate looking at zeros and ones. So let's start with the features, and let's go ahead and take those and make those readable to humans. And let's put that in our code. Let's see, here we go, paste it in. And you'll see here we've done a couple very basic things. We know that the columns in our data frame, again this is a panda thing, the df columns, and we know the first 4 of them, 0, 1, 2, 3, that'd be the first 4, are going to be the features or the titles of those columns. And so when I run this, you'll see down here that it creates an index, SEPA length, SEPA width, petal length, and petal width. And this should be familiar because if you look up here, here's our column titles going across, and here's the first 4. One thing I want you to notice here is that when you're in a command line, whether it's Jupyter Notebook or you're running command line in the terminal window, if you just put the name of it, it'll print it out. This is the same as doing print features. And the shorthand is you just put features in here. If you're actually writing a code and saving the script and running it by remote, you really need to put the print in there. But for this, when I run it, you'll see it gives me the same thing. But for this, we want to go ahead and we'll just leave it as features because it doesn't really matter. And this is one of the fun things about Jupyter Notebooks is I'm just building the code as we go. And then we need to go ahead and create the labels for the other part. So let's take a look and see what that. For our final step in prepping our data, before we actually start running the training and the testing, is we're going to go ahead and convert the species on here into something the computer understands. So let's put this code into our script and see where that takes us. Alright, here we go. We've set y equal to pd.factorize train species of 0. So let's break this down just a little bit. We have our pandas right here, PD. Factorize. What is factorize doing? I'm going to come back to that in just a second. Let's look at what train species is and why we're looking at the group 0 on there. And let's go up here, and here is our species. Remember this that we created this whole column here for species? And then it has Setosa, 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 and if you scroll down enough, you'd also see Virginica and Varicolor. We need to convert that into something the computer understands, zeros and ones. So the trained species of 0, because this is in the format of an array of arrays, so you have to have the 0 on the end. And then species is just that column. Factorize goes in there and looks at the fact that there's only 3 of them. So when I run this, you'll see that y generates an array that's equal to, in this case it's the training set, and it's 0s, 1s, and 2s representing the 3 different kinds of flowers we have. So now we have something the computer understands, and we have a nice table that we can read and understand. And now, finally, we get to actually start doing the predicting. So here we go. We have 2 lines of code. Oh my goodness, that was a lot of work to get to 2 lines of code. But there is a lot in these 2 lines of code. So let's take a look and see what's going on here and put this into our full script that we're running. And let's paste this in here. And let's take a look and see what this is. We're creating a variable CLF, and we're going to set this equal to the random forest classifier. And we're passing 2 variables in here, and there's a lot of variables you can play with. As far as these 2 are concerned, they're very standard. In jobs, all that does is to prioritize it. Not something to really worry about. Usually when you're doing this on your own computer, you do in jobs equals 2. If you're working in a larger or big data and you need to prioritize it differently, this is what that number does, is it changes your priorities and how it's going to run across the system and things like that. And then the random state is just how it starts. 0 is fine for here. But let's go ahead and run this. We also have clf.fit train features, y. And before we run it, let's talk about this a little bit more. clf.fit. So we're training it. We are actually creating our random forest classifier right here. This is the code that does everything. And we're going to take our training set. Remember, we kept our test off to the side. And we're going to take our training set with the features, and then we're going to go ahead and put that in, and here's our target, the y. So the y is 0, 1, and 2 that we just created, and the features is the actual data going in that we put into the training set. And let's go ahead and run that. And this is kind of an interesting thing because it printed out the random forest classifier and everything around it. And so when you're running this in your terminal window or in a script like this, this automatically treats this just like when we were up here and I typed in y and it printed out y instead of print y. This does the same thing. It treats this as a variable and prints it out. But if you were actually running your code, that wouldn't be the case. And what is printed out is it shows us all the different variables we can change. And if we go down here, you can actually see in jobs equals 2. You can see the random state equals 0. Those are the two that we sent in there. You would really have to dig deep to find out all these different meanings of all these different settings on here. Some of them are self-explanatory if you kind of think about it a little bit, like max features is auto. So all the features that we're putting in there is just going to automatically take all 4 of them. Whatever we send it, it'll take. Some of them might have so many features because you're processing words. There might be like 1.4 million features in there because you're doing legal documents, and that's how many different words are in there. At that point, you probably want to limit the maximum features that you're going to process. And leaf nodes, that's the end nodes. Remember we had the fruit and we're talking about the leaf nodes. Like I said, there's a lot in this. We're looking at a lot of stuff here. So you might have, in this case, there's probably only 3 leaf nodes, maybe 4. You might have thousands of leaf nodes, at which point you do need to put a cap on that and say, okay, you can only go so far, and then we're going to use all of our resources on processing this. And that really is what most of these are about, is limiting the process and making sure we don't overwhelm a system. And there's some other settings in here. Again, we're not going to go over all of them. Warm start equals false. Warm start is if you're programming it one piece at a time externally. Since we're not going to have, we're not going to continually to train this particular learning tree. And again, like I said, there's a lot of things in here that you'll want to look up more detail from the sklearn. And if you're digging in deep and running a major project on here. For today, though, all we need to do is fit or train our features and our target Y. So now we have our training model. What's next? If we're going to create a model, we now need to test it. Remember, we set aside the test feature, test group, 25% of the data. So let's go ahead and take this code and let's put it into our script and see what that looks like. Okay, here we go. And we're going to run this, and it's going to come out with a bunch of 0s, 1s, and 2s, which represents the 3 types of flowers, the setosa, the virginica, and the versicolor. And what we're putting into our predict is the test features, and I always kind of like to know what it is I am looking at. So real quick, we're going to do test features. And remember, features is an array of sepal length, sepal width, petal length, petal width. So when we put it in this way, it actually loads all these different columns that we loaded into features. So if we did just features, let me just do features in here so you can see what features looks like. This is just playing with pandas data frames. You'll see that it's an index. So when you put an index in like this into test features, into test, it then takes those columns and creates a panda data frames from those columns. And in this case, we're going to go ahead and put those into our predict. So we're going to put each one of these lines of data, the 5.0, 3.4, 1.5, 0.2, and we're going to put those in and we're going to predict what our new forest classifier is going to come up with. And this is what it predicts. It predicts 0, 0, 0, 1, 2, 1, 1, 2, 2, 2. And again, this is the flower type, setosa, virginica, and versicolor. So now that we've taken our test features, let's explore that. Let's see exactly what that data means to us. So the first thing we can do with our predicts is we can actually generate a different prediction model. When I say different, we're going to view it differently. It's not that the data itself is different. So let's take this next piece of code and put it into our script. So we're pasting it in here, and you'll see that we're doing predict, and we've added underscore proba for probability. So there's our clf.predict probability. So we're running it just like we ran it up here, but this time with this we're going to get a slightly different result, and we're only going to look at the first 10. So you'll see down here, instead of looking at all of them, which was 27, you'll see right down here that this generates a much larger field on the probability. And let's take a look and see what that looks like and what that means. So when we do the predict underscore proba for probability, it generates 3 numbers. So we had 3 leaf nodes at the end. And if you remember from all the theory we did, this is the predictors. The first one is predicting a 1 for setosa. It predicts a 0 for virginica, and it predicts a 0 for versicolor, and so on and so on and so on. And let's, you know what, I'm going to change this just a little bit. Let's look at 10 to 20, just because we can. And we start to get in a little different of data, and you'll see right down here, it gets to this one, this line right here. And this line has 0, 0.5, 0.5. And so if we're going to vote, and we have 2 equal votes, it's going to go with the first one. So it says Setosa gets 0 votes, Virginica gets 0.5 votes, Versacolor gets 0.5 votes, but let's just go with the Virginica since these 2 are equal, and so on down the list. You can see how they vary on here. So now we've looked at both how to do a basic predict of the features, and we've looked at the predict probability. Let's see what's next on here. So now we want to go ahead and start mapping names for the plants. We want to attach names so that it makes a little more sense for us. And that's what we're going to do in these next 2 steps. We're going to start by setting up our predictions and mapping them to the names. So let's see what that looks like. And let's go ahead and paste that code in here and run it. And this goes along with the next piece of code. So we'll skip through this quickly and then come back to it a little bit. So here's iris.targetNames. And if you remember correctly, this was the names that we've been talking about this whole time, the Setosa, Virginica, Versacolor. And then we're going to go ahead and do the prediction again. We could have just set a variable equal to this instead of rerunning it each time. But we're going to go ahead and run it again, clf.predict test features. Remember that returns the 0s, the 1s, and the 2s. And then we're going to set that equal to predictions. So this time we're actually putting it in a variable. And when I run this, it distributes, it comes out as an array, and the array is Setosa, 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 Setosa. We're only looking at the first 5. We could actually let's do the first 25 just so we can see a little bit more on there. And you'll see that it starts mapping it to all the different flower types, the Versacolor and the Virginica in there. And let's see how this goes with the next one. So let's take a look at the top part of our species in here, and we'll take this code and put it in our script. And let's put that down here and paste it. There we go. And we'll go ahead and run it. And let's talk about both these sections of code here and how they go together. The first one is our predictions. And I went ahead and did predictions through 25. Let's just do 5. And so we have Setosa, 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 Setosa. That's what we're predicting from our test model. And then we come down here and we look at test species. I remember I could have just done test.species.head, and you'll see it says Setosa, 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 and they match. So the first one is what our forest is doing, and the second one is what the actual data is. Now, we need to combine these so that we can understand what that means. We need to know how good our forest is, how good it is at predicting the features. So that's where we come up to the next step, which is lots of fun. We're going to use a single line of code to combine our predictions and our actuals so we have a nice chart to look at. And let's go ahead and put that in our script in our Jupyter notebook here. Let's see, let's go ahead and paste that in, and then because I'm on the Jupyter notebook, I can do a control minus so you can see the whole line there. There we go, resize it. And let's take a look and see what's going on here. We're going to create in pandas, remember PD stands for pandas, and we're doing a crosstab. This function takes 2 sets of data and creates a chart out of them. So when I run it, you'll get a nice chart down here. And we have the predicted species. So across the top, you'll see the Setosa, Versacolor, Virginica, and the actual species, Setosa, Versacolor, Virginica. And so the way to read this chart, and let's go ahead and take a look on how to read this chart here. When you read this chart, you have Setosa where they meet, you have Versacolor where they meet, and you have Virginica where they meet. And they're meeting where the actual and the predicted agree. So this is the number of accurate predictions. So in this case, it equals 30. If you add 13 plus 5 plus 12, you get 30. And then we notice here where it says Virginica, but it was supposed to be Versacolor. This is inaccurate. So now we have two inaccurate predictions and 30 accurate predictions. So we'll say that the model accuracy is 93. That's just 30 divided by 32. And if we multiply it by 100, we can say that it is 93% accurate. So we have a 93% accuracy with our model. I did want to add one more quick thing in here on our scripting before we wrap it up. So let's flip back on over to my script. In here, we're going to take this line of code from up above. I don't know if you remember it, but predicts equals the iris.target_names. So we're going to map it to the names. And we're going to run the prediction. And we read it on test features. But we're not just testing it, we want to actually deploy it. So at this point, I would go ahead and change this. And this is an array of arrays. This is really important when you're running these to know that. So you need the double brackets, and I could actually create data. Maybe let's just do 2 flowers. So maybe I'm processing more data coming in, and we'll put 2 flowers in here. And then I actually want to see what the answer is. So let's go ahead and type in preds and print that out. And when I run this, you'll see that I've now predicted 2 flowers that maybe I measured in my front yard as versicolor and versicolor. Not surprising, since I put the same data in for each one. This would be the actual end product going out to be used on data that you don't know the answer for. So that's going to conclude our scripting part of this. Today we're going to cover the k nearest neighbors, a lot referred to as KNN. And KNN is really a fundamental place to start in the machine learning. It's a basis of a lot of other things, and just the logic behind it is easy to understand and incorporated in other forms of machine learning. So today, what's in it for you? Why do we need KNN? What is KNN? How do we choose the factor k? When do we use KNN? How does KNN algorithm work? And then we'll dive into my favorite part, the use case. Predict whether a person will have diabetes or not. That is a very common and popular used data set as far as testing out models and learning how to use the different models in machine learning. By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values, our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws, how sharp are their claws, and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those 2 characteristics. Now tell me if it is a cat or a dog. An odd question, usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats. It must be a cat. Sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or is not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we've gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put k equals 5. We'll talk about k in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose k? How do we know k equals 5? I mean, that was the value we put in there, so we're going to talk about it. How do we choose the factor k? KNN algorithm is based on feature similarity. Choosing the right value of k is a process called parameter tuning and is important for better accuracy. So at k equals 3, we can classify, we have a question mark in the middle, as either as a square or not. Is it a square, or is it, in this case, a triangle? And so if we set k equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put k equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the k changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of k? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right k? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other? And in terms of KNN, the number of k, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things, and it's going to pick those things, and you might get a skewed answer. And if your k is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing k, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your k value odd. That helps it select better. So in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the k value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise-free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where, I mean, you might get into a gig of data if it's really clean, doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work? Consider a data set having two variables, height in centimeters and weight in kilograms. And each point is classified as normal or underweight. So we can see right here we have two variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the two edges of a triangle. We're computing the third edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point, and we placed it there in red, and we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13. And distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer. And it's not a really complicated math, so you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the three closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal. Hence, as per KNN algorithm, the class of 57,170 should be normal. So a recap of KNN. Positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, you know if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine learning packages, but for a very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. At 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly you can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up here and click on Cell. Actually, we want to go ahead and first insert a cell below, and then I'm going to go back up to the top cell, and I'm going to change the cell type to Markdown. That means this is not going to run as Python. It's a Markdown language. So if I run this first one, it comes up in nice big letters, which is kind of nice. Remind us what we're working on. And by now, you should be familiar with doing all of our imports. We're going to import the pandas as PD, import numpy as NP. Pandas is the pandas data frame, and numpy is a number array. Very powerful tools to use in here. So we have our imports. So we've brought in our pandas, our numpy, our two general Python tools. And then you can see over here we have our train test split. By now you should be familiar with splitting the data. We want to split part of it for training our thing and then training our particular model. And then we want to go ahead and test the remaining data just to see how good it is. Pre-processing, a standard scalar preprocessor, so we don't have a bias of really large numbers. Remember in the data we had like number of pregnancies isn't going to get very large, where the amount of insulin they take can get up to 256. So 256 versus 6. That will skew results, so we want to go ahead and change that so that they're all uniform between -1 and 1. And then the actual tool. This is the K-neighbors classifier we're going to use. And finally, the last three are 3 tools to test, all about testing our model. How good is it? We just put down test on there. And we have our confusion matrix, our F1 score, and our accuracy. So we have our 2 general Python modules we're importing, and then we have our 6 modules specific from the sklearn setup.
And then we do need to go ahead and run this so that these are actually imported. There we go. And then move on to the next step. And so in this set, we're going to go ahead and load the database. We're going to use pandas. Remember, pandas is PD. And we'll take a look at the data in Python. We looked at it in a simple spreadsheet, but usually I like to also pull it up so that we can see what we're doing. So here's our data set equals pd.readcsv. That's a pandas command. And the diabetes folder I just put in the same folder where my IPython script is. If you put in a different folder, you'd need the full length on there. We can also do a quick length of the data set. That is a simple Python command, len for length. We might even, let's go ahead and print that. We'll go print. And if you do it on its own line, length.dataset in the Jupyter Notebook, it'll automatically print it. But when you're in most of your different setups, you want to do the print in front of there. And then we want to take a look at the actual dataset. And since we're in pandas, we can simply do dataset head. And again, let's go ahead and add the print in there. If you put a bunch of these in a row, you know, the dataset 1 head, dataset 2 head, it only prints out the last one. So I usually always like to keep the print statement in there. But because most projects only use one data frame, pandas data frame, doing it this way doesn't really matter. The other way works just fine. And you can see when we hit the run button, we have the 768 lines, which we knew, and we have our pregnancies. It's automatically given a label on the left. Remember, the head only shows the first 5 lines. So we have 0 through 4. And just a quick look at the data, you can see it matches what we looked at before. We have pregnancy, glucose, blood pressure, all the way to age, and then the outcome on the end. And we're going to do a couple things in this next step. We're going to create a list of columns where we can't have 0. There's no such thing as 0 skin thickness or 0 blood pressure, 0 glucose. Any of those you'd be dead. So not a really good factor if they have a 0 in there because they didn't have the data. And we'll take a look at that because we're going to start replacing that information with a couple of different things. And let's see what that looks like. So first we create a nice list. As you can see, we have the values we talked about: glucose, blood pressure, skin thickness. And this is a nice way when you're working with columns, is to list the columns you need to do some kind of transformation on. Very common thing to do. And then for this particular setup, we certainly could use there's some Panda tools that will do a lot of this, where we can replace the NA. But we're going to go ahead and do it as a dataset column equals dataset column.replace. This is still pandas. You can do a direct. There's also one that you look for your NaN. A lot of different options in here. But the NaN, numpy NaN is what that stands for, is none. It doesn't exist. So the first thing we're doing here is we're replacing the 0 with a numpy none. There's no data there. That's what that says. That's what this is saying right here. So put the 0 in, and we're going to replace zeros with no data. So if it's a 0, that means the person's, well, hopefully not dead. Hopefully they just didn't get the data. The next thing we want to do is we're going to create the mean, which is the integer from the data set from the column dot mean, where we skip NAs. We can do that. That is a pandas command there, the skip NA. So we're going to figure out the mean of that data set. And then we're going to take that data set column and we're going to replace all the NP-NaN with the means. Why did we do that? And we could have actually just taken this step and gone right down here and just replaced 0 and skip anything where, except you could actually, there's a way to skip zeros and then just replace all the zeros. But in this case, we want to go ahead and do it this way. So you can see that we're switching this to a non-existent value. Then we're going to create the mean. Well, this is the average person. So if we don't know what it is, if they did not get the data and the data is missing, one of the tricks is you replace it with the average. What is the most common data for that? This way, you can still use the rest of those values to do your computation, and it kind of just brings that particular value, or those missing values, out of the equation. Let's go ahead and take this, and we'll go ahead and run it. Doesn't actually do anything, so we're still preparing our data. If you wanted to see what that looks like, we don't have anything in the first few lines, so it's not going to show up, but we certainly could look at a row. Let's do that. Let's go into our data set. Let's print a data set, and let's pick, in this case, let's just do glucose. And if I run this, this is going to print all the different glucose levels going down, and we thankfully don't see anything in here that looks like missing data, at least on the ones it shows. You can see it skipped a bunch in the middle, because that's what it does. If you have too many lines in Jupyter Notebook, it'll skip a few and go on to the next in a data set. Let me go and remove this, and we'll just zero out that. And of course, before we do any processing, before proceeding any further, we need to split the data set into our train and testing data. That way we have something to train it with and something to test it on. And you're going to notice we did a little something here with the pandas database code. There we go, my drawing tool. We've added in this right here off the data set. And what this says is that the first one in pandas, this is from the PD pandas, it's going to say within the data set, we want to look at the I location, and it is all rows. That's what that says. So we're going to keep all the rows, but we're only looking at column 0 to 8. Remember, this is actually 0 to 7. It doesn't include the last one. And then we go down here to Y, which is our answer, and we want just the last one, just column 8. And you can do it this way with this particular notation. And then if you remember, we imported the train test split. That's part of the sklearn right there. And we simply put in our X and our Y. We're going to do random state equals 0. You don't have to necessarily seed it. That's a seed number. I think the default is 1 when you seed it. I'd have to look that up. And then the test size. Test size is 0.2. That simply means we're going to take 20% of the data and put it aside so that we can test it later. That's all that is. And again, we're going to run it. Not very exciting. So far we haven't had any printout other than to look at the data. But that is, a lot of this is prepping this data. Once you prep it, the actual lines of code are quick and easy. And we're almost there with the actual running of our KNN. We need to go ahead and scale the data. If you remember correctly, we're fitting the data in a standard scaler, which means instead of the data being from 5 to 303 in one column, and the next column is 1 to 6, we're going to set that all so that all the data is between -1 and 1. That's what that standard scaler does. Keeps it standardized. And we only want to fit the scaler with the training set, but we want to make sure the testing set is, the X test going in is also transformed, so it's processing it the same. So here we go with our standard scaler. We're going to call it sc_x for the scaler, and we're going to import the standard scaler into this variable, and then our x train equals sc_x dot fit transform. So we're creating the scaler on the x train variable, and then our x test, we're also going to transform it. So we've trained and transformed the x train, and then the x test isn't part of that training. It isn't part of training the transformer. It just gets transformed. That's all it does. And again, we're going to go ahead and run this. And if you look at this, we've now gone through these steps, all 3 of them. We've taken care of replacing our zeros for key columns that shouldn't be 0, and we replaced that with the means of those columns. That way that they fit right in with our data models. We've come down here and we split the data. So now we have our test data and our training data. And then we've taken and we've scaled the data. So all of our data going in. Now, no, we don't train the Y part, the Y train and Y test. That never has to be trained. It's only the data going in. That's what we want to train in there. Then define the model using k-neighbors classifier and fit the train data in the model. So we do all that data prep. And you can see down here we're only going to have a couple lines of code where we're actually building our model and training it. That's one of the cool things about Python and how far we've come. It's such an exciting time to be in machine learning because there's so many automated tools. Let's see, before we do this, let's do a quick length of, and let's do Y. Let's just do length of Y. And we get 768. And if we import math, we do math dot square root. Let's do Y train. There we go. It's actually supposed to be X train. Before we do this, let's go ahead and do import math and do math square root length of Y test. And when I run that, we get 12.409. I wanted to show you where this number comes from we're about to use. 12 is an even number, so if you're ever voting on things, remember the neighbors all vote, don't want to have an even number of neighbors voting, so we want to do something odd. And let's just take one away and we'll make it 11. Let me delete this out of here. And that's one of the reasons I love Jupyter Notebook, because you can flip around and do all kinds of things on the fly. So we'll go ahead and put in our classifier. We're creating our classifier now, and it's going to be the k-neighbors classifier. In neighbors equal 11. Remember we did 12 minus 1 for 11, so we have an odd number of neighbors. P equals 2, because we're looking for are they diabetic or not, and we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of measure this, but the Euclidean is the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll
jump into the F1 score, and finally accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, Y test, Y predict. So those are the two values we're going to put in there. And let me go ahead and run that and print it out. And the way you interpret this is you have the Y predicted, which would be your title up here. We could do, let's just do PRED, predicted across the top, and actual going down. Actual. It's always hard to write in here, actual. That means that this column here down the middle, that's the important column, and it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like three different, if you're looking at this across three different variables instead of just two, you'd end up with the third row down here and the column going down the middle. So in the first case we have the and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an sklearn and running the KNN, the K nearest neighbor on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and we can pretty much round that off and just say we have an accuracy of 80%. Tells us it is a pretty fair fit in the model. So far so clear, but a question should be coming up. We have our sample data set, but instead of looking like this, what if it looked like this, where we have two sets of data, but one of them occurs in the middle of another set? You can see here where we have the blue and the yellow, and then blue again on the other side of our data line. In this data set, we can't use a hyperplane. So when you see data like this, it's necessary to move away from a 1D view of the data to a two-dimensional view of the data. And for the transformation, we use what's called a kernel function. The kernel function will take the 1D input and transfer it to a two-dimensional output. As you can see in this picture here, the 1D when transferred to a two-dimensional makes it very easy to draw a line between the two data sets. What if we make it even more complicated? How do we perform an SVM for this type of data set? Here you can see we have a two-dimensional data set where the data is in the middle surrounded by the green data on the outside. In this case, we're going to segregate the two classes. We have our sample data set, and if you draw a line through, it's obviously not an optimal hyperplane in there. So to do that, we need to transfer the 2D to a 3D array. And when you translate it into a three-dimensional array using the kernel, you can see where you can place a hyperplane right through it and easily split the data. Before we start looking at a programming example and dive into the script, let's look at the advantage of the support vector machine. We'll start with high dimensional input space, or sometimes referred to as the curse of dimensionality. We looked at earlier 1 dimension, 2 dimension, 3 dimension. When you get to 1,000 dimensions, a lot of problems start occurring with most algorithms that have to be adjusted for. The SVM automatically does that in high dimensional space. One high dimensional space that we work on is sparse document vectors. This is where we tokenize the words in documents so we can run our machine learning algorithms over them. I've seen ones get as high as 2.4 million different tokens. That's a lot of vectors to look at. And finally, we have regularization parameter. The regularization parameter, or lambda, is a parameter that helps figure out whether we're going to have a bias or overfitting of the data. Whether it's going to be overfitted to a very specific instance or it's going to be biased to a high or low value. With the SVM, it naturally avoids the overfitting and bias problems that we see in many other algorithms. These three advantages of the support vector machine make it a very powerful tool to add to your repertoire of machine learning tools. Now, we did promise you a use case study where we're actually going to dive into some Python programming. And so we're going to go into a problem statement and start off with the zoo. So in the zoo example, we have family members going to the zoo and we have the young child going, "Dad, is that a group of crocodiles or alligators?" Well, that's hard to differentiate. And zoos are a great place to start looking at science and understanding how things work, especially as a young child. And so we can see the parents sitting here thinking, well, what is the difference between a crocodile and an alligator? Well, one, crocodiles are larger in size, alligators are smaller in size. Snout width, the crocodiles have a narrow snout and alligators have a wider snout. And of course, in the modern day and age, the father's sitting here thinking, how can I turn this into a lesson for my son? And he goes, let a support vector machine segregate the two groups. I don't know if my dad ever told me that, but that would be funny. Now, in this example, we're not going to use actual measurements and data. We're just using that for imagery. And that's very common in a lot of machine learning algorithms and setting them up. But let's roll up our sleeves, and we'll talk about that more in just a moment as we break into our Python script. So here we arrive in our actual coding. And I'm going to move this into a Python editor in just a moment. But let's talk a little bit about what we're going to cover. First, we're going to cover in the code the setup, how to actually create our SVM. And you're going to find that there's only 2 lines of code that actually create it, and the rest of it is done so quick and fast that it's all here on the first page. And we'll show you what that looks like as far as our data, because we're going to create some data. I talked about creating data just a minute ago. And so we'll get into the creating data here, and you'll see this nice correction of our 2 blobs, and we'll go through that in just a second. And then the second part is we're going to take this and we're going to bump it up a notch. We're going to show you what it looks like behind the scenes. But let's start with actually creating our setup. I like to use the Anaconda Jupyter Notebook because it's very easy to use, but you can use any of your favorite Python editors or setups and go in there. But let's go ahead and switch over there and see what that looks like. So here we are in the Anaconda Python Notebook, or Anaconda Jupyter Notebook with Python. We're using Python 3. I believe this is 3.5, but it should be work in any of your 3x versions. And you'd have to look at the sklearn and make sure if you're using a 2x version or an earlier version. Now let's go ahead and put our code in there. And one of the things I like about the Jupyter Notebook is I can go up to View, and I'm going to go ahead and toggle the line numbers on to make it a little bit easier to talk about. And we can even increase the size because this is edited in this case I'm using Google Chrome Explorer, and that's how it opens up for the editor. Although like I said, any editor will work. Now the first step is going to be our imports. And we're going to import 4 different parts. The first 2 I want you to look at are line 1 and line 2 are numpy as np and matplotlibary.pyplot as plt. Now, these are very standardized imports when you're doing work. The first one is the numbers Python. We need that because part of the platform we're using uses that for the numpy array. And I'll talk about that in a minute so you can understand why we want to use a numpy array versus the standard Python array. And normally it's pretty standard setup to use np for numpy. The matplot library is how we're going to view our data. So this has, you do need the NP for the sklearn module, but the matplot library is purely for our use for visualization. And so you really don't need that for the SVM, but we're going to put it there so you have a nice visual aid and we can show you what it looks like. That's really important at the end when you finish everything, so you have a nice display for everybody to look at. And then finally, I'm going to jump one ahead to line number 4. That's the sklearn.datasets.samples generator import make blobs. And I told you that we were going to make up data. And this is a tool that's in the sklearn to make up data. I personally don't want to go to the zoo, get in trouble for jumping over the fence, and probably get eaten by the crocodiles or alligators as I work on measuring their snouts and width and length. Instead, we're just going to make up some data. And that's what that make blobs is. It's a wonderful tool if you're ready to test your setup and you're not sure about what data you're going to put in there. You can create this blob and it makes it real easy to use. And finally, we have our actual SVM, the sklearn import SVM on line 3. So that covers all our imports. We're going to create, remember I used the make blobs to create data, and we're going to create a capital X and a lowercase y equals make blobs in samples equals 40. So we're going to make 40 lines of data. It's going to have 2 centers with a random state equals 20. So each group's going to have 20 different pieces of data in it. And the way that looks is that we'll have under X an XY plane. So I'll have 2 numbers under X, and Y will be 0 or 1. That's the 2 different centers. So we have yes or no, in this case alligator or crocodile. That's what that represents. And then I told you that the actual sklearn or the SVM is in 2 lines of code. And we see it right here with CLF equals svm.svc kernel equals linear, and I set C equal to 1. Although in this example, since we are not regularizing the data, because we want it to be very clear and easy to see, I went ahead, you can set it to 1,000 a lot of times when you're not doing that. But for this thing, linear, because it's a very simple linear example, we only have the 2 dimensions, and it'll be a nice linear hyperplane. Will be a nice linear line instead of a full plane. So we're not dealing with a huge amount of data. And then all we have to do is do clf.fit x, y. And that's it. CLF has been created, and then we're going to go ahead and display it. And I'm going to talk about this display here in just a second, but let me go ahead and run this code. And this is what we've done, is we've created 2 blobs. You'll see the blue on the side and then kind of an orangish on the other side. That's our 2 sets of data. They represent, one represents crocodiles and one represents alligators. And then we have our measurements. In this case we have like the width and length of the snout. And I did say I was going to come up here and talk just a little bit about our plot. And you'll see PLT, that's what we imported. We're going to do a scatter plot. That means we're just putting dots on there. And then look at this notation. I have the capital X, and then in brackets I have a colon comma 0. That's from NumPy. If you did that in a regular array, you'll get an error in a Python array. You have to have that in a NumPy array. It turns out that our make blobs returns a NumPy array. And this notation is great because what it means is the first part is the colon. It means we're going to do all the rows. That's all the data in our blob we created under capital X. And then the second part has a comma 0. We're only going to take the first value. And then if you notice, we do the same thing, but we're going to take the second value. Remember, we always start with 0 and then 1. So we have column 0 and column 1. And you can look at this as our XY plots. The first one is the X plot, and the second one is the Y plot. So the first one is on the bottom, 0, 2, 4, 6, 8, and 10. And then the second one, X of the 1, is the 4, 5, 6, 7, 8, 9, 10 going up the left-hand side. S equals 30 is just the size of the dot, so we can see them instead of real tiny dots. And then CMap equals plt.cm.paired. And you'll also see the C equals Y. That's the color. We're using 2 colors, 0, 1, and that's why we get the nice blue and the 2 different colors for the alligator and the crocodile. Now you can see here that we did this, the actual fit was done in 2 lines of code. A lot of times there'll be a third line where we regularize the data. We set it between like -1 and 1, and we reshape it. But for this, it's not necessary, and it's also kind of nice because you can actually see what's going on. And then if we wanted to actually run a prediction. Let's take a look and see what that looks like. And to predict some new data, and we'll show this again as we get towards the end of digging in deep, you can simply assign your new data. In this case, I am giving it a width and length 3, 4 and a width and length 5, 6. And note that I put the data as a set of brackets, and then I have the brackets inside. And the reason I do that is because when we're looking at data, it's designed to process a large amount of data coming in. We don't want to just process 1 line at a time. And so in this case, I'm processing 2 lines. And then I'm just going to print, and you'll see clf.predict new data. So the clf and the .predict part is going to give us an answer, and let's see what that looks like. And you'll see 0, 1. So predicted the first one, the 3, 4, is going to be on the one side, and the 5, 6 is going to be on the other side. So one came out as an alligator, and one came out as a crocodile. Now that's a pretty short explanation for the setup, but really we want to dig in and see what's going on behind the scenes. And let's see what that looks like. So the next step is to dig in deep and find out what's going on behind the scenes. And also put that in a nice pretty graph. We're going to spend more work on this than we did actually generating the original model. And you'll see here that we go through a few steps, and I'll move this over to our editor in just a second. We come in, we create our original data. It's exactly identical to the first part, and I'll explain why we redid that and show you how not to redo that. And then we're going to go in there and add in those lines. We're going to see what those lines look like and how to set those up. And finally, we're going to plot all that on here and show it, and you'll get a nice graph with what we saw earlier when we were going through the theory behind this, where it shows the support vectors and the hyperplane. And those are done where you can see the support vectors as the dashed lines and the solid line, which is the hyperplane. Let's get that into our Jupyter notebook. Before I scroll down to a new line, I want you to notice line 13. It has plot show. And we're going to talk about that here in just a second, but let's scroll down to a new line down here, and I'm going to paste that code in. And you'll see that the plot show has moved down below. Let's scroll up a little bit. And if you look at the top here of our new section, 1, 2, 3, and 4 is the same code we had before. And let's go back up here and take a look at that. We're going to fit the values on our SVM, and then we're going to plot scatter it, and then we're going to do a plot show. So you should be asking, why are we redoing the same code? Well, when you do the plot show, that blanks out what's in the plot. So once I've done this plot show, I have to reload that data. Now we could do this simply by removing it up here, rerunning it, and then coming down here, and then we wouldn't have to rerun these first 4 lines of code. Now in this, it doesn't matter too much, and you'll see the plot show is down here and then removed right there on line 5. I'll go ahead and just delete that out of there because we don't want to blank out our screen. We want to move on to the next setup. So we can go ahead and just skip the first 4 lines because we did that before. And let's take a look at the AX equals PLT.GCA. Now right now, we're actually spending a lot of time just graphing. That's all we're doing here. Okay, so this is how we display a nice graph with our results and our data. AX is very standard used variable when you're talking about PLT, and it's just setting it to that axis, the last axis in the PLT. It can get very confusing if you're working with many different layers of data on the same graph, and this makes it very easy to reference the AX. So this reference is looking at the PLT that we created and we already mapped out our 2 blobs on. And then we want to know the limits. So we want to know how big the graph is. We can find out the x limit and the y limit simply with the get x limit and get y limit commands, which is part of our matplot library. And then we're going to create a grid. And you'll see down here we've set the variable xx equal to np.linespace, x limit 0, x limit 1, 30. And we've done the same thing for the y space. And then we're going to go in here and we create a mesh grid. And this is a numpy command. So we're back to our numbers Python. Let's go through what these numpy commands mean with the line space and the mesh grid. We've taken xx, small s xx equals np line space, and we have our x limit 0 and our x limit 1, and we're going to create 30 points on it. And we're going to do the same thing for the y-axis. Now, this has nothing to do with our evaluation. It's all we're doing is we're creating a grid of data. And so we're creating a set of points between 0 and the x limit. We're creating 30 points, and the same thing with the y. And then the mesh grid loops those all together, so it forms a nice grid. So if we were going to do this, say, between the limit 0 and 10 and do 10 points, we would have a 0, 0, 1, 1, 0, 1, 0, 2, 0, 3, 0, 4 to 10, and so on. You can just imagine a point at each corner of one of those boxes. And the mesh grid combines them all, so we take the YY and the XX we created and creates the full grid. And we've set that grid into the YY coordinates and the XX coordinates. Now remember, when we're working with NumPy and Python, we like to separate those. We like to have, instead of it being x comma 1, x comma y, and then x2 comma y2, and in the next set of data it would be a column of x's and a column of y's. And that's what we have here, is we have a column of y's, and we put it as a capital YY, and a column of x's, capital XX, with all those different points being listed. And finally we get down to the NumPy VStack. Just as we created those in the mesh grid, we're now going to put them all into one array, XY array. Now that we've created the stack of data points, we're going to do something interesting here. We're going to create a value z, and the z equals the CLF. That's our support vector machine we created, and we've already trained. And we have a dot decision function, and we're going to put the XY in there. So here we have all this data. We're going to put that XY in there, that data, and we're going to reshape it. And you'll see that we have the XX.shape in here. This literally takes the XX, resets it up connected to the Y, and the Z value lets us know whether it is the left-hand side. It's going to generate 3 different values, the Z value does. And it'll tell us whether that data is a support vector to the left, the hyperplane in the middle, or the support vector to the right. So it generates 3 different values for each of those points. And those points have been reshaped so that they're right on a line, on those 3 different lines. So we've set all of our data up. We've labeled it to 3 different areas, and we've reshaped it, and we've just taken 30 points in each direction. If you do the math, you have 30 times 30, so that's 900 points of data, and we separated it between the 3 lines and reshaped it to fit those 3 lines. We can then go back to our matplot library, where we've created the AX, and we're going to create a contour. And you'll see here where we have contour, capital XX, capital YY. These have been reshaped to fit those lines. Z is the labels. So now we have the 3 different points with the labels in there, and we can set the colors equals K. And I told you we had 3 different labels, but we have 3 levels of data. The alpha is just makes it kind of see-through, so it's only 0.5 of the value in there. So when we graph it, the data will show up from behind it, wherever the lines go. And finally, the line styles. This is where we set the 2 support vectors to be dash lines, and then a single one is just a straight line. That's what all of that setup does. And then finally, we take our ax.scatter. We're going to go ahead and plot the support vectors, but we've programmed it in there so that they look nice, like the dash line and the dash line on that grid. And you can see here, when we do the CLF dot support vectors, we are looking at column 0 and column 1. And then again, we have the S equals 100, so we're going to make them larger. And the line width equals 1, face colors equals none. Let's take a look and see what that looks like when we show it. And you can see when we get down to our end result, it creates a really nice graph. We have our 2 support vectors in dash lines, and they have the near data. So you can see those 2 points, or in this case the 4 points, where those lines nicely cleave the data. And then you have your hyperplane down the middle, which is as far from the 2 different points as possible, creating the maximum distance. So you can see that we have our nice output for the size of the body and the width of the snout, and we've easily separated the 2 groups of crocodile and alligator. Congratulations! You've done it. We've made it. Of course, these are pretend data for our crocodiles and alligators, but this hands-on example will help you to encounter any support vector machine projects in the future. And you can see how easy they are to set up and look at in depth.
Regularization in machine learning. So our agenda on this one is fitting the data, understanding linear regression, bias and variance, what is overfitting, what is underfitting, and those are like the biggest things right now in data science, is overfitting and underfitting. What does that mean? And what is regularization? And then we'll do a quick hands-on demo to take a look at this. So fitting the data. Let's start with fitting the data. And we talk about what is data fitting. It's a process of plotting a series of data points and drawing the best fit line to understand the relationship between the variables. And this is what we called data fitting. And you can see here we have a couple of lines we've drawn on this graph. We're going to go in a little deeper on there. So we might have, in this case, just a 2 dimensions. We have an efficiency of the car, and we have the distance traveled in 1,000 kilometers. And so what is data fitting? Well, it's a linear relationship. And a linear relationship, very specifically, linear means line. The line used to represent the relationship is a straight line that passes through the data points, and the variables have a linear relationship. Linear regression. So let's start with how linear regression works. A linear regression finds the line that best fits the data point and gives a relationship between the 2 variables. And so you can see here we have the efficiency of the car versus the distance traveled, and you can see this nice straight line drawn through there. And when you talk about multiple variables, all you're doing is putting this, instead of a line, it now becomes a plane. It gets a little more complicated with multiple variables, but they all come down to this linear kind of drawing a line through your data and finding what fits the data the best. And so we can consider an example. Let's say that we want to find the relationship between the temperature outside versus the sales of ice cream. And so we start looking at that. We're looking at how many ice cream cones we're selling, or how much money we sold in ice cream, and we're looking at how warm it is outside, which would hopefully draw a lot of people into the ice cream store. And suppose we have 2 lines. We're going to draw L1 and L2, and we're going to kind of guess which one we think is the best fit, and which claim to describe the relationship between the variables. And so first we find the square of the distance between the line L1 and each data point and add them all and find the mean distance. And I want you to think about that when we square something. If it's a negative or positive number, it no longer matters, because a minus 2 squared is 4, 2 squared is 4. So we're removing what side of the line it's on, and we're just looking for the error. In this case, the mean distance of each of the little dotted lines you see here. This way of calculating the square of the distance, adding them, and then taking the mean is called mean square error, or loss function. And we talk about loss, how far off are we? That's what we're really talking about. What did we miss? And we have a positive distance and a negative distance. And of course, when we square it, it just becomes a positive error. And so we take the mean square error, and a lot of times you'll see it referred to as MSE. If I look in a code and I'm going through my Python code and I see MSE, I know that's a mean squared error. And we take all the dotted lines and we calculate this error and we add them all together, and then we average it or find the means. And in this case, they ran a demo on this, and it was 1127.27 for our L1 line. Now we find the loss function for line L2 in a similar fashion, and we get the mean square error to be 6,397. And it's computed the same way. So maybe you put this line just way outside the data range, and this is the error you get. By analyzing our results, we find that the loss function, or the mean square error, is less for L1 than L2. Hence, L1 is the best fit line. This process describes a lot of machine learning processes. We're going to keep guessing and get as close as we can to find the right answer. We have to have some way to calculate this and figure out which one's the best, and the mean square error is one of the better fits for doing this and most commonly used. We really want to talk about bias and variance. Very important terms to know in machine learning and with linear regression. So bias. Bias occurs when an algorithm has limited flexibility to learn from data. Variance defines the algorithm's sensitivity to specific sets of data. Let's start with bias and variance. You can see here we have the two different setups. Bias, you can think, is very generalized, where variance is very specific. And so when we talk about bias, such models pay very little attention to the training data and oversimplify the model. Therefore, the validation error or prediction error and training error follow similar trends. And with bias, if you oversimplify it so much, you're going to miss your local, if you have like a really good fit, you're going to miss it. You're going to just kind of guess what the average is, and that's what your answer is going to be. With variance, a model with a high variance pays a lot of attention to training data and does not generalize. Therefore, the validation error or prediction error are far apart from each other. Such models always lead to a high error on training and test data, as a bias does. Where a variance, such models usually perform very well on training data but have high error rates on test data. And I want you to think about this. When we're talking about a bias, the error is going to be high both when you're training it and you're testing it. Why? Because we're just kind of getting an average. We're not really fitting it close. With variance, we're fitting it so close that the test data does really good. It's going to nail it every time. If you're doing categorical testing, that's a car, that's a truck, that's a bicycle. But with variance, suddenly a truck has to have certain features, and it might have to be red because you had so many red pictures. So if it's an 18-wheeler, it has to be red. If it's blue, then it has to be a bicycle. That's the kind of variance we're talking about, where it picks up on something and it cannot get the right answer unless it gets a very specific data. And we see that so that as you're testing it in your models and you programmed it, you got to look for how I trained it, what is coming out, and if it's not looking good on either bias or if it's not looking good on the training or on the test data, then you're biasing your data. If it really looks good on the training data, then that's going to be your variance. You've overfitted the data. And those are very important things to know when you are building your models in regression of any kind or any kind of setup for predicting. So in dart games, if all the data fall on a particular pointer, this can be considered as a biased throw, and the player aims for the particular score. For variance, if all the darts fall on different pointers and no two darts fall on the same pointer, then this can be considered as a varied throw, and the player aims for various scores. Again, the bias sums everything up in one point, kind of averages it together, where the variance really looks for the individual predictions coming out. So let's go ahead and talk about overfitting. When we talk about overfitting, it's a scenario where the machine learning model tries to learn from the details along with the noise, and the data tries to fit each data point on the curve. You can see that if you plug in your coordinates, you're just going to get the whatever is fitted every point on the data stream. There's no average. There's no 2 points that might have the, y might have two different answers, because if the wind blows a certain way, and your efficiency of your car, maybe you have a headwind, so your car might alter how efficient it is as it goes, and so there's going to be this variance on here, and this says no, you can't have any variance. It's going to be exactly this. So it can't be you can't be the same speed or the same car and have a slightly different efficiency. So as the model has very less flexibility, it fails to predict new data points, and thus the model rejects every new data point during the prediction. So you'll get like a really high error on here. And so reasons for overfitting. Data used for training is not cleaned and contains noise, garbage values in it. You can spend so much time cleaning your data, and it's so important. It's so important that if you have some kind of something wrong with the data coming in, it needs to be addressed. Whether it's the source of the data, maybe they use in medical different measuring tools, so you now have to adjust for data that came in from hospital A versus hospital B, or even off of machine A and machine B that's testing something, and those numbers are coming in wrong. The model has a high variance. Again, wind is a good example. I was talking about that with the car. You may have 100 tests, but because the wind's blowing, it's all over the place. Size of training data used is not enough, so a small amount of data is going to also cause this problem. You only have a few points and you try to plot everything. The model is too complex. This comes up a lot. We put too many pieces together, and how they interact can't even be tracked. And so you have to go back, break it up, and find out actually what correlates and what doesn't. So what is underfitting? A scenario where machine learning models can neither learn the relationship between the data points nor predict or classify a new data point. And you can see here we have our efficiency of our car and our line drawn, and it's just going to be way off for both the training and the predicting data. As the model doesn't fully learn the patterns, it accepts every new data point during the prediction. So instead of looking for a general pattern, we just kind of accept everything. Data used for training is not cleaned and contains noise, garbage, and values. Again, underfitting and overfitting, same issue. You got to clean your data. The model has a high bias. We've seen this in all kinds of things, from the most common is the driving cars to facial identification or whatever it is. The model itself, when they build it, might have a bias towards one thing. And this would be an underfitted model, would have that bias because it's averaged it out. So if you have 5 people from India and 10 people from Africa and 20 people from the US, you've created a bias because it's looking at the 20 people, and you only have a small amount of data to work with. Size of training data used is not enough. That goes with the size I was just talking about. So we have a model with a high bias. We have size of training data used is not enough. The model is too simple. Again, this is one straight line through all the data when it has a slight shift to it for other reasons. So what is a good fit? A linear curve that best fits the data is neither overfitting or underfitting models, but is just right. And of course we have the nice examples here where we have overfitting, lines going up and down, every point's trying to be included. Underfitting, the line really is off from where the data is, and then a good fit is got to get rid of that, minimize that error coming through. Regularization is taking the guesswork out. You're looking at this graph and you're going, oh, which one is that really overfit or is that underfit? That's pretty hard to tell. So we talk about regularization. Regularization techniques are used to calibrate the linear regression models and to minimize the adjusted loss function and prevent overfitting or underfitting. So what that means, in this case, we're going to go ahead and take a look at a couple different things. We're going to look at regularization, which will start with a linear model. We'll look at the ridge regularization and the lasso regularization. And these models are just like we did the MLP, the multi-layered positron in the sklearn module. You could bring in the ridge module and you can bring in the lasso module. So when we talk about ridge regression, it modifies the overfitted or underfitted models by adding the penalty equivalent to the sum of the squares of the magnitude of the coefficients. And so we have a cost function equals loss equals lambda times the sum of w squared, or the absolute value of w, depending on how you're doing it. Now remember, we talked about error, whether we either square it or we absolute value it, because that removes the plus or minus sign on there. And there's reasons to do it either way, but it is more common to square the value. And then we have our, in this case, the lambda is going to be the penalty for the errors. We've thrown in a Greek character for you just to confuse everybody. And w is the slope of the curve of the line. So we're going to look at this, and we're going to draw a line. This is going to be like a linear regression model. So if you had in sklearn, you could import just a standard linear regression model. It would plot this line across whatever data we're working on. And we look at this, and of course we're just extrapolating this. I know they use some specific data, but don't want to get into the actual domain. And so for a linear regression line, let's consider 2 points that are on the line. And we'll go ahead and have a loss equals 0, considering the 2 points on the line. We'll go ahead and do lambda equals 1. We'll set our w is going to be 1.4. Then the cost function equals 0 plus 1 times 1.4 squared, which equals 1.96. So really don't get caught up too much in the math on this, other than understanding that this is something that's very easy for a computer to calculate. And if you ever see the loss plus the lambda times w, the sum is w squared. And then let's say we have a ridge regression line, and it does this. We go ahead and plot it, and we do the calculations on the data. And for the ridge regression, let's assume a loss equals 0.3 squared plus 0.2 squared equals 0.13. So when they put all the calculations through of the 2 points, we end up with a 0.62. So we've now had a linear regression model. We now had a ridge regression model. And the ridge regression model plots a little differently than the standard linear regression model. And comparing the two models with all the data points, we can see that the ridge regression line fits the model more accurately than the linear regression line. And I find this true on a lot of data I work with. I'll end up using either the ridge regression model or the lasso Mars regression model for fitting, especially dealing with a lot of like stock markets daily setup. They come out slightly better. You get a slightly better fit. And so we have our lasso. We just talked about lasso coming in here. And the cost function equals, instead of doing a squared, we're just going to do the absolute value. And so if you remember, this is where ridge regression changes. Where's my ridge regression model? We're squaring the value here. And if you look at this, we're not squaring the value. We're just finding the absolute value on here. And so the loss of the squared individuals. And here is our lambda symbol again, penalty for errors, and w equals the slope of the curve. And comparing the two models with all the data points, we can see that the lasso regression line fits the model more accurately than the linear regression line. And this is, like I said, I use these two models a lot. The ridge, and this is important, this is kind of the meat of the matter. How do you know which one to use? Some of it is you just do it a bunch of times and then you figure it out. Ridge regularization is useful when we have many variables with relatively smaller data samples. The model does not encourage convergence towards zero, but is likely to make them closer to zero and prevent overfitting. The Lasser regularization model is preferred when we are fitting a linear model with fewer variables. So in the iris thing, we had 4 or 5 variables as we measured the different leaf pieces. You might be doing the measurements on the cancer project, which has 36 different variables. So as we get down to the iris with 4 variables, Lasso-LAR will probably work pretty good, where you might use the ridge regularization with more if you have something significantly larger. And it encourages the coefficients of the variables to go towards zero because of the shape of the constraint, which is an absolute value. And with any of this, we want to go ahead and do a demo in Lasso and ridge regression. So let's take a look and see what that looks like in our code and bring up our Jupyter notebook. We'll start with our imports. Pandas is PD, import numpy is np, import matplotlib as plt, sklearn, we're going to import our data sets. It's kind of more generic. We usually just import one data set instead of all of them, but you know, quick and dirty when you're putting some of these together. We have our sklearn model selection. We're going to import our train test split for splitting our data up, and then we'll bring in our linear regression model. And we'll go ahead and run these just to load them up, and then load our data set. We were just talking about that. You could just have imported the load Boston and Boston data set in there instead of loading all the data sets. And then once we've loaded our data set, we want to go ahead and take a look at that data and see what we got here. Let me just go ahead and pop that down there, and go ahead and run it. And so we've gone ahead and taken our Boston data. We're going to we put it into our pandas data frame, the Boston data set, and then the Boston columns. So we want to see what's going on with them. We have our target, we have the house price, etc. And so our x equals Boston I location. Now remember, in pandas, the new updates to pandas, they want I location if you're going to pull data. We used to be able to leave this off, but it does something different. It creates a slice versus a direct setup. So make sure you're using that I location and the output. So this is all just bringing our data together. And we can see here, if we do, we print the Boston pandas head, we can see here all of our different aspects we're looking for. And if you're following the X and the Y, the X is everything except for the last column, where Y is all the, that's what this means, all the rows except for the last column, and then Y is all the rows but just the last column. So Y is our house price, and the X is the Crim, Zian, Industry, Chas, Knox, and all these other different statistics they've collected for house sales in Boston. There we go. Whoops, control. So we'll go ahead and split our data. X train and our X test, Y train, Y test equals the train test split, which we imported. And we have our Boston. You could have easily used the X and Y on here as opposed to Boston I location. And we'll create our test size. We're going to take 25% of the data and put it in as a test. And then we'll go ahead and run this. Need an extra drink there. So we have our train and test, and then of course the print the train data shape. I love doing this kind of thing whenever I'm working with this data. Print out the shape, make sure everything looks correct, so that we have 127 by 13 and 127 by 1, 379 by 13. They should match. And if the data sets are not quite matching, then you know something's wrong and you're going to get all those errors. I don't know how many times I've gone through here and it's dropped a row on one of them and not on the other, or something weird has happened when I'm cleaning the data. This is pretty straightforward and simple because the data comes in a nice prepackaged and is all clean for you. So let's go ahead and apply the multiple linear regression model. And we'll call this LREG, linear regression. And we're going to go ahead and fit that linear regression model to X-train and Y-train. Then we'll generate the prediction on the test set. So here's our LREG Y predict with our X test going into the prediction. And let's calculate that mean square error, MSE. I told you you'll see MSE used a lot. People use it in variables and things like that. It's pretty common. And we get our mean squared error equals, this is just the basic formula we've already been talking about. What's the difference squared? And then we look for the average of that. And we'll go ahead and just run this. And you can see when we get through the end of this, we have our mean square error on test, we have our total, and then we have each column coming down. And at this point, unless you really know the data you're working with, it's not going to mean a whole lot. So if it's in your domain, you might know what you're looking at when you see these kinds of numbers coming up. But if it's not, it's just a bunch of numbers, and that's okay. At least that's okay for this demo. And then we're going to go ahead and plot these so we can see what's going on. And this is always kind of fun. It's always nice to have a nice visual of what you're looking at. And you can see here, when we plot the coefficient scores on here, and the guys in the back did a great job putting some pretty colors together, making it look nice, and setting up the columns. You can see here, your Knox has like just a huge coefficient. When I look at a table like this, I look for what has very little different coefficients. They're not using a huge change, and what has huge changes. And that flags you for all kinds of things as you're working with the data, but it depends so much on the domain you're working with. These are great things, though, as just a quick look to see what's going on with your data and what you're looking for. And of course, once we look at this, now our motive is to reduce the coefficient score. So now we want to take these and bring them down as much as we can. And for that, we're going to work with the ridge regression on here. So let's start by going ahead and we're going to import our ridge model, the ridge regression from the sklearn library or the scikit. And we're going to go ahead and train the model. So here's our ridge, r equals alpha equals 1. And I mentioned that earlier. When I work with the ridge model, you'll see alpha equals 1. If you set alpha equal to 0, that's a standard linear regression model. So you have alpha equals 1, 2, 3, 4, and you usually use 1, 2, or 3, 4 and a standard integer on there. And we'll go ahead and fit the ridge model on there with our X-train and our Y-train data, generate a prediction for that, for our X test, and we'll calculate the mean square error, just like we did before. This should all look familiar. And we'll go ahead and print that out, and we'll look at the ridge coefficients for our data and see what that looks like. Now, if I jump up and down between these two, you'll get a headache. You'll still see the Knox value. Let's just look at the Knox because that was the biggest value. It's a -9 here. And if we go back up here, the Knox value is a -18. So right off the bat, I'm seeing a huge change in the biggest coefficient there. So if we're going to do that nice setup, we want to go ahead and just print it and see what that looks like. Here we go. And we've set up our plots, subplots, and again, the team put together some nice colors so it makes it look good. And we're doing an X bar based on the columns. And our L-regress coefficients, color equals color, X spine bottom, and so forth. So just puts together a nice little graph. And you're starting to see, when you compare this, if you put it on the same graph as this one up here, this is up here at -18. This is at -9. And so this graph is half the size of the graph above. The same thing with these values here. They might look the same, but they're actually all almost half the value on here. And then finally, you can do the same thing for the lasso regression. This will all look very similar as far as what we worked on before. And I'm just going to go ahead and print that on here and run it. And again, let's go up to Knox. Look where Knox is. It's all the way down to 0. And if we look at our next biggest coefficient, it's minus 0.8. And really, here's our 22.73. We go up here, 16.7. And we go up here and we look at the same number, 16.69. And so we look at this, if I was running this and working on a project with this, I would look at these numbers. I start with the 16.69, come down here and compare it to 16.78. 6.9 is better than 7.8. So from the very beginning, we might start looking at this first model for overall predicting. But there's other factors involved. We might know that the Knox value is central and the other ones aren't quite as good. And so we might start looking at just certain setups, like what is this particular coefficient, because it might have a certain meaning to us and so forth. And so you got to look at all those different items in there. Again, but the bottom dollar is our first model did better than our other two models. Our mean square error on the test set continues to come down on this. Dimensionality reduction. Dimensionality reduction refers to the technique that reduces the number of input variables in a data set. And so you can see on the table on the right shows the orders made at an automobile parts retailer. The retailer sells different automobile parts from different companies. And you can see we have company BPAX, Isomax, and they have the item, the tire, the axle, an order ID, a price number, and a quantity. In order to predict the future sales, we find out that using correlation analysis that we just need 3 attributes. Therefore, we have reduced the number of attributes from 5 to 3. And clearly we don't really care about the part number. I don't think the part number would have an effect on how many tires are bought. And even the store, who's buying them, probably does not have an effect on that. In this case, that's what they've actually done, is remove those. And we just have the item, the tire, the price, and the quantity. One of the things you should be taking away from this is, in the scheme of things, we are in the descriptive phase. We're describing the data, and we're pre-processing the data. What can we do to clean it up? Why dimensionality reduction? Well, number one, less dimensions for a given data set means less computation or training time. That can be really important if you're trying a number of different models and you're rerunning them over and over again. And even if you have 7 gigabytes of data, that can start taking days to go through all those different models. So this is huge. This is probably the hugest part as far as reducing our data set. Redundancy is removed after removing similar entries from the data set. Again, pre-processing, some of our models, like a neural network, if you put in 2 of the same data, it might give them a higher weight than they would if it was just one. So we want to get rid of that redundancy. It also increases the processing time if you have multiple data coming in. Space required to store the data is reduced. So if we're committing this into a big data pool, we might not send the company that bought it. Why would we want to store 2 whole extra columns when we add it into that pool of data? Makes the data easy for plotting in 2D and 3D plots. This is my favorite part. Very important. You're in your shareholder meeting. You want to be able to give them a really good, clear, and simplified version. You want to reduce it down to something people can take in. It helps to find out the most significant features and skip the rest, which also comes in post-scribing. Leads to better human interpretation. That kind of goes with number 4, where it makes data easy for plotting. You have a better interpretation when we're looking at it. Principal component analysis. So what is it? Principal component analysis is a technique for reducing the dimensionality of data sets, increasing interpretability, but at the same time minimizing information loss. So we take some very complex data set with lots of variables, we run it through the PCA, we reduce the variables. We end up with a reduced variable setup. This is very confusing to look at, because if you look at the end result, we have the different colors all lined up. So what we're going to take a look at is, let's say we have a picture here. Let's say you are asked to take a picture of some toddlers and you are deciding which angle would be the best to take the picture from. So if we come up here and we look at this, we say, okay, this is, one angle. We get the back of a lot of heads, not many faces. So we'll do it from here. We might get the one person up front smiling. A lot of the people in the class are missing, so we have a huge amount off to the right of blank space. Maybe from up here, again, we have the back of someone's head. And it turns out that the best angle to click the picture from might be this bottom left angle. You look at it and you say, hey, that makes sense. It's a good configuration of all the people in the picture. Now, when we're talking about data, it's not, you really can't do it by what you think is going to be the best. We need to have some kind of mathematical formula so it's consistent and so it makes sense in the back end. One of the projects I worked on many years ago had something similar to the iris. And if you've ever done the iris data set, it's probably one of the most common ones out there, where they have the flower and they're measuring the stamen in the petals, and they have width and they have length of the petal. Instead of putting through the width and the length of the petal, we could just as easily do the width to length ratio. We can divide the width by the length and you get a single number where you had 2. That's the kind of idea that's going on into this, in pre-processing and looking at what we can do to bring the data down. The very simplified example on my iris petal example. When we look at the similarity in PCA, we find the best picture or projection of the data points. And so when we look down at from one angle, we've drawn a line down there, we can see these data points based on, in this case, just 2 variables. Now keep in mind, we're usually talking about 36, 40 variables. Almost all of your business models usually have about 26 to 27 different variables they're looking at. Same thing with like a bank loan model. We're talking 26 to 36 different variables they're looking at that are going in. So what we want to do is we want to find the best view. In this case, we're just looking at the XY. We look down at it and we have our second idea, PC2. And again, we're looking at the XY, this time from a different direction. Here, for our ease, we can consider that we get 2 principal components, namely PC1 and PC2. Comparing both the principal components, we find the data points are sufficiently spaced in PC1. So if you look at what we got here, we have PC1. You can see along the line how the data points are spaced versus the spacing in PC2. And that's what they're coming up with. What is going to give us the best look for these data points when we combine them? And we're looking at them from just a single angle. Whereas in PC2, they are less spaced, which makes the observation and further calculations much more difficult. Therefore, we accept the PC1 and not the PC2 as the data points are more spaced. Now, obviously, the back-end calculations are a little bit more complicated when we get into the math of how they decide what is more valuable. This gives you an idea, though, that when we're talking about this, we're talking about the perspective, which would help in understanding how PCA analysis works. What we want to go ahead and do is dive into the important terminologies under PCA. And important terminologies are views, the perspective through which data points are observed. And so you'll hear that if someone's talking about a PCA presentation and they're not taking the time to reduce it to something that the average person, shareholders, can understand, you might hear them refer to it as the different views. What view are we taking? Dimension, number of columns in a data set are called the dimensions of that data set. And we talked about, you'll hear features, dimensions. Now I was talking about features. There's usually, when you're running a business, you're talking 25, 26, 27 different features minimal. And then you have the principal component, new variables that are constructed as linear combinations or mixtures of the initial variables. Principal component is very important. It's a combination. If you remember my flower example, it would be the width over the length of the petal as opposed to putting both width and length in. You just put in the ratio instead, which is a single number versus 2 separate numbers. Projections. The perpendicular distance between the principal component and the data points. And that goes to that line we had earlier. It's that right angle line of where how all those points fall onto the line. Important properties. Important properties. Number of principal components is always less than or equal to the number of attributes. That just makes common sense. You're not going to do 10 principal properties with only 3 features. You're trying to reduce them, so it's just kind of goofy, but it is important to remember that. People will throw weird code out there and just randomly do stuff instead of really thinking it through. Principal components are orthogonal. And this is what we're talking about, that right angle from the line. When we do PC1, we're looking at how those points fall on to that line. Same thing with PC2. And we want to make sure that PC1 does not equal PC2. We don't want to have the same 2 principal points when we do 2 points. The priority of principal components decreases as their numbers increase. This is important to understand. If you're going to create one principal component, everything is summarized into that one component. As we go to 2 components, the priority, how much it holds value, decreases as we go down. So if you have 5 different points, each one of those points is going to have less value than just the one point, which has everything summarized in it. How PCA works. I said there was more in the back end when we talk about the math. This is what we're talking about, is how does it actually work. So now we have understanding that you're looking at a perspective. Now we want to see how that math side works. PCA performs the following operations in order to evaluate the principal components for a given data set. First, we start with the standardization. Then we have a covariance matrix computation. And we use that to generate our igene vectors and igene values, which is the feature vector. And if you remember, the igene vector is like a translation. If we're moving the data from x equals 1 to x equals 2, or whatever, altering it, and the igene value is the final value that we generate. When we talk about standardization, the main aim of this step is to standardize the range of the attributes so that each one of them lie within similar boundaries. This process involves removal of the mean from the variable values and scaling the data with respect to the standard deviation. And you can see here we have z equals the variable values minus the mean over the standard deviation. The covariance matrix computation. Covariance matrix is used to express the correlation between any 2 or more attributes in multi-dimensional data set. The covariance matrix has the entries as the variance and the covariance of the attribute values. The variance is denoted by var and the covariance is denoted by cov. On the right, we can see the covariance matrix for 2 attributes and their values. When we do a hands-on look at the code, we'll do a display of this so you can see what we're talking about and what that looks like. For now, you can just notice that this is a matrix that we're generating with the variance and then the covariance of x to y. On the right side, we can see the covariance table for more than 2 attributes in a multi-dimensional data set. And this is what I was talking about. We usually are looking at not just 1 feature or 2 features. We're usually looking at 25, 30 features going on. And so if we do a setup like this, we should see all those different features as the different variables. Covariance matrix tells us how the 2 or more variables are related. Positive covariance indicate that the value of one variable is directly proportional to the other variable. Negative covariance indicate that the value of one variable is inversely proportional to the other variable. That is always important to note whenever we're doing any of these matrices, that we're going to be looking at that positive and negative, whether it's inverted or not. And then we have the igene values and the igene vectors. Igene values and igene vectors are the mathematical value that are extracted from the covariance table. They are responsible for the generation of a new set of variables from the old set of variables, which further lead to the construction of the principal components. Igene vectors do not change directions after linear transformation. Igene values are the scalars or the magnitude of the igene vectors. And again, this is just transforming that data. So we're going to change the vector b to the b prime as denoted on the chart. And so when we have like multiple variables, how do we calculate that new variable? And then we have feature vectors. Feature vectors is simply a matrix that has eigenvectors of the components that we decide to keep as the columns. Here we decide whether we must keep or discard the less significant principal components that we have generated in the above steps. This becomes really important as we start looking at the back end of this, and we'll do this in the demo, but one of the more important steps to understand. And so we have the PCA example. Consider matrix X with n rows or observations and k columns or variables. Now for this matrix we would construct a variable space with as many dimensions as the variable. But for our simplicity, let's consider this 3 dimensions for now. Now each observation, row of the matrix X, is placed in the k-dimensional variable space, such that the rows in the data table form a swarm of points in this space. Now we find the mean of all the observations and then place it along the data points on the plot. The first principal component is a line that best accounts for the shape of the point swarm. It represents the maximal variance direction in the data. Each observation may be projected onto this line in order to get a coordinate value along the PC1. This value is known as a score. Usually only one principal component is insufficient to model the systematic variation for a data set. Thus, a second principal axis is created. The second principal component is oriented such that it reflects the second largest source of variation in the data. While being orthogonal to PC1, PC2 also passes through the average point. Let's go ahead and pull this up and just see what that means inside our Python scripting. I'm going to use the Anaconda Navigator, and I will be in Python 3.6 for this example. I believe there's even like a 3.9 out. I tend to stay in 3.6 because a lot of the models I use, especially with the neural networks, are stable in 3.6. And then we open up our Jupyter. I'm in Chrome, and we go ahead and create a new Python 3. And for ease of use, our team in the back was nice enough to put this together for me. And we'll go ahead and start with the libraries. The first thing I like to do whenever I'm looking at any new setup, well, you know what, let's do the libraries first. We're going to do our basic libraries, which is matplotlib, the PLT from the matplotlib library. Pandas, our data frame, PD, numpy, our numbers array, NP, Seaborn for graphing, SNS, that goes with the plot that actually sits on matplotlib library, so the Seaborn sits on there. And then we have our ampersand, because we're in Jupyter Notebook, matplotlib library inline. The newer version actually doesn't require that, but I put it in there anyway just because I'm so used to it. And then we want to go ahead and take a look at the data. And in this case, we're going to pull in, certainly you can have lots of fun with different data, but we're going to use the cancer data set. And one of the reasons the cancer data set is it has like 36, 35 different features. So it's kind of fun to use that as our base for this. And we'll go ahead and run this and look at our keys. And the first thing we notice in our keys for the cancer data set is we have our data, we have our target, our frame, target names, description, feature names, and file name. So what we're looking for in all this is, well, let's take a look at the description. Let's go in here and pull up the description on here. I'm not going to spend a huge amount of time on the description because we don't want to get into a medical domain. We want to focus on our PCA setup. What's important is you start looking at what the different attributes are, what they mean. If you were in the medical field, you'd want to note all these different things, what they're measuring, where it's coming from. You can actually see the actual different measurements they're taking. No missing attributes. We page all the way to the bottom. And you're going to have your data, in this case our target. And if you dig deep enough to the target, let's actually do this. Let's go ahead and print target names. Real quick here, I always like to just take a look and see what's on the other end of this. Target names. Run that. And so the target name is it malignant or is it benign? So in other words, is this dangerous growth or is it something we don't have to worry about? That's the bottom line with the cancer in this case. And then we can go ahead and load our data. And you know what, let me go up just a notch here for easy of reading. It's hard to get that just right. I guess I'll have to do. So let's go ahead and look at our data. We're going to use our pandas, and we're going to go ahead and do our data frame. It's going to equal cancer data. Columns equals cancer, feature equals feature names. So remember up here, we already loaded the names up of the features in there. What is going to come out of this? Let me just see if I can get to that. It's at the top of target names. That's just this list of names here in the setup. And we can go ahead and run this code, and it'll print the head. And you can see here we have the mean radius, the mean texture, mean perimeter. I don't know about you, this is a wonderful data set if you're playing with it, because like most of the data that comes in, half the time we don't even know what we're looking at. We're just handed a bunch of stuff as a data scientist going, what the heck is this? And so this is a good place to start because this has a number of different features in there and we have no idea what these features means or where they come from. We want to just look at the data and figure that out. And now we actually are getting into the PCA side of it. As we've noticed before, it's difficult to visualize high-dimensional data. We can use PCA to find the first two principal components and visualize the data, this new two-dimensional space, with a single scatter plot. Before we do this, we need to go ahead and scale our data. Now, I haven't run this to see if you really have to scale the data on this, but as just a general run time, I almost do that as the first step of any modeling, even if it's pre-modeling as we're doing here. In neural networks, that is so important. With PCA visualization, it's already going to scale it when we do the means and deviation inside the PCA. But just in case, it's always good to scale it. And then we're going to take our PCA with the scikit-learn uses very similar process to other pre-processing functions that come with scikit-learn. We instantiate a PCA object, find the principal components using the fit method, then apply the rotation and dimensionality reduction by calling transform. We can also specify how many components we want to keep when creating the PCA object. And so the code for this, oops, getting a little bit ahead. We go ahead and run this code. So the code for this is from sklearn decomposition import PCA. PCA equals PCA and components equals 2. And that's really important to note that because we're only going to want to look at 2 components. I would never go over 4 components, especially if you're going to demo this with somebody else. If you're showing this to the shareholders, the whole idea is to reduce it to something people can see. And then the PCA fit, we're going to is going to take the scaled data that we generated up here, and then you can see we've created our PCA model with in components equals 2. Now, whenever I use a new tool, I like to go in there and actually see what I'm using. So let's go to the Scikit webpage for the PCA. And you can see in here, here's our call statement. It describes what all the different setups you have on there. Probably the biggest one to look at would be, well, the biggest one is your components. How many components do you want, which you have to put in there pretty much. And then you also might look at the SVD solver. It's on auto right now, but you can override that and do different things with it. It does a pretty good job as it is. And if we go down, all the way down to, here we go, to our methods, if you notice we have fit and we have fit transform. Nowhere in here is predict, because this is not used for prediction. It's used to look at the data. Again, we're in the describe setup. We're fitting the data. We're taking a look at it. We've already looked at our Minimum, maximum, we've already looked at what's in each quarter. We've done a full description of the data. This is part of describing the data. That's the biggest thing I take away when I come zooming in here. And of course, they have examples of it down here if you forget. And the biggest one, of course, is the number of components. And then, the rest you can play with. The actual solver, whether you're doing a full or randomized, there's different things. It does pretty good on the auto. And now we can transform this data to its first two principal components. And so we have our XPCA. We're going to set that equal to PCA transform scaled data. So there we go. There's our first transformation. And let's just go ahead and print the scaled data shape and the XPCA data shape. And the reason we want to do this is just to show us what's going on here. We've taken 30 features. I think I said 36 or something like that, but it's 30. And we've compressed it down to 2 features. And we decided we wanted 2 features. And that's where this comes from. We on 2 features. So let's go ahead and plot these and take a look and see what's going on. And we're just going to use our PLT figure. We're going to set the figure size on here. Here's our scatter plot, XPCA, X underscore PCA of 1. These are our 2 different perceptions we're using. And then you'll see right here, C for color, cancer equals target. And so remember, we have 0, we have 1. And if I remember correctly, 0 was malignant, 1 was benign. So everything in the 0 column is going to be one color, and the other color is going to be 1. And then we're going to use the plasma map, just kind of telling you what color it is. Add some labels, first principal component, second principal component. And we'll go ahead and run this. And you can see here, instead of having a chart, one of those heat maps with 30 different columns in it, we can look at this and say, hey, this one actually did a pretty good job of separating the data. And a couple things when I'm looking at this that I notice is, first, we have a very clear area where it's clumped together, where it's going to be benign. And we have a huge area, it's still clumped together, more spread out, where it's going to be malignant. Or I think I had that backwards. And then in the middle, because we're dealing with something, in this particular case, cancer, we would try to separate, I would be exploring how to separate this middle group out. In other words, there's an area where everything overlaps, and we're not going to have a clear result on it. Just because those are the people you want to go in there and have extra tests, or treat it differently, versus going in and saying just cutting into the cancer so that the body absorbs it and it dissipates, versus actively going in there, removing it, testing it, going through chemo and all the different things. That's a big difference, you know, as far as what's going to happen here. And that middle line where they overlap is going to be huge. That's domain specific. Going back to the data, we can see here, clearly by using these 2 components, we can easily separate these 2 classes. So the next step is, what does that mean? Interpreting the components. Unfortunately, with this great power of dimensionality reduction comes the cost of not being able to easily understand what these components represent. I don't know what principal component 1 represents, or second principal. The components correspond to combinations of original features. The components themselves are stored as an attribute of the filtered PCA object. And so when we look at that, we can go ahead and look at the PCA components. This is in our model we built. We've trained it. We can run that, and you can see here's the actual components. It's the 2 components each have their own array. And within the array, you can see what the scores they're using. And these actually give weight to what features are doing what. So in this NumPy matrix array, each row represents a principal component, and each column relates back to the original features. What's really neat about this is we can now go in reverse and drop this onto a heat map and start seeing what this means. And so let me go ahead and just put this down. Oops, I already got it down here. We go ahead and put this in here. We're going to use our dfcomp data frame, and we do our PCA components. And I want you to notice how easy this is. We're going to set our columns equal to cancer feature names. That just makes it really easy. And we're dumping it into a data frame. What's neat about a data frame is when we get to Seaborn, it will pull that data frame apart and set it up for us the way we want. And so we're just going to do the Seaborn heat map of our data frame composition, and we'll use the plasma coloring. And it creates a nice little color graph here. You can see we have the mean radius and all the different features along the bottom. On the right, we have a scale, so we can see we have the dark colors all the way to the really light colors, which are what's really shining there. This is like the primary stuff we want to look at. So this heat map and the color bar basically represent the correlation between the various features and the principal component itself. So, very powerful map to look at, and then you can go in here, and we might notice that the mean radius, look how on the bottom of the map it is on some of this. So you have some interesting correlations here that change the variations on that and what means what. This is more when you get to PostScribe, you can also use this to try to guess as what these things mean and what you want to change to get a better result.
In this session, we will briefly understand what coronavirus really is and the various symptoms of coronavirus. Then, we'll look at the global impact of coronavirus in terms of the total cases, the deaths reported, the fatality rate, and the tests carried out so far by different countries. After that, we will perform an analysis using SVM and polynomial regression in Python to predict the number of upcoming cases from the 28th of April to the 17th of May. The data we have taken is from the 22nd of January to the 27th of April. Then, we will analyze the model using charts and graphs. And finally, we will discuss the various safety measures you can take to ensure you are safe and not attacked by coronavirus. So what is coronavirus? Coronavirus, or COVID-19, is an infectious disease caused by a newly discovered coronavirus that is believed to have emerged from a seafood market in Wuhan, China during December 2019. It is zoonotic, so it's a disease that can be transmitted from animals to people, or more specifically a disease that normally exists in animals but that can infect humans too. The virus that causes COVID-19 is mainly transmitted through droplets generated when an infected person coughs, sneezes, or exhales. These droplets are too heavy to hang in the air and quickly fall on floors or surfaces. It appears that symptoms show up in people within 14 days of exposure to the virus. With that, now let's look at the various symptoms of COVID-19. A patient with coronavirus can show generic symptoms such as cough, fever, shortness of breath, and muscle pain. They can also have a sore throat, headache, and loss of taste or smell. They are also expected to have Middle East Respiratory Syndrome or MERS and Severe Acute Respiratory Syndrome or SARS. Middle East Respiratory Syndrome is a viral respiratory illness caused by a coronavirus. It is a contagious, sometimes fatal respiratory illness. It often spreads through close contact with an infected person. SARS is a contagious and sometimes fatal respiratory illness caused by a coronavirus. It appeared in 2009 in China. It spread worldwide within a few months, although it was quickly contained. SARS is a virus transmitted through droplets that enters the air when someone with the disease coughs, sneezes, or talks. Now, let's look at the impact of coronavirus worldwide. The maps and the charts that I am going to show you now have been taken from an organization called Our World in Data. They largely focus on problems that the world faces, such as poverty, different diseases, hunger, climate change, existential crisis, and inequality. Their main goal is to research and use data to make progress against the world's largest problems. The map that you see on your screens shows the total number of confirmed COVID-19 cases till the 26th of April. Below, you can see the color scale ranging from 0 to 1 million. The countries with the least number of cases are marked in light orange color. The countries with cases between 5,000 to 10,000 cases have been depicted using orange color. The countries with cases above 1 lakh are shown using red color, while those above 5 lakhs have a dark red color. You can see from the map, African nations have fewer cases compared to nations in Asia, Europe, and America. China has close to 84,000 cases. India has around 26,500 cases as of April 26th. Iran has nearly 89,000 cases. Now if you look at Australia, it has cases of around 6,700. In North America, the United States has the highest number of cases, which is actually the highest throughout the world. In South America, Brazil has the maximum number of cases. The next map shows the confirmed cases of countries on the Asian continent. China, Iran, Turkey, India, and Saudi Arabia have the highest number of cases. Then we have the map of Europe. In Europe, countries such as Italy, France, Germany, the United Kingdom, Spain, and Russia have the highest number of cases. Moving ahead, you can see a graph of certain selected countries and the total confirmed cases. I have filtered out the total world cases, then countries like the United States, Spain, Italy, Germany, France, China, and India. You will learn how to create a similar graph when we will do our prediction analysis. Let's now have a look at the total number of daily confirmed cases. So on the 26th of April, the United States had around 48,500 cases, Russia had around 6,000 cases, Brazil had nearly 5,500 cases, followed by the United Kingdom with close to 5,000 cases. The number of confirmed cases is lower than the number of total cases, the reason being limited testing in different countries across the world. Now looking at the total deaths reported across the world on this map, the United States has the highest number with over 53,000 deaths so far, followed by Italy, France, the United Kingdom, and Germany. Next, you can see a graph of a few countries and their total death cases till the 26th of April. You can see the United States, Spain, Italy, France, China, and India here. We will see how to build a similar graph in our demo. Up next on your screens is the map of different countries and their fatality rate. Fatality rate is actually the ratio between the confirmed deaths and confirmed cases. France has the highest fatality rate with over 18.22%, followed by the United Kingdom at 13.69% and Italy at 13.51%. Moving ahead, the next map shows the total number of COVID-19 test numbers. The United States has conducted over 5 million tests so far, followed by Russia with over 2.88 million tests. Germany, Turkey, Canada, and India have been conducting COVID-19 tests in large numbers to deal with the situation. Now each country is dealing with this pandemic within its own capacity. To make sure the situation doesn't worsen, most affected countries have gone for a lockdown. But does lockdown work? Well, the research says yes. On the screens, you can see the number of days some countries have enforced a partial or full lockdown to curb the spread of coronavirus. This information has been taken from one of India's leading media groups, India Today Data Intelligence Unit. The orange color represents full lockdown, while the yellow color depicts partial lockdown. Countries like Australia, India, Belgium, the United Kingdom, China, the United States, France, Spain, and others already have announced lockdown for more than 40 days. To make sure the lockdowns don't extend further and the situation improves, people are being advised to stay at home and avoid public gatherings. Now, let's look at where India stands with its battle for coronavirus. As per the Press Information Bureau of India or PIB, here are the figures and the situation report till 5 p.m. on the 26th of April. The states that have been affected the most are Maharashtra, Gujarat, Delhi, Madhya Pradesh, Uttar Pradesh, and Tamil Nadu. Maharashtra has over 7,600 cases, followed by Gujarat with over 3,000 cases. Maharashtra also has the highest number of deaths reported, which stands at 323. Next is Gujarat with 133, followed by Madhya Pradesh at 99 deaths so far. There are still 312 cases yet to be assigned to the states which are under the process of contact tracing. You can see on the top there are more than 27,000 confirmed cases in India, out of which 20,177 are active cases. More than 6,000 people have recovered from coronavirus, while the death tally stands at 872. The government is doing its best to control the situation. Please follow the rules and guidelines issued by the local and central authorities. This will help us fight the situation together effectively. Now coming to the most important part of this session, which you guys have been waiting for a while, the coronavirus outbreak prediction analysis. We will analyze the outbreak of coronavirus in the coming days across various countries worldwide, visualize them using charts and graphs, and predict the number of upcoming cases for the next 20 days using polynomial regression and support vector machines model in Python. Our data has information from the 22nd of January to the 28th of April. The datasets we will be using are taken from the repository operated by the Johns Hopkins University Center of Systems Science and Engineering. Let me show you where you can locate the datasets. So here is the GitHub repository where you can find the datasets and a few other resources. It is being updated on a regular basis. I would encourage you to go through this link once. Now, let me take you to the Jupyter notebook where I have already implemented the codes. I'll run through it and explain each cell of code to make you understand what it does. So this is my Jupyter notebook. First, we will import all the libraries necessary for this analysis. We are importing the NumPy and pandas that are used for numerical computations, data manipulation, and data analysis. Then, I'm importing the matplotlib library for creating data visualizations. Next, I'm also going to import random, math, and time libraries. After that, from the sklearn library, I'm importing the linear regression model as well as certain functions such as train test split and polynomial features to build our polynomial regression. SVR will help us create the support vector machines model. We will also use sklearn matrix to import functions such as mean squared error, mean absolute error, and so on. This we will use for calculating the accuracy of our model. Let me now run this cell by hitting Shift plus Enter. So you can see we have successfully run the first cell. Now we will load our datasets. We'll be using 3 datasets for this demo. The datasets are present in a GitHub repository maintained by Johns Hopkins University. To import the datasets, I have used the pandas library and read_csv function. I provided the URL location of the files followed by the file name and the extension of the file, which is .csv. I have loaded these 3 datasets to 3 variable names. Now let's run the cells to import all the 3 datasets. So first I have imported the confirmed cases dataset. Now to display the dataset, I am using the .head function to see the top 5 rows from the data. If I scroll down, you can see our confirmed underscore cases dataset. We are displaying the first 5 rows from the dataset. It has information like province or the state, country or the region, the latitude, the longitude, and the date value starting from 22nd of January to the 27th of April. Now let me go ahead and import the deaths underscore reported dataset. And now to display the dataset, I have used the .head function. So this is how the deaths dataset looks like. Let me now go ahead and import the recovered underscore cases dataset. And now to display the head of the dataset. So here is how the recovered dataset looks like, or the recoveries dataset looks like. Finally, I load the dataset, which is all the latest updates from across the globe regarding confirmed cases, deaths, recovered and active cases. Let's see the head of this latest dataset. As you can see, it has information about the province or the state, country or the region, when it was last updated, the latitude and the longitude of the location, and it has data regarding the confirmed cases, the deaths reported, the recovered cases, the active cases, and so on. After that, I'm extracting all the column names from the confirmed cases data frame using the .keys function. If I run this, below you can see we have all the column names. Next, we are extracting only the date columns that have information of confirmed cases, death cases, and recovered cases using the .loc function. We are storing it in respective variables. The first parameter, that is colon, tells us we need all the rows from the data, while the second parameter tells us we need the data from the fourth column till the last column, which are the date values. Let me run it. Let's check the confirmed variable and see what it has. As you can see, it has the date columns from the 22nd of Jan till the 27th of April. In the next cell of code, I'm basically creating multiple empty lists to find the total cases worldwide, the total number of deaths so far, the mortality rate, the recovered cases, and the total active cases. I also want to find out the confirmed cases, deaths, and recoveries for few countries such as China, Italy, United States, Spain, France, Germany, UK, Russia, and India. So I have created empty lists for these countries as well. We will see how to append values to these empty lists in the next step. Let me just run it. Now, using a for loop, I am finding the total sum of confirmed cases, death cases, and recoveries made so far. These values I am appending to the empty lists, world cases, total deaths, total recovered, and total active cases. The total active cases are calculated as the confirmed cases minus the death cases minus the recovered cases. Now to calculate the mortality rate, I am using a simple formula, which is the sum of the total deaths divided by the total confirmed cases. The recovery rate is also calculated by dividing the total recovered cases with the total confirmed cases. Then, I am appending the values of confirmed cases for each country using the append function and selecting different countries for which we had created an empty list. Similarly, I'm also appending the values for deaths and recoveries made for each of these countries. Let's run it. Now you can check the world cases each day. So these are the world cases that have come up each day, and you can see the number has reached almost 30 lakhs now. Then you can see the total deaths so far globally. So these are the deaths reported each day across the globe. You can see there have been around more than 2 lakhs casualties so far. Let me collapse it. Next, I'm printing out the total sum of confirmed cases. So you can see it stands at around 30 lakhs 41,764. Similarly, let me print out the total death sum. So it's around 2 lakhs 11,167 as of 27th of April. Now also check the recovered sum. It's around 8 lakhs 93,967. You can also have a look at the cases based on individual countries. So here you can see the cases that have come up so far in the United States, which is US_cases. So United States has nearly 9 lakhs 88,197 cases. Let me collapse it. Now let's check for India as well. So in India, the total cases have reached 29,451. Let me collapse it further. You can also have a look at the recoveries for each country. Here I am printing out the recoveries made in Italy. Next, I want to analyze the data for understanding the daily increase in cases across the world, the daily casualties, and the daily recovery cases. For that, I'm using a user-defined function to track the daily increase. Let me run it. Okay. Now to find the total worldwide increase in cases, I am calling the above created user-defined function and assigning it to world daily increase variable. Similarly, I am using the same method to find the daily increase in cases for different countries. Let me show you the daily increase in confirmed cases for Spain. So yesterday, that is 27th of April, Spain had 2,793 cases. Now let's check for Germany also. As you can see, yesterday Germany had around 988 cases. In the next cell, I am finding out the daily death cases across the world as well as for a few countries. Let me run it. Let's check the daily deaths that have been reported in China. So these are the values of daily deaths in China. You can see the numbers have significantly reduced. Also, let's check for the United Kingdom as well. So on 27th of April, United Kingdom had 363 deaths reported. Moving ahead, I'm also calculating the daily recovery cases across the world and for some countries. Now let's go ahead and check the data from India in terms of the daily recovery cases. So these are the values. And if I scroll down, you can see yesterday, that is 27th of April, India had 614 recovered cases. Also, let's have a look at the world recovery cases. Here you can see on 27th of April, Nearly 28,234 people have recovered across the globe. With that, the next step is to visualize our data. So first, I am finding out the list of unique countries using the list function and passing the latest data variable to filter the different unique countries. So here you can see the list of different countries. Now the cell that you see on your screens, we are using these lines of code to find the country's confirmed cases, the death cases, active cases, recovery cases, and mortality rate. We are finding the sum of the cases and appending it to empty list that we have created. We are also removing the countries that have no cases at all. And finally, we are sorting the countries by the number of confirmed cases. So let me run it. In this cell, you will be visualizing the data using a gradient styled color map to see the country name, the number of confirmed cases, and the number of deaths, the number of recoveries, and so on. I have taken blue as my gradient. Let me run it. As you can see, we have an interesting table that looks really attractive. On the left, you can see the country names. The table has been sorted in descending order of confirmed cases. You can see the dark blue color depicts the countries with the highest number of cases. In this case, it's United States. Then we have Spain, Italy, and France. We also have Germany and United Kingdom. You can also see the number of deaths and recoveries in the middle of this table. And to the right, you can see the number of active cases and the mortality rate. You can see from the visual, Italy has the highest mortality rate, followed by the United Kingdom. Similarly, I am finding out the list of unique provinces using the list function and passing the latest data variable to filter out different provinces. In the next cell, we are finding the confirmed cases, the death cases, active cases, recovery cases, and mortality rate for each province of a particular country. We're also finding the sum of the cases and appending it to empty list that we have created. We are also removing the provinces that have no cases at all. And finally, we are sorting the provinces by the number of confirmed cases. So let's run it. In this cell, we'll be visualizing the data of different provinces using a gradient styled color map to see the province or the state names, the number of confirmed cases, the number of deaths, number of recoveries, and so on. I have taken red as my gradient. Let's run it. There you go. We have our visual here on the screen. New York State has the highest number of confirmed cases and the number of deaths as well. The Hubei province in China has had the highest recoveries, which is around 63,604. And to the extreme right, you can see the mortality rate. The next cell of code deals with handling missing values or NaN values. It is important to handle such values, otherwise your data would be noisy and messy and it will lead to inappropriate results. Now, I am plotting a horizontal bar graph to compare the number of cases in the United States and outside of United States. The outside United States cases have been calculated by subtracting the United States confirmed cases from the country confirmed cases worldwide. I have used plt.barh function to plot my horizontal bars. We have also given a title to this plot. Let me run it. So this is my bar graph. The blue bar represents the United States confirmed cases and the red bar represents the cases outside of United States. Now if you want to print the actual values of the cases in the United States and outside of United States, you can do that too. As you can see, there are nearly 19,58,592 cases outside of United States. In United States, there are nearly 9,38,154 cases, and the total cases stand at 28,96,746 cases. Then, I want to show only 10 countries with the most confirmed cases. The rest, I want to group it into the others category. So using two empty lists, I am going to find out the top 10 countries with the highest number of cases. The remaining I am categorizing under others. Now to show these countries, I have defined a function that will plot my horizontal bar graph. Let me run it. Now using plot underscore bar underscore graphs function, we will create the bar graph. I have used the visual underscore unique underscore countries and visual underscore confirmed underscore cases variables and given a title to the graph. So here is our horizontal bar graph. You can see the United States has the highest number of cases. The next is Spain. The United Kingdom is at the 6th position. Russia is at the 10th place. And on the top, you can see the others category as well. Now, we will create a pie chart to plot the same graph. For that, I have created another function called plot underscore pie underscore charts. Let me just run it. Now using plot underscore pie underscore charts function name, we will create the pie chart. I've again used visual underscore unique underscore countries and visual underscore confirmed underscore cases variables and given a title to the graph. There you go. We have our pie chart on the screen, and on the right you can see the legend which shows the different country names. The maximum area in the pie chart has been occupied by United States. Then we have the others category, followed by Spain, Italy and France. I'll follow the same procedure to show 10 provinces with the most confirmed cases. The rest I will group into the others category. For that, I will be using two empty lists, visual underscore unique underscore provinces and visual underscore confirmed underscore cases 2. Let's plot the graph using plot underscore bar underscore graphs function. So here you can see the bar graph. New York province or the New York state has the highest number of cases. Then we have New Jersey, followed by Hubei province in China and Massachusetts. And on the top you can see the others category. The next cell of code looks pretty complicated. It is essentially trying to plot a pie chart for different countries along with its several states and provinces. Here, we want to show only the top 10 states with the highest number of cases. Let me run it. Now, I want to show the pie chart for the United States and its top 10 states. Let me do that. As you can see, we have our pie chart, and on the right you can see we have the legend for 10 states. So the maximum area in the pie chart has been occupied by New York, and then we have the other states Next is New Jersey, followed by Massachusetts and California. Let me also check the confirmed cases for different states in France. I'll change this to France. So here is our pie chart, which has 10 different states in France. With that, let's now come to building our model using polynomial regression and support vector machines. In this step, I'm converting all the dates and the cases in the form of a numpy array using the np.array function. Let's run it. Since our prediction will be for the next 20 days, so I have created a variable called days_future and I have assigned a value of 20. Then I'm adding the last 20 days to the total number of days we have. Now let me show you the values of future_forecast. So here is a list of values. Basically, it's the number of total days. Next, we are converting all the integers into datetime values for better visualization. Now, it's time to split our data into training and testing sets. For that, I'm using the train_test_split function. I've taken days since 22nd of Jan and the world cases as my parameters. I'll be using 75% of data for training the model and 25% for testing the model. We will now transform our data for polynomial regression. For that, I will use the polynomial features function and fit_transform method to transform our training, testing and future forecast data. Next, I will build the polynomial regression model using the linear regression function, and I have used the linear_model.fit function to fit the training data. After that, I have used the predict function to predict the test data set values. Finally, I am printing the mean absolute error value and the mean squared error value as well. So you can see the results here. Let's now plot the graph between the test dataset and the values from the predicted polynomial regression model. So below you can see the graph here. The blue line represents the test data and the red line represents our polynomial regression predictions. Now, let's start building our model using a support vector machines algorithm. SVM uses different parameters to build a model. These parameters are kernel, C, gamma, epsilon, shrinking, and SVM_grid. Kernel specifies the kernel type to be used in the algorithm. It must be one of linear, poly, RBF, sigmoid, pre-computed, or callable. If nothing is given, RBF will be used by default. C is a regularization parameter. Gamma is the kernel coefficient of RBF, poly, and sigmoid. Epsilon specifies the epsilon tube within which no penalty is associated in the training loss function. Shrinking takes Boolean values, true or false. SVM grid has all the values parameters passed to it. Here, we are creating the support vector regressors and then using the fit function to fit our training dataset. Finally, we are predicting the values for future data as well. Let me now print the MAE and the MSE values and display the graph of the prediction. As you can see, the blue line represents the test data and the red line represents the SVM predictions. Now let's create some more visualizations to understand the model and our data better. Here, I'm plotting the number of coronavirus cases over time. I've used the adjusted dates and the world cases to plot the graph. I've also assigned the X labels and the Y labels. Let me run it. As you can see from the graph, the total number of cases have reached close to 30 lakhs now. Next. In this graph, we are showing the total number of coronavirus deaths over time. I've also used the X label and the Y label. You can see the total number of deaths have reached over 2 lakhs. Similarly, in the next graph, we can see the total number of recovered cases, which are more than 8 lakhs. Then, we are also looking at the total number of active cases across the globe. So here is the graph for that. You can see the number of coronavirus active cases over time. I am now creating a bar graph with adjusted dates and the world daily increase as my variables. As you can see, on some of the days, the cases have gone very high, reaching 100,000 in a day. The next graph we are plotting to show the world daily increase in confirmed death cases. So here is the bar graph for that. You can see there are certain days that have reported more than 10,000 deaths in a day. The next graph shows the world daily increase in confirmed recovery cases. So here is the graph for that. Moving ahead, I'll plot the graphs to show the number of coronavirus cases over time. Let's now plot the actual graph. I've taken adjusted underscore dates, world cases, linear underscore pred variables as my parameter. Let me run it. You can see this is our graph. The blue line represents the confirmed. We will check for the SVM model as well. So below is the graph. Again, now let me print out the predicted values from the polynomial regression model as a data frame. So you can see we have our predicted confirmed cases for the next 20 days. That is from the 28th of April to the 17th of May. Likewise, let me also print out the predicted values for the SVM model as a data frame. So here are our predicted values from the SVM model. In the next graph, we are plotting the deaths and the recoveries in the same graph. So here is our line graph. You can see clearly the number of recoveries are way higher than the number of deaths, which is actually a good sign. Moving forward, the next graph shows a line chart with the number of coronavirus deaths versus the number of coronavirus recoveries. So here is the graph. The x-axis has the number of recoveries and the y-axis has the number of total deaths. Now this cell of code looks pretty huge. We want to plot the total number of confirmed cases, the daily increase in confirmed cases, the increase in deaths, and the increase in recoveries for different countries across the globe. Let me run this cell. So using the country underscore plot function that was defined above, we will be plotting the data for various countries. Let me start with China first. So you can see there are 4 graphs in total. If I scroll down, the first you see here is China confirmed cases. Next is the China daily increase in confirmed cases. So you can see in one of the days it had a huge spike in the increase in confirmed cases. Then we have the China daily increase in deaths. And finally we have the daily increase in recoveries. Now let's check for Italy. Let me scroll down. You can see the same plots for Italy as well. The first we have total confirmed cases in Italy, which is nearly around 2 lakhs. Then we have the daily increase in confirmed cases. Next we have the Italy daily increase in deaths. And finally we have the increase in recoveries. Let's have a look at how the graphs for India looks like. You see the total well. Let's also see for the United States. So here you can see all the 4 graphs for the United States. Spain, France, Germany, and they have been depicted using different colors. On the top left you can see the legend. Now this graph looks similar to the one that we saw in our slides. Next, I'm plotting the total coronavirus death. So here is our graph. Finally, let us look at the total coronavirus cases in these countries. The last 3 graphs look similar to what we have used in the slides from our world in data. Now it's my responsibility to call out all the safety precautions that you should take to make sure you are safe from being attacked by coronavirus. First and foremost, do not panic. During these unprecedented times, if you feel you are showing symptoms of coronavirus, do not wait. Please consult a doctor immediately. Stay at home to ensure you are not exposed to the virus outside. Maintain social distancing with people if you are talking to someone outside and if someone is sick. Do not forget to wash your hands regularly using soaps, sanitizers, and other disinfectants. Always remember to wear a mask while you are going outside. Make sure to practice respiratory hygiene such as cover your mouth while coughing and try eating healthy food. All these precautions will help you avoid coronavirus and make sure you are safe and healthy.
Now moving on to the final section, let me tell you how Simplilearn can help you start your career in machine learning. So let me take you to our website first. Okay, so I am on the Chrome browser. Let me search for simplilearn.com, and here under what you want to learn, let me type machine learning. It will show me the relevant courses that Simplilearn offers in the machine learning category. So you can see here there are multiple courses. First let me open the first link, and let's open the second link as well. So this is the postgraduate program in AI and machine learning, which is in collaboration with Purdue University and IBM. If I scroll down, you can see the key features of this course. So we'll get Purdue Alumni Association membership, industry recognized IBM certificates, enrollment to Simplilearn's Job Assist. There's 25 plus hands-on projects on GPU enabled labs. You have 450 plus hours of applied learning, capstone projects in 3 domains, and much more. And here you can see on the right, this is the certificate that you will get after completing this program. And you will also get certificates recognized by IBM. And another key feature of this course is you can enroll to Simplilearn Job Assist program. So you will get IIM Jobs Pro membership for 6 months, resume assistance and career monitoring, there's interview preparation and career affairs. If I scroll further, here you can see the learning path, and you will learn about Python for data science, there's machine learning, deep learning with TensorFlow and Keras, there's advanced deep learning and computer vision. You will also learn about natural language processing, that is NLP, and speech recognition. We have reinforcement learning, and you also have the opportunity to select a few electives. So we have IBM Watson for chatbots, machine learning with R, there's Git and GitHub training, and 2 others. Here you can see the skills that will be covered. So you will learn about statistics, which is a core component of machine learning. You'll learn about Python, supervised learning, there's GANs, computer vision, TensorFlow, there's reinforcement learning, speech recognition. You will also learn about NumPy, Pandas and other libraries. And here you can see these are some of the tools that will be covered in this course. If I scroll further, now this is the important section. You can see the industry projects that you will get to work on. So this is on Twitter, there's one on Zomato, one on Uber, and Mercedes-Benz as well. Now they are our course advisors. So please go ahead and enroll to this postgraduate program in AI machine learning if you want to kickstart your career in machine learning. Now the next course we have is machine learning certification course. If I scroll down, you can see the details of this course. So you will gain expertise with 25 plus hands-on exercises. You will get to work on 4 real-life industry-based projects with integrated labs. There will be dedicated mentoring sessions from industry experts, 44 hours of instructor-led training with certification. Here on the right, you can see the skills that will be covered. So we learn about time series modeling, linear and logistic regression. You will also learn about support vector machines, k-means clustering, naive Bayes, decision trees, random forest, and you'll learn the concepts of bagging and boosting and deep learning fundamentals as well. Here you can see the course content. And if I scroll further, now these are the projects that you'll get to work on. And finally, you'll receive this certificate once you complete the course.
Thank you all for watching this full course video tutorial on machine learning with Python. I hope you liked it. If you have any questions, then please put them in the comments section. Our team will help you solve your queries. Thanks again. Stay tuned for more from Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.